The Physical Sciences in Ancient Greece. Plato's Timaeus and Republic. Although a great portion of the physical speculations of the Greek philosophers was fanciful and consisted of doctrines which were rejected in the subsequent progress of the inductive sciences, still, many of these speculations must be considered as forming a prelude to more exact knowledge afterwards attained, and thus as really belonging to the progress of knowledge. These speculations express, as we have already said, the conviction that the phenomena of nature are governed by laws of space and number, and commonly, the mathematical laws which are thus asserted have some foundation in the facts of nature. This is more especially the case in the speculations of Plato. It has been justly stated by Professor Thompson, A. Butler's Lectures, 3rd Series, Lect. I note 11, that it is Plato's merit to have discovered that the laws of the physical universe are resolvable into numerical relations, and therefore capable of being represented by mathematical formulae. Of this truth, it is there said, Aristotle does not betray the slightest consciousness. The Timaeus of Plato contains a scheme of mathematical and physical doctrines concerning the universe, which make it far more analogous than any work of Aristotle to treatises which, in modern times, have borne the titles of Principia, System of the World, and the like. And fortunately, the work has recently been well and carefully studied, with attention not only to the language, but to the doctrines and their bearing upon our real knowledge. Stahlbaum has published an edition of the Dialogue and has compared the opinions of Plato with those of Aristotle on the like subjects. Professor Archer Butler of Dublin has devoted to it several of his striking and eloquent lectures, and these have been furnished with valuable annotations by Professor Thompson of Cambridge, and M. the Henry Martin, then professor at Rennes, published in 1841 2 volumes of Etudes sur la Timae de Platon, in 498, which the bearings of the work on science are very fully discussed. The dialogue treats not only concerning the numerical laws of harmonical sounds, of visual appearances, and of the motions of planets and stars, but also concerning heat as well as light, and concerning water, ice, gold, gems, iron, rust, and other natural objects, concerning odors, tastes, hearing, sight, light, colors, and the powers of sense in general, concerning the parts and organs of the body, as the bones, the marrow, the brain, the flesh, muscles, tendons, ligaments, nerves, the skin, the hair, the nails, the veins and arteries, respiration, generation, and in short, every obvious point of physiology. But the opinions delivered in the Timaeus upon these latter subjects have little to do with the progress of real knowledge. The doctrines, on the other hand, which depend upon geometrical and arithmetical relations, are portions or preludes of the sciences which, in the fullness of time, assumed a mathematical form for the expression of truth. Among these may be mentioned the arithmetical relations of harmonical sounds, to which I have referred in the history. These occur in various parts of Plato's writings. In the Timaeus, in which the numbers are most fully given, the meaning of the numbers is, at first sight, least obvious. The numbers are given as representing the proportion of the parts of the soul, Tim pp. 35-36, which does not immediately refer us to the relations of sounds. But in a subsequent part of the dialogue, 47d, we are told that music is a privilege of the hearing given on account of harmony, and that harmony has cycles corresponding to the movements of the soul, referring plainly to those already asserted. And the numbers which are thus given by Plato as elements of harmony are in a great measure the same as those which express the musical relations of the tones of the musical scale at this day in use, as M. Henry Martin shows, et. Sur la Timae, note Roman 23. The intervals C to D, C to F, C to G, C to C are expressed by the fractions 9, 8, 4, 3, 3, 2, 2/1 and are now called a tone, a fourth, a fifth, and octave. They were expressed by the same fractions among the Greeks and were called tone, diatessaron, diapent, diapason. The major and minor third and the major and minor sixth were however wanting, it is conceived, in the musical scale of Plato. The Timaeus contains also a kind of theory of vision by reflexion from a plane and in a concave mirror, although the theory is in this case less mathematical and less precise than that of Euclid referred to in chapter Roman 2 of this book. One of the most remarkable speculations in the Timaeus is that in 499, which the regular solids are assigned as the forms of the elements of which the universe is composed. This curious branch of mathematics, solid geometry, had been pursued with great zeal by Plato and his friends, and with remarkable success. The 5 regular solids, the tetrahedron or regular triangular pyramid, the cube, the octahedron, the dodecahedron, and the icosahedron, had been discovered. And the remarkable theorem, that of regular solids there can be just so many, these and no others, was known. And in the Timaeus it is asserted that the particles of the various elements have the forms of these solids. Fire has the pyramid, earth has the cube, water the octahedron, air the icosahedron, and the dodecahedron is the plan of the universe itself. It was natural that when Plato had learnt that other mathematical properties had a bearing upon the constitution of the universe, he should suppose that the singular property of space, which the existence of this limited and varied class of solids implied, should have some corresponding property in the universe, which exists in space. We find afterwards, in Kepler and others, a recurrence to this assumption. And we may say perhaps that crystallography shows us that there are properties of bodies, of the most intimate kind, which involve such spatial relations as are exhibited in the regular solids. If the distinctions of crystalline system in bodies were hereafter to be found to depend upon the chemical elements which predominate in their composition, the admirers of Plato might point to his doctrine of the different form of the particles of the different elements of the universe as a remote prelude to such a discovery. But the mathematical doctrines concerning the parts and elements of the universe are put forwards by Plato, not so much as assertions concerning physical facts, of which the truth or falsehood is to be determined by a reference to nature herself. They are rather propounded as examples of a truth of a higher kind than any reference to observation can give or can test, and as revelations of principles such as must have prevailed in the mind of the Creator of the universe, or else as contemplations by which the mind of man is to be raised above the region of sense and brought nearer to the divine mind. In the Timaeus these doctrines appear rather in the former of the two lights, as an exposition of the necessary scheme of creation so far as its leading features are concerned. In the 7th book of the Polity, the same doctrines are regarded more as a mental discipline, as the necessary study of the true philosopher. But in both places these mathematical, 500, propositions are represented as realities more real than the phenomena, as a natural philosophy of a higher kind than the study of nature itself can teach. This is no doubt an erroneous assumption. Yet even in this there is a germ of truth, namely, that the mathematical laws which prevail in the universe involve mathematical truths which, being demonstrative, are of a higher and more cogent kind than mere experimental truths. Notions, such as these of Plato, respecting a truth at which science is to aim, which is of an exact and demonstrative kind, and is imperfectly manifested in the phenomena of nature, may help or may mislead inquirers. They may be the impulse and the occasion to great discoveries, or they may lead to the assertion of false and the loss of true doctrines. Plato considers the phenomena which nature offers to the senses as mere suggestions and rude sketches of the objects, which the philosophically mind is to contemplate. The heavenly bodies and all the splendors of the sky, though the most beautiful of visible objects, being only visible objects, are far inferior to the true objects of which they are the representatives. They are merely diagrams which may assist in the study of the higher truth, as we might study geometry, by the aid of diagrams constructed by some consummate artist. Even then, the true object about which we reason is the conception which we have in the mind. We have, I conceive, an instance of the error as well as of the truth, to which such views may lead, in the speculations of Plato concerning harmony, contained in that part of his writings, the 7th book of the Republic, in which these views are especially urged. He there, by way of illustrating the superiority of philosophical truth over such exactness, as the senses can attest, speaks slightingly of those who take immense pains in measuring musical notes and intervals by the ear, as the astronomers measure the heavenly motions by the eye. They screw their pegs and pinch their strings, and dispute whether two notes are the same or not. Now, in truth, the ear is the final and supreme judge whether two notes are the same or not. But there is a case in which notes which are nominally the same are different really and to the ear, and it is probably to disputes on this subject, which we know did prevail among the Greek musicians, that Plato here refers. We may ascend from a note A1 to a note C3 by 2 octaves and a third. We may also ascend from the same note A1 to C3 by fifths 4 times repeated. But the two notes C3, thus arrived at, are not the same. They differ by a small interval, which the Greeks called a 501 comma, of which the notes are in the ratio of 80 to 81. That the ear really detects this defect of the musical coincidence of the two notes under the proper conditions is a proof of the coincidence of our musical perceptions with the mathematical relations of the notes, and is therefore an experimental confirmation of the mathematical principles of harmony. But it seems to be represented by Plato that to look out for such confirmation of mathematical principles implies a disposition to lean on the senses, which he regards as very unphilosophical. Hero of Alexandria. The other branches of mathematical science which I have spoken of in the history as cultivated by the Greeks, namely mechanics and hydrostatics, are not treated expressly by Plato, though we know from Aristotle and others that some of the propositions of those sciences were known about his time. Machines moved not only by weights and springs, but by water and air, were constructed at an early period. C. Ctesibius, who lived probably about BC 250 under the Ptolemies, is said to have invented a clepsydra or water clock and an hydraulic organ, and to have been the first to discover the elastic power of air and to apply it as a moving power. Of his pupil Hero, the name is to this day familiar, through the little pneumatic instrument called Hero's fountain. He also described pumps and hydraulic machines of various kinds, and an instrument which has been spoken of by some modern writers as a steam engine, but which was merely a toy made to whirl round by the steam emitted from holes in its arms. Concerning mechanism, besides descriptions of automatons, Hero composed 2 works, the one entitled Mechanics or Mechanical Introductions, the other Barulcos, the weightlifter. In these works, the elementary contrivances by which weights may be lifted or drawn were spoken of as the 5 mechanical powers, the same enumeration of such machines as prevails to this day, namely, the lever, the wheel and axle, the pulley, the wedge, and the screw. In his Mechanics, it appears that Hero reduced all these machines to one single machine, namely to the lever. In the Barulcos, Hero proposed and solved the problem which it was the glory of Archimedes to have solved: to move any object, however large, by any power, however small. This, as may easily be conceived by anyone acquainted with the elements of mechanics, is done by means of a combination of the mechanical powers, and especially by means of a train of toothed wheels and axles. 502. The remaining writings of Hero of Alexandria have been the subject of a special, careful, and learned examination by M.Th. H. Martin, Paris, 1854, in which the works of this writer, Hero the Ancient, as he is sometimes called, are distinguished from those of another writer of the same name of later date. Hero of Alexandria wrote also, as it appears, a treatise on pneumatics, in which he described machines, either useful or amusing, moved by the force of air and vapor. He also wrote a work called Catoptrics, which contained proofs of properties of the rays of reflected light, and a treatise on the dioptra, which subject, however, must be carefully distinguished from the subject entitled dioptrics by the moderns. This latter subject treats of the properties of refracted light, a subject on which the ancients had little exact knowledge till a later period, as I have shown in the history. The dioptra, as understood by Hero, was an instrument for taking angles so as to measure the position and hence to determine the distance of inaccessible objects, as is done by the theodolite in our times. M. Martin is of opinion that Hero of Alexandria lived at a later period than is generally supposed, namely, after BC 81. 503, Book 3. The Greek Astronomy. Introduction. The mathematical opinions of Plato respecting the philosophy of nature, and especially respecting what we commonly call the heavenly bodies, the sun, moon, and planets, were founded upon the view which I have already described, namely, that it is the business of philosophy to aim at a truth higher than observation can teach, and to solve problems which the phenomena of the universe only suggest. And though the students of nature in more recent times have learnt that this is too presumptuous a notion of human knowledge, Yet the very boldness and hopefulness which it involved impelled men in the pursuit of truth, with more vigor than a more timorous temper could have done. And the belief that there must be, in nature, mathematical laws more exact than experience could discover, stimulated men often to discover true laws, though often also to invent false laws. Plato's writings, supplying examples of both these processes, belong to the prelude of true astronomy as well as to the errors of false philosophy. We may find specimens of both kinds in those parts of his dialogues to which we have referred in the preceding book of our history. To Plato's merits in preparing the way for the theory of epicycles, I have already referred in Chapter 2 of this book. I conceive that he had a great share in that which is an important step in every discovery, the proposing distinctly the problem to be solved, which was, in this case, as he states it, to account for the apparent movements of the planets by a combination of two circular motions for each, the motion of identity and the motion of difference. Tim. 39a in the 10th book of the Republic, quoted in our text, the spindle which destiny or necessity holds between her knees, and on which are rings, by means of which the planets revolve round it as an axis, is a step towards the conception of the problem, as the construction of a machine. It will not be thought surprising that Plato expected that 504 astronomy, when further advanced, would be able to render an account of many things for which she has not accounted even to this day. Thus, in the passage in the 7th book of the Republic, he says that the philosopher requires a reason for the proportion of the day to the month, and the month to the year, deeper and more substantial than mere observation can give. Yet astronomy has not yet shown us any reason why the proportion of the times of the Earth's rotation on its axis, the moon's revolution round the Earth, and the Earth's revolution round the sun, might not have been made by the Creator quite different from what they are. But in thus asking mathematical astronomy for reasons which she cannot give, Plato was only doing what a great astronomical discoverer, Kepler, did at a later period. One of the questions which Kepler especially wished to have answered was, why there are 5 planets, and why at such particular distances from the sun? And it is still more curious that he thought he had found the reason of these things in the relations of those 5 regular solids which, as we have seen, Plato was desirous of introducing into the philosophy of the universe. We have Kepler's account of this, his imaginary discovery in the Mysterium Cosmographicum, published in 1596, as stated in our History, Book 5, Chapter Roman 4, Sect. 2. Kepler regards the law which thus determines the number and magnitude of the planetary orbits, by means of the 5 regular solids, as a discovery no less remarkable and certain than the 3 laws which give his name its imperishable place in the history of astronomy. We are not on this account to think that there is no steady criterion of the difference between imaginary and real discoveries in science. As discovery becomes possible by the liberty of guessing, it becomes real by allowing observation constantly and authoritatively to determine the value of guesses. Kepler added to Plato's boldness of fancy his own patient and candid habit of testing his fancies by a rigorous and laborious comparison with the phenomena, and thus his discoveries led to those of Newton. 505. Chapter 1. Earliest stages of astronomy. The globular form of the Earth. There are parts of Plato's writings which have been adduced as bearing upon the subsequent progress of science, and especially upon the globular form of the Earth and the other views which led to the discovery of America. In the Timaeus, we read of a great continent lying in the ocean west of the Pillars of Hercules, which Plato calls Atlantis. He makes the personage in his dialogue who speaks of this put it forward as an Egyptian tradition. M. H. Martin, who has discussed what has been written respecting the Atlantis of Plato, and has given therein a dissertation rich in erudition and of the most lively interest, conceives that Plato's notions on this subject arose from his combining his conviction of the spherical form of the Earth with interpretations of Homer, and perhaps with traditions which were current in Egypt, Etudes sur la Timae, note Roman 13. Section Roman 9. He does not consider that the belief in Plato's Atlantis had any share in the discoveries of Columbus. It may perhaps surprise modern readers who have a difficulty in getting rid of the persuasion that there is a natural direction upwards and a natural direction downwards, to learn that both Plato and Aristotle, and of course other philosophers also, had completely overcome this difficulty. They were quite ready to allow and to conceive that down meant nothing but towards some center, and up the opposite direction. Aristotle has, besides, an ingenious notion that while heavy bodies, as earth and water, tend to the center, and light bodies, as fire, tend from the center, the fifth element, of which the heavenly bodies are composed, tends to move round the center. Plato explains this in the most decided manner in the Timaeus, 62c. It is quite erroneous to suppose that there are two opposite regions in the universe, one above and the other below, and that heavy things naturally tend to the latter place. The heavens are spherical, and everything tends to the center, and thus above and below have no real meaning. If there be a solid globe in the middle, 506, and if a person walk round it, he will become the antipodes to himself, and the direction which is up at one time will be down at another. The notion of antipodes, the inhabitants of the part of the globe of the earth opposite to ourselves, was very familiar. Thus, in Cicero's Academic Questions, Roman 2:39, one of the speakers says, Etiam decitus esse e regini nobis, e contraria parteri, qui adversus vestigiae stant contra nostra vestigia, quos antipodes vocatis. See also Tusk. Disp. I-28 and V-24. The heliocentric system, among the ancients. As the more clear-sighted of the ancients had overcome the natural prejudice of believing that there is an absolute up and down, so had they also overcome the natural prejudice of believing that the earth is at rest. Cicero says, Acad. Quest. Roman 2:39, Histus of Syracuse, as Theophrastus tells us, thinks that the heavens, the sun, the moon, the stars, do not move, and that nothing does move but the earth. The earth revolves about her axis with immense velocity, and thus the same effect is produced as if the earth were at rest and the heavens moved. And this, he says, Plato teaches in the Timaeus, though somewhat obscurely. Of course, the assertion that the moon and planets do not move was meant of the diurnal motion only. The passage referred to in the Timaeus seems to be this, 40c, as to the earth, which is our nurse, and which clings to the axis which stretches through the universe, God made her the producer and preserver of day and night. The word epsilon letter 1f31 lambda lambda omicron mu epsilon nu eta nu, which I have translated clings to, some translate revolves, and an extensive controversy has prevailed, both in ancient and modern times, beginning with Aristotle, whether Plato did or did not believe in the rotation of the earth on her axis. See M. Cousin's note on the Timaeus, and M. Henry Martin's dissertation, note Roman 37, in his Etudes sur le Timaeus. The result of this discussion seems to be that, in the Timaeus, the earth is supposed to be at rest. It is, however, related by Plutarch, Platonic Questions, Roman 8:1, that Plato in his old age repented of having given to the earth the place in the center of the universe which did not belong to it. In describing the prelude to the Epic of Copernicus, Book 5, Chapter I have spoken of Philolaus, one of the followers of Pythagoras, who lived at the time of Socrates, as having held the doctrine that the earth revolves about the sun. This has been a current, 507 opinion, so current, indeed, that the Abbé Bouilhaud, or Bullialdus, as we more commonly call him, gave the title of Philolaus to the defense of Copernicus, which he published in 1639, and Chiaramonti, an Aristotelian, published his answer under the title of Antiphilolaus. In 1645, Bullialdus published his Astronomia Philolaica, which was another exposition of the heliocentric doctrine. Yet notwithstanding this general belief, it appears to be tolerably certain that Philolaus did not hold the doctrine of the earth's motion round the sun. M. H. Martin, Etudes sur le Timaeus, 1841, note Roman 37. Sect. I and Boek de Vera Indole Astronomiae Philolaici, 1810. In the system of Philolaus, the earth revolved about the central fire, but this central fire was not the sun. The sun, along with the moon and planets, revolved in circles external to the earth. The earth had the antechthon or counter-earth between it and the center, and revolving round this center in one day, the antechthon, being always between it and the center, was, during a portion of the revolution, interposed between the earth and the sun, and thus made night, while the sun, by his proper motion, produced the changes of the year. When men were willing to suppose the earth to be in motion, in order to account for the recurrence of day and night, it is curious that they did not see that the revolution of a spherical earth about an axis passing through its center was a scheme both simple and quite satisfactory. Yet the illumination of a globular Earth by a distant sun, and the circumstances and phenomena thence resulting, appear to have been conceived in a very confused manner by many persons. Thus Tacitus, Agric, Roman 12. After stating that he has heard that in the northern part of the island of Britain, the night disappears in the height of summer, says, as his account of this phenomenon, that the extreme parts of the earth are low and level, and do not throw their shadow upwards, so that the shade of night falls below the sky and the stars. But, as a little consideration will show, it is the globular form of the earth, and not the level character of the country, which produces this effect. It is not in any degree probable that Pythagoras taught that the earth revolves round the sun, or that it rotates on its own axis. Nor did Plato hold either of these motions of the earth. They got so far as to believe in the spherical form of the earth, and this was apparently such an effort that the human mind made a pause before going any further. It required, says M. H. Martin, a great struggle for 508 men to free themselves from the prejudices of the senses, and to interpret their testimony in such a manner as to conceive the sphericity of the earth. It is natural that they should have stopped at this point, before putting the earth in motion in space. Some of the expressions which have been understood as describing a system in which the sun is the center of motion do really imply merely the sun is the middle term of the series of heavenly bodies which revolve round the earth, the series being Moon, Mercury, Venus, Sun, Mars, Jupiter, Saturn. This is the case, for instance, in a passage of Cicero's Vision of Scipio, which has been supposed to imply, as I have stated in the history, that Mercury and Venus revolve about the sun. But though the doctrine of the diurnal rotation and annual revolution of the earth is not the doctrine of Pythagoras, or of Philolaus, or of Plato, it was nevertheless held by some of the philosophers of antiquity. The testimony of Archimedes that this doctrine was held by his contemporary Aristarchus of Samos is unquestionable, and there is no reason to doubt Plutarch's assertion that Seleucus further enforced it. It is curious that Copernicus appears not to have known anything of the opinions of Aristarchus and Seleucus, which were really anticipations of his doctrine, and to have derived his notion from passages which, as I have been showing, contain no such doctrine. He says, in his dedication to Pope Paul Roman III, I found in Cicero that Nicetas held that the earth was in motion, and in Plutarch I found that some others had been of that opinion, and his words I will transcribe that anyone may read them. Philosophers in general hold that the earth is at rest. But Philolaus, the Pythagorean, teaches that it moves round the central fire in an oblique circle, in the same direction as the sun and the moon. Heraclides of Pontus and Ecphantus, the Pythagorean, give the earth a motion, but not a motion of translation. They make it revolve like a wheel about its own center from west to east. This last opinion was a correct assertion of the diurnal motion. The eclipse of Thales. The eclipse of Thales is so remarkable a point in the history of astronomy, and has been the subject of so much discussion among astronomers, that it ought to be more especially noticed. The original 509 record is in the first book of Herodotus's History, chapter Alexiv. He says that there was a war between the Lydians and the Medes, and after various turns of fortune, in the 6th year a conflict took place, and on the battle being joined, it happened that the day suddenly became night. And this change Thales of Miletus had predicted to them, definitely naming this year, in which the event really took place. The Lydians and the Medes, when they saw day turned into night, ceased from fighting, and both sides were desirous of peace. Probably this prediction was founded upon the Chaldean period of 18 years, of which I have spoken in section 11. It is probable, as I have already said, that this period was discovered by noticing the recurrence of eclipses. It is to be observed that Thales predicted only the year of the eclipse, not the day or the month. In fact, the exact prediction of the circumstances of an eclipse of the sun is a very difficult problem. Much more difficult, it may be remarked, than the prediction of the circumstance of an eclipse of the moon. Now that the theory of the moon is brought so far towards completeness, astronomers are able to calculate backwards the eclipses of the sun which have taken place in former times, and the question has been much discussed in what year this eclipse of Thales really occurred. The memoir of Mr. Airy, the Astronomer Royal, on this subject, in the Phil. Trans for 1853, gives an account of the modern examinations of this subject. Mr. Airy starts from the assumption that the eclipse must have been one decidedly total, the difference between such a one and an eclipse only nearly total being very marked. A total eclipse alone was likely to produce so strong an effect on the minds of the combatants. Mr. Airy concludes from his calculations that the eclipse predicted by Thales took place BC 585. Ancient eclipses of the moon and sun, if they can be identified, are of great value for modern astronomy. For in the long interval of between 2,000 and 3,000 years which separates them from our time, those of the inequalities, that is, accelerations or retardations of the moon's motion, which go on increasing constantly, accumulate to a large amount. So that the actual time and circumstances of the eclipse give astronomers the means of determining what the rate of these accelerations or retardations has been. Accordingly, Mr. Airy has discussed, as even more important than the eclipse of Thales, an eclipse which Diodorus relates to have happened during an expedition of 510 Agathocles, the ruler of Sicily, and which is hence known as the eclipse of Agathocles. He determines it to have occurred BC 310. M. H. Martin, in Note Roman 37, to his Etudes sur la Timée, discusses among other astronomical matters the eclipse of Thales. He does not appear to render a very cordial belief to the historical fact of Thales having delivered the prediction before the event. He says that even if Thales did make such a prediction of an eclipse of the sun, as he might do, by means of the Chaldean period of 18 years or 223 lunations, he would have to take the chance of its being visible in Greece, about which he could only guess. That no author asserts that Thales, or his successors Anaximander and Anaxagoras, ever tried their luck in the same way again. That, en revanche, we are told that Anaximander predicted an earthquake, and Anaxagoras the fall of Aerolites, which are plainly fabulous stories, though as well attested as the eclipse of Thales. He adds that according to Aristotle, Thales and Anaximenes were so far from having sound notions of cosmography that they did not even believe in the roundness of the earth. 511, Book 4. Physical Science in the Middle Ages. General Remarks. In the 12th book of the Philosophy, in which I have given a review of opinions on the nature of knowledge and the method of seeking it, I have given some account of several of the most important persons belonging to the ages now under consideration. I have there volume Roman 2, B. Roman 12, p. 146, spoken of the manner in which remarks made by Aristotle came to be accepted as fundamental maxims in the schools of the Middle Ages, and of the manner in which they were discussed by the greatest of the schoolmen, as Thomas Aquinas, Albertus Magnus, and the like. I have spoken also, p. 149, of a certain kind of recognition of the derivation of our knowledge from experience, as shown in Richard of St. Victor in the 12th century. I have considered p. 152, the plea of the admirers of those ages, that religious authority was not claimed for physical science. I have noticed that the rise of experimental philosophy exhibited two features, chapter Roman 7, p. 155, the insurrection against authority and the appeal to experience, and as exemplifying these features, I have spoken of Raymond Lully and of Roger Bacon. I have further noticed the opposition to the prevailing Aristotelian dogmatism manifested, chapter Roman 8, by Nicholas of Cuss, Marsilius Ficinus, Francis Patricius, Picus of Murrangula, Cornelius Agrippa, Theophrastus Paracelsus, Robert Flood. I have gone on to notice the theoretical reformers of science, chapter Roman 9. Bernardinus Telesius, Thomas Campanella, Andreas Caesalpinus, Peter Ramus, and the Protestant reformers as Melanchthon. After these come the practical reformers of science, who have their place in the subsequent history of inductive philosophy, Leonardo da Vinci, and the heralds of the dawning light of real science, whom Francis Bacon welcomes, as heralds are accosted in Homer. Chi alpha iotero epsilon tau epsilon, capi rho epsilon cap epsilon sigma, delta iota letter 1 F78, sigma letter 1 F04 gamma gamma epsilon lambda omicron iota, letter 1 F20 delta letter 1 F72, kappa alpha letter 1 F76, letter 1 F00, nu delta rho letter 1 FF6 nu hail, heralds, messengers of gods and men. 512. I have, in the part of the philosophy referred to, discuss the merits and defects of Francis Bacon's method, and I shall have occasion, in the next book, to speak of his mode of dealing with the positive science of his time. There is room for much more reflection on these subjects, but the references now made may suffice at present. Chapter 5. Progress in the Middle Ages. Thomas Aquinas. Aquinas wrote, besides the summa mentioned in the text, a commentary on the physics of Aristotle, Commentaria in Aristoteles Libros Physicorum, Venice, 1492. This work is of course of no scientific value, and the commentary consists of empty permutations of abstract terms, similar to those which constitute the main substance of the text in Aristotle's physical speculations. There is, however, an attempt to give a more technical form to the propositions and their demonstrations. As specimens of these, I may mention that in Book 6. C2, we have a demonstration that when bodies move, the time and the magnitude, that is, the space described, are divided similarly, with many like propositions, and in Book 8, we have such propositions as this, C10, demonstration that a finite mover, movens, cannot move anything in an infinite time. This is illustrated by a diagram in which two hands are represented as engaged in moving a whole sphere, and one hand in moving a hemisphere. This mode of representing force, in diagrams illustrative of mechanical reasonings, by human hands pushing, pulling, and the like, is still employed in elementary books. Probably this is the first example of such a mode of representation. Roger Bacon. This writer, a contemporary of Thomas Aquinas, exhibits to us a kind of knowledge, speculation, and opinion, so different from that of any known person near his time, that he deserves a special notice here. 513, and I shall transfer to this place the account which I have given of him in the Philosophy. I do this the more willingly because I regard the existence of such a work as the opus majus at that period, as a problem which has never yet been solved. Also, I may add that the scheme of the contents of this work which I have given deserves, as I conceive, more notice than it has yet received. Roger Bacon was born in 1214 near Ilchester, in Somersetshire, of an old family. In his youth he was a student at Oxford and made extraordinary progress in all branches of learning. He then went to the University of Paris, as was at that time the custom of learned Englishmen, and there received the degree of Doctor of Theology. At the persuasion of Robert Grosseteste, Bishop of Lincoln, he entered the Brotherhood of Franciscans in Oxford and gave himself up to study with extraordinary fervor. He was termed by his brother monks Doctor Mirabilis. We know from his own works, as well as from the traditions concerning him, that he possessed an intimate acquaintance with all the science of his time which could be acquired from books, and that he had made many remarkable advances by means of his own experimental labors. He was acquainted with Arabic, as well as with the other languages common in his time. In the title of his works, we find the whole range of science and philosophy, mathematics and mechanics, optics, astronomy, geography, chronology, chemistry, magic, music, medicine, grammar, logics, metaphysics, ethics, and theology. And judging from those which are published, these works are full of sound and exact knowledge. He is, with good reason, supposed to have discovered, or to have had some knowledge of, several of the most remarkable inventions which were made generally known soon afterwards, as gunpowder, lenses, burning specula, telescopes, clocks, the correction of the calendar, and the explanation of the rainbow. Thus possessing, in the acquirements and habits of his own mind, abundant examples of the nature of knowledge and of the process of invention, Roger Bacon felt also a deep interest in the growth and progress of science, a spirit of inquiry respecting the causes which produced or prevented its advance, and a fervent hope and trust in its future destinies. And these feelings impelled him to speculate worthily and wisely respecting a reform of the method of philosophizing. The manuscripts of his works have existed for nearly 600 years in many of the libraries of Europe, and especially in those of England. And for a long period, the very imperfect portions of them, which were 514 generally known, left the character and attainments of the author shrouded in a kind of mysterious obscurity. About a century ago, however, his opus majus was published by Dr. S. Jebb, principally from a manuscript in the Library of Trinity College, Dublin, and this contained most or all of the separate works which were previously known to the public, along with others still more peculiar and characteristic. We are thus able to judge of Roger Bacon's knowledge and of his views, and they are in every way well worthy our attention. Note 5\a. Fratris Rogeri Bacon ordinis minorum opus magis ad clementem quordam, pontificem Romanum, ex mis codis Dubliniensi, cum aliis quibustum collado nunc primum edidit S. Jeb, M.D. Lindini, 1733. The Opus Magis is addressed to Pope Clement IV, whom Bacon had known when he was legate in England as Cardinal Bishop of Sabina, and who admired the talents of the monk and pitied him for the persecutions to which he was exposed. On his elevation to the papal chair, this account of Bacon's labors and views was sent, at the earnest request of the pontiff. Besides the Opus Magis, he wrote two others, the Opus Minus and Opus Tertium, which were also sent to the Pope, as the author says, on account of the danger of roads and the possible loss of the work. These works still exist unpublished in the Catanian and other libraries. The Opus Magis is a work equally wonderful with regard to its general scheme, and to the special treatises with which the outlines of the plan are filled up. The professed object of the work is to urge the necessity of a reform in the mode of philosophizing, to set forth the reasons why knowledge had not made a greater progress, to draw back attention to the sources of knowledge which had been unwisely neglected, to discover other sources which were yet almost untouched, and to animate men in the undertaking by a prospect of the vast advantages which it offered. In the development of this plan, all the leading portions of science are expounded in the most complete shape which they had at that time assumed, and improvements of a very wide and striking kind are proposed in some of the principal of these departments. Even if the work had had no leading purpose, it would have been highly valuable as a treasure of the most solid knowledge and soundest speculations of the time. Even if it had contained no such details, it would have been a work most remarkable for its general views and scope. It may be considered as, at the same time, the encyclopedia and the novum organon of the 13th century. 515. Since this work is thus so important in the history of inductive philosophy, I shall give, in a note, a view of its divisions and contents. But I must now endeavor to point out more especially the way in which the various principles, which the reform of scientific method involved, are here brought into view. Note 7\a, Contents of Roger Bacon's Opus Magis, Part 1. On the four causes of human ignorance, authority, custom, popular opinion, and the pride of supposed knowledge, Part 2. On the source of perfect wisdom in the sacred scripture, Part 3. On the usefulness of grammar, Part 4. On the usefulness of mathematics. 1. The necessity of mathematics in human things, published separately as the Specula Mathematica. 2. The necessity of mathematics in divine things, 1 degrees. This study has occupied holy men, 2 degrees. Geography, 3 degrees. Chronology, 4 degrees. Cycles, the golden number and c, 5 degrees. Natural phenomena as the rainbow, 6 degrees. Arithmetic degrees. Music, 3. The necessity of mathematics in ecclesiastical things, 1 degrees. The certification of faith, 2 degrees. The correction of the calendar, 4. The necessity of mathematics in the state, 1 degrees. Of climates, 2 degrees. Hydrography, 3 degrees. Geography, 4 degrees. Astrology, Part 5. On perspective, published separately as Perspectiva. 1. The organs of vision. 2. Vision in straight lines. 3. Vision reflected and refracted. 4. Demultiplication Specirum, on the propagation of the impressions of light, heat, and c, Part 6, on experimental science. One of the first points to be noticed for this purpose is the resistance to authority, and at the stage of philosophical history with which we here have to do, this means resistance to the authority of Aristotle as adopted and interpreted by the doctors of the schools. Bacon's work is divided into 6 parts, and of these parts, the first is of the 4 universal causes of all human ignorance. The causes thus enumerated are the force of unworthy authority, traditionary habit, the imperfection of the undisciplined senses, and the disposition to conceal our ignorance and to make an ostentatious show of our knowledge. These influences involve every man, occupy every condition. They prevent our obtaining the most useful and large and fair doctrines of wisdom, the secrets of all sciences and arts. He then proceeds to argue from the testimony of philosophers themselves that the authority of antiquity, and especially of Aristotle, is not infallible. we find their books full of doubts, obscurities, and perplexities. They 516 scarce agree with each other in one empty question or one worthless sophism, or one operation of science, as one man agrees with another in the practical operations of medicine, surgery, and the like arts of secular men. Indeed, he adds, not only the philosophers, but the saints have fallen into errors which they have afterwards retracted. And this he instances in Augustine, Jerome, and others. He gives an admirable sketch of the progress of philosophy from the Ionic school to Aristotle, of whom he speaks with great applause. Yet, he adds, those who came after him corrected him in some things, and added many things to his works, and shall go on adding to the end of the world. Aristotle, he adds, is now called peculiarly the philosopher. Yet there was a time when his philosophy was silent and unregarded, either on account of the rarity of copies of his works, or their difficulty, or from envy. Till after the time of Mahomet, when Avicenna and Averroes, and others, recalled this philosophy into the full light of exposition. And although the Logic and some other works were translated by Boethius from the Greek, yet the philosophy of Aristotle first received a quick increase among the Latins at the time of Michael Scott, who, in the year of our Lord 1230, appeared, bringing with him portions of the books of Aristotle on natural philosophy and mathematics. And yet a small part only of the works of this author is translated, and a still smaller part is in the hands of common students. He adds further in the third part of the Opus Majus, which is a dissertation on language, that the translations which are current of these writings are very bad and imperfect. With these views, he is moved to express himself somewhat impatiently respecting these works. If I had, he says, power over the works of Aristotle, I would have them all burnt, for it is only a loss of time to study in them, and a course of error, and a multiplication of ignorance beyond expression. The common herd of students, he says, with their heads, have no principle by which they can be excited to any worthy employment, and hence they mope and make asses of themselves over their bad translations, and lose their time and trouble and money. 517. Note 14 \A, see Pref. To Jebb's edition. The passages there quoted, however, are not extracts from the Opus Majus, but apparently from the Opus Minus Mizkat. Tib. C5. Si habrum potestatum supra libros Aristoteles, ego facerum omnes cremeri, quia non est nisi temporis emissio studier inneles, et causa erroris, et multiplicatio ignorantiae ultra id quod velet explicari. Vulgus studentum, cum capitibus sues non habet, under exciter ad aliquid dignum. Et ideo lanct et assoninet circa male translata, et tempus et studium amitit in omnibus et expenses. The remedies which he recommends for these evils are, in the first place, the study of that only perfect wisdom which is to be found in the sacred Scripture. In the next place, the study of mathematics and the use of experiment. By the aid of these methods, Bacon anticipates the most splendid progress for human knowledge. He takes up the strain of hope and confidence, which we have noticed as so peculiar in the Roman writers, and quotes some of the passages of Seneca which we adduced in illustration of this, that the attempts in science were at first rude and imperfect, and were afterwards improved, that the day will come when what is still unknown shall be brought to light by the progress of time and the labors of a longer period, that one age does not suffice for inquiries so wide and various, that the people of future times shall know many things unknown to us, and that the time shall arrive when posterity will wonder that we overlooked what was so obvious. Bacon himself adds anticipations more peculiarly in the spirit of his own time. We have seen, he says at the end of the work, how Aristotle, by the ways which wisdom teaches, could give to Alexander the empire of the world. And this the Church ought to take into consideration against the infidels and rebels, that there may be a sparing of Christian blood, and especially on account of the troubles that shall come to pass in the days of Antichrist, which by the grace of God it would be easy to obviate, if prelates and princes would encourage study, and join in searching out the secrets of nature and art. It may not be improper to observe here that this belief in the appointed progress of knowledge is not combined with any overweening belief in the unbounded and independent power of the human intellect. On the contrary, one of the lessons which Bacon draws from the state and prospects of knowledge is the duty of faith and humility. To him, he says, who denies the truth of the faith because he is unable to understand it, I will propose in reply the course of nature, and as we have seen it in examples. And after giving some instances, he adds, these and the like ought to move men and to excite them to the reception of divine truths. For if in the vilest objects of creation, truths are found, before which the inward pride of man must bow, and believe though it cannot understand, how much more should man humble his mind before the glorious truths of God? He had before said, man is incapable of perfect wisdom in this life. It is hard for 518 him to ascend towards perfection, easy to glide downwards to falsehoods and vanities. Let him then not boast of his wisdom, or extol his knowledge. What he knows is little and worthless, in respect of that which he believes without knowing, and still less, in respect of that which he is ignorant of. He is mad who thinks highly of his wisdom, he most mad, who exhibits it as something to be wondered at. He adds, as another reason for humility, that he has proved by trial, he could teach in 1 year, to a poor boy, the marrow of all that the most diligent person could acquire in 40 years' laborious and expensive study. To proceed somewhat more in detail with regard to Roger Bacon's views of a reform in scientific inquiry, we may observe that by making mathematics and experiment the 2 great points of his recommendation, he directed his improvement to the 2 essential parts of all knowledge, ideas and facts, and thus took the course which the most enlightened philosophy would have suggested. He did not urge the prosecution of experiment to the comparative neglect of the existing mathematical sciences and conceptions, a fault which there is some ground for ascribing to his great namesake and successor Francis Bacon. Still less did he content himself with a mere protest against the authority of the schools and a vague demand for change, which was almost all that was done by those who put themselves forward as reformers in the intermediate time. Roger Bacon holds his way steadily between the 2 poles of human knowledge, which, as we have seen, it is far from easy to do. There are 2 modes of knowing, says he, by argument and by experiment. Argument concludes a question, but it does not make us feel certain or acquiesce in the contemplation of truth, except the truth be also found to be so by experience. It is not easy to express more decidedly the clearly seen union of exact conceptions with certain facts, which, as we have explained, constitutes real knowledge. Note 19/A, Op. Mag. p. 445, see also p. 448. Scientiae alii sciant sua principia invenir per experimenta, sed conclusions per argumenta facta ex principiis inventis. Si viro debint haber experientium conclusionum suarum particularum et completum, tunc oportet quod habent per adjutorium istius scientiae nobilis, experimentalis. One large division of the Opus Majus is on the usefulness of mathematics, which is shown by a copious enumeration of existing branches of knowledge, as chronology, geography, the calendar, and in a separate part optics. There is a chapter in which it is proved, 519 by reason, that all science requires mathematics, and the arguments which are used to establish this doctrine show a most just appreciation of the office of mathematics in science. They are such as follows: that other sciences use examples taken from mathematics as the most evident, that mathematical knowledge is, as it were, innate to us, on which point he refers to the well-known dialogue of Plato, as quoted by Cicero, that this science, being the easiest, offers the best introduction to the more difficult, that in mathematics, things as known to us are identical with things as known to nature, that we can here entirely avoid doubt and error, and obtain certainty and truth, that mathematics is prior to other sciences in nature, because it takes cognizance of quantity, which is apprehended by intuition, intuitu intellectus. Moreover, he adds, there have been found famous men, as Robert, Bishop of Lincoln, and Brother Adam Marshman, de Morisco, and many others who by the power of mathematics have been able to explain the causes of things, as may be seen in the writings of these men, for instance, concerning the rainbow and comets and the generation of heat and climates and the celestial bodies. But undoubtedly, the most remarkable portion of the Opus Majus is the 6th and last part, which is entitled De Scientia Experimentali. It is indeed an extraordinary circumstance to find a writer of the 13th century, not only recognizing experiment as one source of knowledge, but urging its claims as something far more important than men had yet been aware of, exemplifying its value by striking and just examples, and speaking of its authority with a dignity of diction, which sounds like a foremurmur of the Baconian sentences uttered nearly 400 years later. Yet this is the character of what we here find. Experimental science, the sole mistress of speculative sciences, has three great prerogatives among other parts of knowledge. First, she tests by experiment the noblest conclusions of all other sciences. Next, she discovers respecting the notions which other sciences deal with, magnificent truths to which these sciences of themselves can by no means attain. Her third dignity is that she by her own power and without respect of other sciences investigates the secrets of nature. 520. Note 22:a. Veritates magnificas in terminis aliorum scientiarum in quas per nullum viam passant illi scientiae, hic sola scientiarum domina speculativarum potus dare. Op. Mag. p. 465. The examples which Bacon gives of these prerogatives are very curious, exhibiting, among some error and credulity, sound and clear views. His leading example of the first prerogative is the rainbow, of which the cause, as given by Aristotle, is tested by reference to experiment with a skill which is, even to us now, truly admirable. The examples of the second prerogative are three. First, the art of making an artificial sphere which shall move with the heavens by natural influences, which Bacon trusts may be done, though astronomy herself cannot do it at tunc, he says. Thesaurem unius regis valerit hoc instrumentum. Secondly, the art of prolonging life, which experiment may teach, though medicine has no means of securing it except by regimen. Thirdly, the art of making gold finer than fine gold, which goes beyond the power of alchemy. The third prerogative of experimental science, arts independent of the received sciences, is exemplified in many curious examples, many of them whimsical traditions. Thus it is said that the character of a people may be altered by altering the air. Alexander, it seems, applied to Aristotle to know whether he should exterminate certain nations which he had discovered as being irreclaimably barbarous, to which the philosopher replied, "If you can alter their air, permit them to live, if not, put them to death." In this part, we find the suggestion that the fireworks made by children, of saltpeter, might lead to the invention of a formidable military weapon. Note 23:a. One of the ingredients of a preparation here mentioned is the flesh of a dragon, which, it appears, is used as food by the Ethiopians. The mode of preparing this food cannot fail to amuse the reader. Where there are good flying dragons, by the art which they possess, they draw them out of their dens and have bridles and saddles in readiness, and they ride upon them, and make them bound about in the air in a violent manner, that the hardness and toughness of the flesh may be reduced, as boars are hunted and bulls are baited before they are killed for eating. Op. Mag. p. 470. It could not be expected that Roger Bacon, at a time when experimental science hardly existed, could give any precepts for the discovery of truth by experiment. But nothing can be a better example of the method of such investigation than his inquiry concerning the cause of the rainbow. Neither Aristotle, nor Avicenna, nor Seneca, he says, have given us any clear knowledge of this matter, but experimental science can do so. Let the experimentator, consider the cases in which he finds the same colors, as the hexagonal crystals from Ireland and India. By looking into these, he will see colors like those of the rainbow. Many think that this arises from some 521 special virtue of these stones and their hexagonal figure. Let therefore the experimenter go on, and he will find the same in other transparent stones, in dark ones as well as in light-colored. He will find the same effect also in other forms than the hexagon, if they be furrowed in the surface, as the Irish crystals are. Let him consider, too, that he sees the same colors in the drops which are dashed from oars in the sunshine, and in the spray thrown by a mill-wheel, and in the dewdrops which lie on the grass in a meadow on a summer morning. And if a man takes water in his mouth and projects it on one side into a sunbeam, and if in an oil lamp hanging in the air, the rays fall in certain positions upon the surface of the oil, and in many other ways are colors produced. We have here a collection of instances, which are almost all examples of the same kind as the phenomenon under consideration. And by the help of a principle collected by induction from these facts, the colors of the rainbow were afterwards really explained. With regard to the form and other circumstances of the bow, he is still more precise. He bids us measure the height of the bow and of the sun, to show that the center of the bow is exactly opposite to the sun. He explains the circular form of the bow its being independent of the form of the cloud. It's moving when we move. It's flying when we follow by its consisting of the reflections from a vast number of minute drops. He does not, indeed, trace the course of the rays through the drop, or account for the precise magnitude which the bow assumes, but he approaches to the verge of this part of the explanation, and must be considered as having given a most happy example of experimental inquiry into nature, at a time when such examples were exceedingly scanty. In this respect, he was more fortunate than Francis Bacon, as we shall hereafter see. We know but little of the biography of Roger Bacon, but we have every reason to believe that his influence upon his age was not great. He was suspected of magic, and is said to have been put into close confinement in consequence of this charge. In his work, he speaks of astrology as a science well worth cultivating. But, says he, theologians and decretists, not being learned in such matters, and seeing that evil as well as good may be done, neglect and abhor such things, and reckon them among magic arts. We have already seen that at the very time when Bacon was thus raising his voice against the habit of blindly following authority, and seeking for all science in Aristotle, Thomas Aquinas was employed in fashioning Aristotle's tenets into that fixed form in which they became the great impediment to the 522 progress of knowledge. It would seem, indeed, that something of a struggle between the progressive and stationary powers of the human mind was going on at this time. Bacon himself says, "Never was there so great an appearance of wisdom, nor so much exercise of study in so many faculties, in so many regions, as for this last 40 years. Doctors are dispersed everywhere, in every castle, in every burg, and especially by the students of two orders." He means the Franciscans and Dominicans, who were almost the only religious orders that distinguished themselves by an application to study, which has not happened except for about 40 years. And yet there was never so much ignorance, so much error. And in the part of his work which refers to mathematics, he says of that study that it is the door and the key of the sciences, and that the neglect of it for 30 or 40 years has entirely ruined the studies of the Latins. According to these statements, some change, disastrous to the fortunes of science, must have taken place about 1230, soon after the foundation of the Dominican and Franciscan orders. Nor can we doubt that the adoption of the Aristotelian philosophy by these two orders, in the form in which the angelical doctor had systematized it, was one of the events which most tended to defer, for 3 centuries, the reform which Roger Bacon urged as a matter of crying necessity in his own time. It is worthy of remark that in the Opus Majus of Roger Bacon, as afterwards in the Novum Organon of Francis Bacon, we have certain features of experimental research pointed out conspicuously as prerogativi. Although in the former, this term is employed to designate the superiority of experimental science in general to the science of the schools. In the latter work, the term is applied to certain classes of experiments as superior to others. 523, Book 5. Formal Astronomy. Chapter 1. Prelude to Copernicus. Nicholas of Cuss. I will quote the passage in the writings of this author, which bears upon the subject in question. I translate it from the edition of his book De Docta Ignorantia, from his works published at Basel in 1565. He praises learned ignorance that is, acknowledged ignorance as the source of knowledge. His ground for asserting the motions of the earth is that there is no such thing as perfect rest, or an exact center, or a perfect circle, nor perfect uniformity of motion. Nec vera circulus dabilis est, quae nicium virier duri possit, nec unquam uno tempor sicut alio equaliter precis, aut moveter, aut circulum veri similim, equalum describit, etiam nobis hoc non apparit, et ubicum quis furit, si in centro esse credit. Lib I cap. Xi. p. 39. He adds, the ancients did not attain to this knowledge because they were wanting in learned ignorance. Now it is manifest to us that the earth is truly in motion, although this do not appear to us, since we do not apprehend motion except by comparison with something fixed. For if anyone were in a boat in the middle of a river, ignorant that the water was flowing, and not seeing the banks, how could he apprehend that the boat was moving? And thus, since everyone, whether he be in the earth, or in the sun, or in any other star, thinks that he is in an immovable center, and that everything else is moving, he would assign different poles for himself, others as being in the sun, others in the earth, and others in the moon, and so of the rest. Whence the machine of the world is as if it had its center everywhere and its circumference nowhere. This train of thought, 524, might be a preparation for the reception of the Copernican system, but it is very different from the doctrine that the sun is the center of the planetary motions. Chapter 2. The Copernican Theory. The moon's rotation. I have said, in page 264, that a confusion of mind produced by the double reference of motion to absolute space and to a center of revolution often leads persons to dispute whether the moon, while she revolves about the earth, always turning to it the same face, revolves about her axis or not. This dispute has been revived very lately, and has been conducted in a manner which shows that popular readers and writers have made little progress in the clearness of their notions during the last 2 or 3 centuries, and that they have accepted the Newtonian doctrines in words with a very dim apprehension of their real import. If the moon were carried round the earth by a rigid arm revolving about the earth as a center, being rigidly fastened to this arm, as a mimic moon might be, in a machine constructed to represent her motions, this contrivance, while it made her revolve round the earth, would make her also turn the same face to the earth. And if we were to make such a machine the standard example of rotation, the moon might be said not to rotate on her axis. But we are speedily led to endless confusion by taking this case as the standard of rotation. For the selection of the center of rotation in a system which includes several bodies is arbitrary. The moon turns all her faces successively to the sun, and therefore with regard to the sun, she does rotate on her axis, and yet she revolves round the sun as truly as she revolves round the earth. And the only really simple and consistent mode of speaking of rotation is to refer the motion not to any relative center, but to absolute space. This is the argument merely on the ground of simplicity and consistency, but we find physical reasons, as well as mathematical, for referring the motion to absolute space. If a cup of water be carried round a center so as to describe a circle, a straw floating on the surface, 525 of the water, if it point to the center of the circle at first, does not continue to do so, but remains parallel to itself during the whole revolution. Now there is no cause to make the water, and therefore the straw, rotate on its axis, and therefore it is not a clear or convenient way of speaking to say that the water in this case does revolve on its axis. But if the water in this case do not revolve on its axis, a body in the case of the moon does revolve on its axis. The difficulty, as I have said in the text, is of the same nature as that which the Copernicans at first found in the parallel motion of the Earth's axis. In order to make the axis of the Earth's rotation remain parallel to itself while the Earth revolves about the sun, in a mechanical representation, some machinery is needed in addition to the machinery which produces the revolution round the center, the sun. But the simplest way of regarding the parallel motion is to conceive that the axis has no motion except that which carries it round the central sun. And it was seen, when the science of mechanics was established, that no force was needed in nature to produce this parallelism of the Earth's axis. It was therefore the only scientific course to conceive this parallelism as not being a rotation. And in like manner, we are to conceive the parallelism of a revolving body as not being a rotation. M. Foucault's proofs of the Earth's motion. It was hardly to be expected that we should discover, in our own day, a new physical proof of the Earth's motion. Yet so it has been. The experiments of M. Foucault have enabled us to see the rotation of the Earth on its axis, as taking place, we may say, before our eyes. These experiments are, in fact, a result of what has been said in speaking of the moon's rotation, namely, that the mechanical causes of motion operate with reference to absolute, not relative space, so that where there is no cause operating to change a motion, it will retain its direction in absolute space, and may on that account seem to change if regarded relatively in a limited space. In M. Foucault's first experiment, the motion employed was that of a pendulum. If a pendulum oscillate quite freely, there is no cause acting to change the vertical plane of oscillation absolutely, for the forces which produce the oscillation are in the vertical plane. But if the vertical plane remain the same absolutely, at a spot on the surface of the revolving Earth, it will change relatively to the spectator. He will see the pendulum oscillate in a vertical plane, which gradually, 526, turns away from its first position. Now this is what really happens, and thus the revolution of the Earth in absolute space is experimentally proved. In subsequent experiments, M. Foucault has used the rotation of a body to prove the same thing. For when a body rotates freely, acted upon by no power, there is nothing to change the position of the axis of rotation in absolute space. But if the position of the axis remain the same in absolute space, it will, in virtue of its relative motion, change as seen by a spectator at any spot on the rotating Earth. By taking a heavy disk or globe and making it rotate on its axis rapidly, the force of absolute permanence, as compared with the inevitable casual disturbances arising from the machinery which supports the revolving disk, becomes considerable, and hence the relative motion can, in this way also, be made visible. Mr. De Morgan has said, comp. to Britt. 1836, p. 18, that astronomy does not supply any argument for the Earth's motion which is absolutely and demonstrably conclusive till we come to the aberration of light. But we may now venture to say that the experiments of M. Foucault prove the diurnal motion of the Earth in the most conclusive manner, by palpable and broad effects, if we accept the doctrines of the science of mechanics, while aberration proves the annual motion, if we suppose that we can observe the places of the fixed stars to the accuracy of a few seconds. And if we accept, in addition to the doctrines of mechanics, the doctrine of the motion of light with a certain great velocity. Chapter 3. Sequel to Copernicus. English Copernicans. Professor De Morgan has made numerous and interesting contributions to the history of the progress and reception of the Copernican system. These are given mainly in the companion to the British Almanac, especially in his papers entitled Old Arguments Against the Motion of the Earth, 1836, English Mathematical and Astronomical Writers, 1837, On the Difficulty of Correct, 527, Description of Books, 1853, The Progress of the Doctrine of the Earth's Motion Between the Times of Copernicus and Galileo, 1855. In these papers, he insists very rightly upon the distinction between the mathematical and the physical aspect of the doctrines of Copernicus, a distinction corresponding very nearly with the distinction which we have drawn between formal and physical astronomy, and in accordance with which we have given the history of the heliocentric doctrine as a formal theory in Book 5, and as a physical theory in Book 7. Another interesting part of Mr. De Morgan's researches are the notices which he has given of the early assertors of the heliocentric doctrine in England. These make their appearance as soon as it was well possible they should exist. The work of Copernicus was published, as we have said, in 1543. In September 1556, John Field published an ephemeris for 1557, Juxta Copernicus et Reinholdi Canons, in the preface to which he avows his conviction of the truth of the Copernican hypothesis. Robert Record, the author of various works on arithmetic, published among others, The Pathway to Knowledge in 1551. In this book, the author discusses the question of the quietness of the Earth and professes to leave it undecided. But Mr. De Morgan, comp. A. 1837, p. 33, conceives that it appears from what is said that he was really a Copernican, but did not think the world ripe for any such doctrine. Mr. Joseph Hunter also has brought to notice the claims of Field, whom he designates as the Proto-Copernican of England. He quotes the address to the reader prefixed to his first ephemeris, and dated May 31, 1556, in which he says that, since abler men decline the task, I have therefore published this ephemeris of the year 1557, following in it as my authorities N. Copernicus and Erasmus Reinhold, whose writings are established and founded on true, certain, and authentic demonstrations. I conceive that this passage, however, only shows that Field had adopted the Copernican scheme as a basis for the calculation of ephemerides, which, as Mr. De Morgan has remarked, is a very different thing from accepting it as a physical truth. Field, in this same address, makes mention of the errors Elias turbi qui alpansi uditor hypothesi, but the word hypothesis is still indecisive. As evidence that Field was regarded in his own day as a man who, 528, had rendered good service to science, Mr. Hunter notices that, in 1558, the heralds granted to him the right of using, with his arms, the crest or additional device of a red right arm issuing from the clouds, and presenting a golden armillary sphere. Record's claims depend upon a passage in a dialogue between master and scholar, in which the master expounds the doctrine of Copernicus and the authorities against it, to which the scholar answers, taking the common view, "Nay, sir, in good faith I desire not to hear such vain fantasies, so far against common reason, and repugnant to all the learned multitude of writers, and therefore let it pass for ever and a day longer." The master, more sagely, warns him against a hasty judgment and says, "Another time I will so declare his supposition, that you shall not only wonder to hear it, but also peradventure be as earnest then to credit it, as you now are now to condemn it." I conceive that this passage proves Mr. de Morgan's assertion that Record was a Copernican, and very likely the first in England. In 1555 also, Leonard Digges published his Prognostication Everlasting, but this is, as Mr. de Morgan says, Comp. A 1837, p. 40, a meteorological work. It was republished in 1592 by his son Thomas Digges with additions, and as these have been the occasion of some confusion among those who have written on the history of astronomy, I am glad to be able, through the kindness of Professor Walker of Oxford, to give a distinct account of the editions of the work. In the Bodleian Library, besides the editions of 1555 and 1592 of the Prognostication Everlasting, there is an edition of 1564. It is still decidedly Ptolemaic and contains a diagram representing a number of concentric circles, which are marked in order as the Earth, Moon, Venus, Mercury, Sun, Mars, Jupiter, Saturn, the starry firmament, the crystalline heavens, the first mover, the abode of God and the elect. Here the learned do approve. 529. The third edition of 1592 contains an addition by the son of 20 pages. He there speaks of having found, apparently among his father's papers, a description or model of the world and situation of spheres celestial and elementare according to the doctrine of Ptolemy, whereunto all universities, led thereunto chiefly by the authority of Aristotle, do consent. He adds, "But in this our age, one rare wit, seeing the continual errors that from time to time more and more continually have been discovered, besides the infinite absurdities in their theorics, which they have been forced to admit that would not confess any mobility in the ball of the earth, hath by long study, painful practice, and rare invention, delivered a new theoric or model of the world, showing that the earth resteth not in the center of the whole world or globe of elements, which encircled and enclosed in the moon's orb, and together with the whole globe of mortality is carried yearly round about the sun, which like a king in the midst of all, reigneth and giveth laws of motion to all the rest, spherically dispersing his glorious beams of light through all this sacred celestial temple. And the earth itself to be one of the planets, having his peculiar and strange courses, turning every 24 hours round upon his own center, whereby the sun and great globe of fixed stars seem to sway about and turn, albeit indeed they remain fixed so, many ways is the sense of mortal man abused." This edition is headed, "A perfect description of the celestial orbs, according to the most ancient doctrine of the Pythagoreans, lately revived by Copernicus and by geometrical demonstrations approved." Mr. de Morgan, not having seen this edition, and knowing the title page only as far as the word Pythagoreans, says their astrological doctrines we presume, not their reputed Copernican ones. But it now appears that in this, as in other cases, the authority of the Pythagoreans was claimed for the Copernican system. Antony a Wood quotes the latter part of the title thus, "Cui subnictiter orbium Copernicarum accurata descriptio," which is inaccurate. Weidler still more inaccurately cites it, "Cui subnictiter operum Copernicus accurata descriptio." Lalande goes still further, attempting, it would seem, to recover the English title page from the Latin we find in the Bible. Astron, the following, 1592, Leonard Digges, accurate description of the Copernican system to the astronomical perpetual prognostication. Thomas Digges appears, by others also of his writings, to have been 530, a clear and decided Copernican. In his Elisive Scali Mathematici, 1573, he bestows high praise upon Copernicus and upon his system, and appears to have been a believer in the real motion of the Earth, and not merely an admirer of the system of Copernicus as an explanatory hypothesis. Giordano Bruno. The complete title of the work referred to is Giordani Bruni Nalani de Monade Numero et Figura Liber Consequens Quinque de Minimo Magno et Mensura, item de innumerabilibus, immenso et infigurabili, Sudi Universo et Mundis Libri Octo. Frankfurti, 1591. That the reader may judge of the value of Bruno's speculations, I give the following quotations. Lib. Roman 4, C11 Index. Tellurum totem habitabilum esse in tus et extra, et innumerabilia animantium complecti, tum nobis sensibilium, tum occultorum genera. C13. Ut mundorum synodi in universo et particulars mundi in synodis ordinenter, and c. He says lib. VC1, p. 461. Besides the stars and the great worlds, there are smaller living creatures carried through the ethereal space, in the form of a small sphere which has the aspect of a bright fire, and is by the vulgar regarded as a fiery beam. They are below the clouds, and I saw one which seemed to touch the roofs of the houses. Now this sphere, or beam as they call it, was really a living creature, animal, which I once saw moving in a straight path, and grazing as it were the roofs of the city of Nola, as if it were going to impinge on Mount Cicada, which however it went over. There are two recent editions of the works of Giordano Bruno, by Adolf Wagner, Leipzig, 1830 in 2 volumes, and by Giefroyer, Berlin, 1833. Of the latter, I do not know that more than 1 volume, volume Roman II, has appeared. Did Francis Bacon reject the Copernican system? Mr. de Morgan has very properly remarked, Comp. B.A. 1855, p. 11, that the notice of the heliocentric question in the Novum Organon must be considered one of the most important passages in his works upon this point, as being probably the latest written and best, 531 matured. It occurs in Lib. Roman 2. Aphorism Roman 36, in which he is speaking of prerogative instances, of which he gives 27 species. In the passage now referred to, he is speaking of a kind of prerogative instances, better known to ordinary readers than most of the kinds by name, the instantia crucis, though probably the metaphor from which this name is derived is commonly wrongly apprehended. Bacon's meaning is guidepost instances, and the crux which he alludes to is not a cross, but a guidepost at crossroads. And among the cases to which such instances may be applied, he mentions the diurnal motion of the heavens from east to west, and the special motion of the particular heavenly bodies from west to east. And he suggests what he conceives may be an instantia crucis in each case. If, he says, we find any motion from east to west in the bodies which surround the earth, slow in the ocean, quicker in the air, quicker still in comets, gradually quicker in planets according to their greater distance from the earth, then we may suppose that there is a cosmical diurnal motion, and the motion of the earth must be denied. With regard to the special motions of the heavenly bodies, he first remarks that each body not coming quite so far westwards as before, after one revolution of the heavens, and going to the north or the south, does not imply any special motion, since it may be accounted for by a modification of the diurnal motion in each, which produces a defect of the return and a spiral path. And he says that if we look at the matter as common people and disregard the devices of astronomers, the motion is really so to the senses, and that he has made an imitation of it by means of wires. The instantia crucis which he here suggests is to see if we can find in any credible history an account of any comet which did not share in the diurnal revolution of the skies. Note 30:A. Et certissimum est si polisper pro plebis nos geramus, missus astronomorum et scali commentis, quibus alud in mor est, ut sensui in multis immerito vim facient, et obscurira malent, talem es modum istum ad sensum qualum diximus. On his assertion that the motion of each separate planet is, to sense, a spiral, we may remark that it is certainly true, but that the business of science, here as elsewhere, consists in resolving the complex phenomenon into simple phenomena, the complex spiral motion into simple circular motions. With regard to the diurnal motion of the earth, it would seem as if Bacon himself had a leaning to believe it when he wrote this passage, for neither is he himself, nor are any of the anti-Copernicans. 532, accustomed to assert that the immensely rapid motion of the sphere of the fixed stars graduates by a slower and slower motion of planets, comets, air, and ocean, into the immobility of the Earth. So that the conditions are not satisfied on which he hypothetically says, tum abnegandus est modus terrae. With regard to the proper motions of the planets, this passage seems to me to confirm what I have already said of him, that he does not appear to have seen the full value and meaning of what had been done, up to his time, in formal astronomy. We may, however, fully agree with Mr. de Morgan that the whole of what he has said on this subject, when put together, does not justify Hume's assertion that he rejected the Copernican system with the most positive disdain. Mr. de Morgan, in order to balance the Copernican argument derived from the immense velocity of the stars in their diurnal velocity on the other supposition, has reminded us that those who reject this great velocity as improbable accept without scruple the greater velocity of light. It is curious that Bacon also has made this comparison, though using it for a different purpose, namely, to show that the transmission of the visual impression may be instantaneous. In Aphorism, Roman 46. Of Book 2 of the Novum Organon, he is speaking of what he calls instantiae curriculi, or instantiae ad aquam, which we may call instances by the clock. And he says that the great velocity of the diurnal sphere makes the marvelous velocity of the rays of light more credible. Immensa illa velocitas in ipso corpore, qui cerniter in modu diurno, qui etiam viros graves ida obstupefecit ut malent credier modum terri, facit modum illum ejaculationis ob ipsis, licet celeritate ut diximus admirabilum, magis credibilum. This passage shows an inclination towards the opinion of the Earth's being at rest, but not a very strong conviction. Kepler persecuted. We have seen, p. 280, that Kepler writes to Galileo in 1597, "Be trustful and go forwards. If Italy is not a convenient place for the publication of your views, and if you are likely to meet with any obstacles, perhaps Germany will grant us the necessary liberty." Kepler, however, had soon afterwards occasion to learn that in Germany also, the cultivators of science were exposed to persecution. It is true that 533, in his case, the persecution went mainly on the broad ground of his being a Protestant, and extended to great numbers of persons at that time. The circumstances of this and other portions of Kepler's life have been brought to light only recently through an examination of public documents in the archives of Württemberg and unpublished letters of Kepler. Johann Kepler's Leben und Werken, nach neuerlich aufgefundenen Manuskripten Bearbeitet von J. L. C. Freiherren wie Breitschwart, K. Württemberg. Staatsrath. Stuttgart, 1831. Schiller, in his History of the 30 Years' War, says that when Ferdinand of Austria succeeded to the Archduchy of Styria, and found a great number of Protestants among his subjects, he suppressed their public worship without cruelty and almost without noise. But it appears now that the Protestants were treated with great severity. Kepler held a professorship in Styria, and had married in 1507 Barbara Muller, who had landed property in that province. On the 11th of June, 1598, he writes to his friend Meislin that the arrival of the prince out of Italy is looked forwards to with terror. In December, he writes that the Protestants had irritated the Catholics by attacks from the pulpit and by caricatures, that hereupon the prince, at the prayer of the estates, had declared the letter of license granted by his father to be forfeited, and had ordered all the evangelical teachers to leave the country on pain of death. They went to the frontiers of Hungary and Croatia, but after a month, Kepler was allowed to return on condition of keeping quiet. His discoveries appear to have operated in his favor. But the next year he found his situation in Styria intolerable and longed to return to his native country of Württemberg and to find some position there. This he did not obtain. He wrote a circular letter to his brother Protestants to give them consolation and courage, and this was held to be a violation of the conditions on which his residence was tolerated. Fortunately, at this time he was invited to join Tycho Brahe, who had also been driven from his native country and was living at Prague. The two astronomers worked together under the patronage of the Emperor Rudolf Roman II. And when Tycho died in 1601, Kepler became the imperial mathematicus. We are not to imagine that even among Protestants, astronomical notions were out of the sphere of religious considerations. When Kepler was established in Styria, his first official business was the calculation of the calendar for the evangelical community. They protested against the new calendar, as manifestly calculated for the furtherance of an impious papistry, and, say they, we hold the Pope for a 534 horrible roaring lion. If we take his calendar, we must needs go into the church when he rings us in. Kepler, however, did not fail to see, and to say, that the papal reformation of the calendar was a vast improvement. Kepler, as court astronomer, was of course required to provide such observations of the heavens as were requisite for the calculations of the astrologers. That he considered astrology to be valuable only as the nurse of astronomy, he did not hesitate to reveal. He wrote a work with a title of which the following is the best translation which I can give: Tertius Interveniens, or A Warning to Certain Theologi Medici Philosophy, that while they reasonably reject stargazing superstition, they do not throw away the kernel with the shell. 1610. In this he says, "You overclever philosophers blame this daughter of astronomy more than is reasonable. Do you not know that she must maintain her mother with her charms? How many men would be able to make astronomy their business, if men did not cherish the hope to read the future in the skies?" Note 31-A. The German passage involves a curious image, borrowed, I suppose, from some odd story. Das sei mit billiger Verwerfung des Sterngekerischen Aberglaubens des Kind nicht mit dem Bade auscht. That they do not throw away the child along with the dirty water of his bath. Were the papal edicts against the Copernican system repealed? Admiral Smythe, in his Cycle of Celestial Objects, volume IP 65, says, at length, in 1818, the voice of truth was so prevailing that Pius Roman VII repealed the edicts against the Copernican system, and thus, in the emphatic words of Cardinal Torriazzi, wiped off this scandal from the Church. A like story is referred to by Sir Francis Palgrave, in his entertaining and instructive fiction, The Merchant and the Friar. Having made inquiry of persons most likely to be well informed on this subject, I have not been able to learn that there is any further foundation for these statements than this. In 1818, on the revisal of the Index Expurgatorius, Galileo's writings were, after some opposition, expunged from that catalogue. Monsignor Marino Marini, an eminent Roman prelate, had addressed to the Romana Academia di Archeologia certain historico-critical memoirs, which he published in 1850 with the title Galileo e Elenquisizione. In these, he confirms the conclusion which I think almost 535 all persons who have studied the facts have arrived at, that Galileo trifled with authority to which he professed to submit, and was punished for obstinate contumacy, not for heresy. M. Marini renders full justice to Galileo's ability, and does not at all hesitate to regard his scientific attainments as among the glories of Italy. He quotes what Galileo himself quoted, an expression of Cardinal Baronius, that the intention of the Holy Spirit was to teach how to go to heaven, not how heaven goes. He shows that Galileo pleaded, p. 62, that he had not held the Copernican opinion after it had been intimated to him, by Bellarmine in 1616, that he was not to hold it, and that his breach of promise in this respect was the cause of the proceedings against him. Note 32-A. M. Marini, p. 29, mentions Leibniz, Gizot, Spittler, Eichhorn, Römer, rank among the Storicei Heterodoxi who have at last done justice to the Roman Church. Those who admire Galileo and regard him as a martyr because, after escaping punishment by saying, "It does not move," he forthwith said, "and yet it does move," will perhaps be interested to know that the former answer was suggested to him by friends anxious for his safety. Niccolini writes to Bali Scioli, April 9, 1633, that Galileo continued to be so persuaded of the truth of his opinions that he was resolved, some moments before his sentence, to defend them stoutly. But I, continues Niccolini, exhorted him to make an end of this, not to mind defending them, and to submit himself to that which he sees that they may desire him to believe or to hold about this matter of the motion of the earth. He was extremely afflicted. But the Inquisition was satisfied with his answers, and required no more. 536, Book 6. Mechanics. Chapter 3. Principles and Problems. Significance of analytical mechanics. In the text, page 372, I have stated that Lagrange, near the end of his life, expressed his sorrow that the methods of approximation employed in physical astronomy rested on arbitrary processes, and not on any insight into the results of mechanical action. From the recent biography of Gauss, the greatest physical mathematician of modern times, we learn that he congratulated himself on having escaped this error. He remarked that many of the most celebrated mathematicians, Euler very often, Lagrange sometimes, had trusted too much to the symbolical calculation of their problems, and would not have been able to give an account of the meaning of each successive step of their investigation. He said that he himself, on the other hand, could assert that at every step which he took, he always had the aim and purpose of his operations before his eyes without ever turning aside from the way. The same, he remarked, might be said of Newton. Note 35 \A. Gauss, zum Gedächtnis von W. Sartorius v. Walterschassen p. 80. Engineering mechanics. The principles of the science of mechanics were discovered by observations made upon bodies within the reach of men, as we have seen in speaking of the discoveries of Stevinus, Galileo, and others, up to the time of Newton. And when there arose the controversy about vis viva, chapter v. sect. 2 of this book, namely, whether the living force of a body is measured by the product of the weight into the 537 velocity, or of the weight into the square of the velocity, still the examples taken were cases of action in machines and the like terrestrial objects. But Newton's discoveries identified celestial with terrestrial mechanics, and from that time, the mechanical problems of the heavens became more important and attractive to mathematicians than the problems about earthly machines. And thus the generalizations of the problems, principles, and methods of the mathematical science of mechanics from this period are principally those which have reference to the motions of the heavenly bodies, such as the problem of three bodies, the principles of the conservation of areas, and of the immovable plane, the method of variation of parameters, and the like, chapter Romans 6. Sect. 7 and 14. And the same is the case in the more recent progress of that subject, in the hands of Gauss, Bessel, Hansen, and others. But yet the science of mechanics as applied to terrestrial machines, industrial mechanics, as it has been termed, has made some steps which it may be worthwhile to notice, even in a general history of science. For the most part, all the most general laws of mechanical action being already finally established, in the way which we have had to narrate, the determination of the results and conditions of any combination of materials and movements becomes really a mathematical deduction from known principles. But such deductions may be made much more easy and much more luminous by the establishment of general terms and general propositions suited to their special conditions. Among these I may mention a new abstract term, introduced because a general mechanical principle can be expressed by means of it, which has lately been much employed by the mathematical engineers of France. Poncelet, Navier, Morin, and C. The abstract term is travail, which has been translated laboring force, and the principle which gives it its value and makes it useful in the solution of problems is this, that the work done in overcoming resistance or producing any other effect is equal to the laboring force, by whatever contrivances the force be applied. This is not a new principle, being in fact mathematically equivalent to the conservation of vis viva. But it has been employed by the mathematicians of whom I have spoken with a fertility and simplicity which make it the mark of a new school of the mechanics of engineering. The laboring force expended and the work done have been described by various terms as theoretical effect and practical effect, and the like. The usual term among English engineers for the work, 538, which an engine usually does, is duty. But as this word naturally signifies what the engine ought to do, rather than what it does, we should at least distinguish between the theoretical and the actual duty. The difference between the theoretical and actual duty of a machine arises from this, that a portion of the laboring force is absorbed in producing effects, that is, in doing work which is not reckoned as duty, for instance, overcoming the resistance and waste of the machine itself. And so long as this resistance and waste are not rightly estimated, no correspondence can be established between the theoretical and the practical duty. Though much had been written previously upon the theory of the steam engine, the correspondence between the force expended and the work done was not clearly made out, till Comte de Pamber published his treatise on locomotive engines in 1835, and his theory of the steam engine in 1839. Strength of materials. Among the subjects which have specially engaged the attention of those who have applied the science of mechanics to practical matters is the strength of materials. For example, the strength of a horizontal beam to resist being broken by a weight pressing upon it. This was one of the problems which Galileo took up. He was led to his study of it by a visit which he made to the arsenal and dockyards of Venice, and the conclusions which he drew were published in his Dialogues in 1633. In his mode of regarding the problem, he considers the section at which the beam breaks as the short arm of a bent lever which resists fracture, and the part of the beam which is broken off as the longer arm of the lever turning about the fracture as a hinge. So far this is true, and from this principle, he obtained results which are also true, as that the strength of a rectangular beam is proportional to the breadth multiplied into the square of the depth, that a hollow beam is stronger than a solid beam of the same mass, and the like. But he erred in this, that he supposed the hinge about which the breaking beam turns to be exactly at the unrent surface, that surface resisting all change, and the beam being rent all the way across. Whereas the fact is that the unrent surface yields to compression, while the opposite surface is rent, and the hinge about which the breaking beam turns is at an intermediate point, where the extension, 539 and rupture end, and the compression and crushing begin, a point which has been called the neutral axis. This was pointed out by Marriott, and the notion, once suggested, was so manifestly true that it was adopted by mathematicians in general. James Bernoulli, in 1705, investigated the strength of beams on this view, and several eminent mathematicians pursued the subject, as Varignon, Parent, and Bulfinger, and at a later period, Dr. Robison in our own country. But along with the fracture of beams, the mathematicians considered also another subject, the flexure of beams, which they undergo before they break, in virtue of their elasticity. What is the elastic curve? The curve into which an elastic line forms itself under the pressure of a weight is a problem which had been proposed by Galileo, and was fully solved as a mathematical problem by Euler and others. But beams in practice are not mere lines, they are solids, and their resistance to flexure, and the amount of it, depends upon the resistance of their internal parts to extension and compression, and is different for different substances. To measure these differences, Dr. Thomas Young introduced the notion of the modulus of elasticity, meaning thereby a column of the substance of the same diameter, such as would by its weight produce a compression equal to the whole length of the beam, the rate of compression being supposed to continue the same throughout. Thus, if a rod of any kind, 100 inches long, were compressed 1 inch by a weight 1,000 pounds, the weight of its modulus of elasticity would be 100,000 pounds. This notion assumes Hooke's law that the extension of a substance is as its tension, and extends this law to compression also. Note 37A, Lecture Roman 13. The height of the modulus is the same for the same substance, whatever its breadth and thickness may be. For atmospheric air it is about 5 miles, and for steel nearly 1,500 miles. There is this great advantage in introducing the definition of the modulus of elasticity that it applies equally to the flexure of a substance, and to the minute vibrations which propagate sound, and the like. And the notion was applied so as to lead to curious and important results with regard to the power of beams to resist flexure, not only when loaded transversely, but when pressed in the direction of their length and in any oblique direction. But in the fracture of beams, the resistance to extension and to compression are not practically equal, and it was necessary to determine, 540, the difference of these two forces by experiments. Several persons pursued researches on this subject, especially Mr. Barlow, of the Royal Military Academy, who investigated the subject with great labor and skill, so far as wood is concerned. But the difference between the resistance to tension and to compression requires more special study in the case of iron, and has been especially attended to in recent times in consequence of the vast increase in the number of iron structures, and in particular railways. It appears that wrought iron yields to compressive somewhat more easily than to tensile force, while cast iron yields far more easily to tensile than to compressive strains. In all cases, the power of a beam to resist fracture resides mainly in the upper and the underside, for there the tenacity of the material acts at the greatest leverage round the hinge of fracture. Hence the practice was introduced of making iron beams with a broad flange at the upper and another flange at the underside, connected by a vertical plate or web, of which the office was to keep the two flanges asunder. Mr. Hodgkinson made many valuable experiments, on a large scale, to determine the forms and properties of such beams. Note 38/A, an essay on the strength and shape of timber, 3D edition, 1826. But though engineers were, by such experiments and reasonings, enabled to calculate the strength of a given iron beam and the dimensions of a beam which should bear a given load, it would hardly have occurred to the boldest speculator, a few years ago, to predict that there might be constructed beams nearly 500 feet long, resting merely on their two extremities, of which it could be known beforehand that they would sustain without bending or yielding in any perceptible degree the weight of a railroad train and the jar of its unchecked motion. Yet of such beams, constructed beforehand with the most perfect confidence, crowned with the most complete success, is composed the great tubular bridge which that consummate engineer, Mr. Robert Stephenson, has thrown across the Menai Strait, joining Wales with the island of Anglesey. The upper and under surfaces of this quadrangular tube are the flanges of the beam, and the two sides are the webs which connect them. In planning this wonderful structure, the point which required especial care was to make the upper surface strong enough to resist the compressive force which it has to sustain. And this was done by constructing the upper part of the beam of a series of cells, made of iron plate. The application of the arch, of the dome, and of groined vaulting, to the widest space over which they have ever been thrown, 541, are achievements which have, in the ages in which they occurred, been received with great admiration and applause. But in those cases the principle of the structure had been tried and verified for ages upon a smaller scale. Here not only was the space thus spanned wider than any ever spanned before, but the principle of such a beam with a cellular structure of its parts was invented for this very purpose, experimentally verified with care, and applied with the most exact calculation of its results. Roofs, arches, vaults. The calculations of the mechanical conditions of structures consisting of several beams, as for instance, the frames of roofs, depends upon elementary principles of mechanics, and was a subject of investigation at an early period of the science. Such frames may be regarded as assemblages of levers. The parts of which they consist are rigid beams which sustain and convey force, and ties which resist such force by their tension. The former parts must be made rigid in the way just spoken of with regard to iron beams, but ties may be rods merely. The wide structures of many of the roofs of railway stations, compared with the massive wooden roofs of ancient buildings, may show us how boldly and how successfully this distinction has been carried out in modern times. The investigation of the conditions and strength of structures consisting of wooden beams has been cultivated by mathematicians and engineers, and is often entitled carpentry in our mechanical treatises. In our own time, Dr. Robison and Dr. Thomas Young have been two of the most eminent mathematicians who have written upon this subject. The properties of the simple machines have been known, as we have narrated, from the time of the ancient Greeks. But it is plain that such machines are prevented from producing their full effect by various causes. Among the rest, the rubbing of one part of the machine upon another produces an obstacle to the effectiveness of a machine. For instance, the rubbing of the axle of a wheel in the hole in which it rests, the rubbing of a screw against the sides of its hollow screw, the rubbing of a wedge against the sides of its notch, the rubbing of a cord against its pulley. In all these cases, the effect of the machine to produce motion is diminished by the friction. And this friction may be measured and its effects calculated, and thus we have a new branch of mechanics which has been much cultivated. 542. Among the effects of friction, we may notice the standing of a stone arch. For each of the vaulting stones of an arch is a truncated wedge, and though a collection of such stones might be so proportioned in their weights as to balance exactly, yet this balance would be a tottering equilibrium, which the slightest shock would throw down and which would not practically subsist. But the friction of the vaulting stones against one another prevents this instability from being a practical inconvenience and makes an equilibrated arch to be an arch strong for practical purposes. The theory of arches is a portion of mechanics which has been much cultivated and which has led to conclusions of practical use as well as of theoretical beauty. I have already spoken of the invention of the arch, the dome, and groined vaulting as marked steps in building. In all these cases, the invention was devised by practical builders, and mechanical theory, though it can afterwards justify these structures, did not originally suggest them. They are not part of the result, nor even of the application of theory, but only of its exemplification. The authors of all these inventions are unknown, and the inventions themselves may be regarded as a part of the prelude of the science of mechanics, because they indicate that the ideas of mechanical pressure and support, in various forms, are acquiring clearness and fixity. In this point of view, I spoke Book 4, Chapter V Sect 5 of the Architecture of the Middle Ages as indicating a progress of thought which led men towards the formation of statics as a science. As particular instances of the operation of such ideas, we have the flying buttresses which support stone vaults, and especially, as already noted, the various contrivances by which stone vaults are made to intersect one another, so as to cover a complex pillared space below with groined vaulting. This invention, executed as it was by the builders of the 12th and succeeding centuries, is the most remarkable advance in the mechanics of building, after the invention of the arch itself. It is curious that it has been the fortune of our times, among its many inventions, to have produced one in this department, of which we may say that it is the most remarkable step in the mechanics of arches which has been made since the introduction of pointed groined vaults. I speak of what are called skew arches, in which the courses of stone or brick of which the bridge is built run obliquely to the walls of the bridge. Such bridges have become very common in the works of railroads, for they save space and material, and the 543 invention once made, the cost of the ingenuity is nothing. Of course, the mechanical principles involved in such structures are obvious to the mathematician when the problem has been practically solved. And in this case, as in the previous cardinal inventions in structure, though the event has taken place within a few years, no single person, so far as I am aware, can be named as the inventor. Note 39\A. Since this was written, I have been referred to Rees's Cyclopedia, article oblique arches, where this invention is correctly explained, and is claimed for an engineer named Chapman. It is there said that the first arch of this kind was erected in 1787 at Naas, near Kildare in Ireland. 544, Book 7. Physical Astronomy. Chapter 1. Prelude to Newton. The Ancients. Expressions in ancient writers which may be interpreted as indicating a notion of gravitation in the Newtonian sense, no doubt occur. But such a notion, we may be sure, must have been in the highest degree obscure, wavering, and partial. I have mentioned, Book 1, Chapter 3, an author who has fancied that he traces in the works of the ancients the origin of most of the vaunted discoveries of the moderns. But to ascribe much importance to such expressions would be to give a false representation of the real progress of science. Yet some of Newton's followers put forward these passages as well deserving notice, and Newton himself appears to have had some pleasure in citing such expressions, probably with the feeling that they relieved him of some of the odium which, he seems to have apprehended, hung over new discoveries. The preface to the Principia begins by quoting the authority of the ancients, as well as the moderns, in favor of applying the science of mechanics to natural philosophy. In the preface to David Gregory's Astronomiae Physicae et Geometricae Elementa, published in 1702, is a large array of names of ancient authors, and of quotations, to prove the early and wide diffusion of the doctrine of the gravity of the heavenly bodies. And it appears to be now made out that this collection of ancient authorities, 545, was supplied to Gregory by Newton himself. The late Professor Rigaud, in his historical essay on the first publication of Sir Isaac Newton's Principia, says, pp. 80 and 101, that having been allowed to examine Gregory's papers, He found that the quotations given by him in his preface are copied or abridged from notes which Newton had supplied to him in his own handwriting. Some of the most noticeable of the quotations are those taken from Plutarch's dialogue on the face which appears in the moon's disk. It is there said, for example, by one of the speakers, that the moon is perhaps prevented from falling to the earth by the rapidity of her revolution round it, as a stone whirled in a sling keeps it stretched. Lucretius also is quoted as teaching that all bodies would descend with an equal celerity in a vacuum, omnia quapropter debent per inane quietum ec ponderibus non equis concita feri. Lib. Roman 2. v. 238. Note 40 \a. Cum vetters mechanicam, iudi author est papus. In rerum naturalium investigation maximi fesserent, et recentiers, Mrs. Formis substantialibus et qualitatibus occultis, phenomena naturae ad legs mathematicas revocare aggressa sunt. Visum est in hoc tractatum Matheson excoler quatenus e ad philosophiam spectat. It is asserted in Gregory's preface that Pythagoras was not unacquainted with the important law of gravity, the inverse squares of the distances from the center. For, it is argued, the 7 strings of Apollo's lyre mean the 7 planets, and the proportions of the notes of strings are reciprocally as the inverse squares of the weights which stretch them. I have attempted, throughout this work, to trace the progress of the discovery of the great truths which constitute real science, in a more precise manner than that which these interpretations of ancient authors exemplify. Jeremiah Horrocks. In describing the prelude to the Epoch of Newton, I have spoken, p. 395, of a group of philosophers in England who began, in the first half of the 17th century, to knock at the door where truth was to be found, although it was left for Newton to force it open, and I have there noticed the influence of the civil wars on the progress of philosophical studies. To the persons thus tending towards the true physical theory of the solar system, I ought to have added Jeremy Horrocks, whom I have mentioned in a former part, Book 5, Chapter 5, as one of the earliest admirers of Kepler's discoveries. He died at the early age of 22, having been the first person who ever saw Venus pass across the disk of the Sun according to astronomical prediction, which took place in 1639. His Venus in Sol Visa, 546, in which this is described, did not appear till 1661, when it was published by Hevelius of Danzig. Some of his papers were destroyed by the soldiers in the English Civil Wars, and his remaining works were finally published by Wallis in 1673. The passage to which I here specially wish to refer is contained in a letter to his astronomical ally, William Crabtree, dated 1638. He appears to have been asked by his friend to suggest some cause for the motion of the aphelion of a planet, and in reply, he uses an experimental illustration, which was afterwards employed by Hooke in 1666. A ball at the end of a string is made to swing so that it describes an oval. This contrivance Hooke employed to show the way in which an orbit results from the combination of a projectile motion with a central force. But the oval does not keep its axis constantly in the same position. The apsides, as Horrocks remarked, move in the same direction as the pendulum, though much slower. And it is true that this experiment does illustrate, in a general way, the cause of the motion of the aphelia of the planetary orbits. Although the form of the orbit is different in the experiment and in the solar system, being an ellipse with the center of force in the center of the ellipse, in the former case, and an ellipse with the center of force in the focus, in the latter case. These two forms of orbits correspond to a central force varying directly as the distance, and a central force varying inversely as the square of the distance, as Newton proved in the Principia. But the illustration appears to show that Horrocks pretty clearly saw how an orbit arose from a central force. So far, and no further, Newton's contemporaries could get, and then he had to help them onwards by showing what was the law of the force and what larger truths were now attainable. Newton's discovery of gravitation. As I have already remarked, men have a willingness to believe that great discoveries are governed by casual coincidences and accompanied by sudden revolutions of feeling. Newton had entertained the thought of the moon being retained in her orbit by gravitation as early as 1665 or 1666. He resumed the subject and worked the thought out into a system in 1684 and 5. What induced him to return to the question? What led to his success on this last occasion? With what feelings was the success attended? It is easy to make an imaginary connection of facts. His optical discoveries had recommended him to the Royal Society, and he was now a member. He, 547, there learned the accurate measurement of the Earth by Picard, differing very much from the estimation by which he had made his calculation in 1666, and he thought his conjecture now more likely to be just. M. Biot gives his assent to this guess. The English translation of M. Biot's biography converts the guess into an assertion. But, says Professor Rigaud, Picard's measurement of the Earth was well known to the Fellows of the Royal Society as early as 1675, there being an account of the results of it given in the Philosophical Transactions for that year. Moreover, Norwood, in his Seaman's Practice, dated 1636, had given a much more exact measure than Newton employed in 1666. But Norwood, says Voltaire, had been buried in oblivion by the civil wars. No, again, says the exact and truth-loving Professor Rigaud, Norwood was in communication with the Royal Society in 1667 and 1668. So these guesses at the accident which made the apple of 1665 germinate in 1684 are to be carefully distinguished from history. Note 41-A, Robison's Mechanical Philosophy, Volume Roman 3, p. 94. Art, 195. Note 44-A, Historical Essay on the First Publication of the Principia, 1838. But with what feelings did Newton attain to his success? Here again we have, I fear, nothing better than conjecture. He went home, took out his old papers, and resumed his calculations. As they drew near to a close, he was so much agitated that he was obliged to desire a friend to finish them. His former conjecture was now found to agree with the phenomena with the utmost precision. This conjectural story has been called a tradition, but he who relates it does not call it so. Everyone must decide, says Professor Rigaud from his view of Newton's character, how far he thinks it consistent with this statement. Is it likely that Newton, so calm and so indifferent to fame as he generally showed himself, should be thus agitated on such an occasion? No, says Sir David Brewster, it is not supported by what we know of Newton's character. To this we may assent, and this conjectural incident we must therefore, I conceive, separate from history. I had incautiously admitted it into the text of the first edition. Newton appears to have discovered the method of demonstrating that a body might describe an ellipse when acted upon by a force residing in the focus, and varying inversely as the square of the distance, in 1669, upon occasion of his correspondence with Hooke. In 1684, 548 at Halle's request, he returned to the subject, and in February 1685 there was inserted in the Register of the Royal Society a paper of Newton's, Issae Newtoni Propositions de Motu, which contained some of the principal propositions of the first two books of the Principia. This paper, however, does not contain the proposition Lunam Graviter in Terram, nor any of the propositions of the third book. Chapter 3. The Principia. Sect 2. Reception of the Principia. Lord Brougham has very recently, analytical view of Sir Isaac Newton's Principia, 1855, shown a strong disposition still to maintain, what he says has frequently been alleged, that the reception of the work was not, even in this country, such as might have been expected. He says, in explanation of the facts which I have adduced, showing the high estimation in which Newton was held immediately after the publication of the Principia, that Newton's previous fame was great by former discoveries. This is true, but the effect of this was precisely what was most honorable to Newton's countrymen, that they received with immediate acclamations this new and greater discovery. Lord Brougham adds, after its appearance the Principia was more admired than studied, which is probably true of the Principia still, and of all great works of like novelty and difficulty at all times. But, says Lord Brougham, there is no getting over the inference on this head which arises from the dates of the two first editions. There elapsed an interval of no less than 27 years between them. And although Coates speaks of the copies having become scarce and in very great demand when the second edition appeared in 1713, yet had this urgent demand been of many years' continuance, the reprinting could never have been so long delayed. But Lord Brougham might have learnt from Sir David Brewster's Life of Newton, volume IP 312, which he extols so emphatically, that already in 1691, only 4 years after the publication, A copy of the Principia could hardly be procured, and that even at that 549 time an improved edition was in contemplation, that Newton had been pressed by his friends to undertake it, and had refused. When Bentley had induced Newton to consent that a new edition should be printed, he announces his success with obvious exultation to Coates, who was to superintend the work. And in the meantime, the Astronomy of David Gregory, published in 1702, showed in every page how familiar the Newtonian doctrines were to English philosophers, and tended to make them more so, as the sermons of Bentley himself had done in 1692. Newton's Cambridge contemporaries were among those who took a part in bringing the Principia before the world. The manuscript draft of it was conveyed to the Royal Society, April 28, 1686, by Dr. Vincent, Fellow of Clare Hall, who was the tutor of Whiston, Newton's deputy in his professorship. And he, in presenting the work, spoke of the novelty and dignity of the subject. There exists in the library of the University of Cambridge a manuscript containing the early propositions of the Principia as far as Prop. Roman 33, which is a part of Section 7, about falling bodies. This appears to have been a transcript of Newton's lectures, delivered as Lucasian professor. It is dated October, 1684. Is gravitation proportional to quantity of matter? It was a portion of Newton's assertion in his great discovery, that all the bodies of the universe attract each other with forces which are as the quantity of matter in each. That is, for instance, the sun attracts the satellites of any planet just as much as he attracts the planet itself, in proportion to the quantity of matter in each. And the planets attract one another just as much as they attract the sun, according to the quantity of matter. To prove this part of the law exactly is a matter which requires careful experiments, and though proved experimentally by Newton, has been considered in our time worthy of re-examination by the great astronomer Bessel. There was some ground for doubt, for the mass of Jupiter, as deduced from the perturbations of Saturn, was only 1/1070 of the mass of the Sun. The mass of the same planet, as deduced from the perturbations of Juno and Pallas, was 1/1045 of that of the Sun. If this difference were to be confirmed by accurate observations and calculations, it would follow that the attractive power exercised by Jupiter upon the minor planets was greater than that exercised upon 550 Saturn. And in the same way, if the attraction of the Earth had any specific relation to different kinds of matter, the time of oscillation of a pendulum of equal length composed wholly or in part of the two substances would be different. If, for instance, it were more intense for magnetized iron than for stone, the iron pendulum would oscillate more quickly. Bessel showed that it was possible to assume hypothetically a constitution of the Sun, planets, and their appendages, such that the attraction of the Sun on the planets and satellites should be proportional to the quantity of matter in each, but that the attraction of the planets on one another would not be on the same scale. Newton had made experiments, described in the Principia, Book 3, Prop. Roman 6, by which it was shown that there could be no considerable or palpable amount of such specific difference among terrestrial bodies, but his experiments could not be regarded as exact enough for the requirements of modern science. Bessel instituted a laborious series of experiments, presented to the Berlin Academy in 1832, which completely disproved the conjecture of such a difference. Every substance examined having given exactly the same coefficient of gravitating intensity as compared with inertia. Among the substances examined were metallic and stony masses of meteoric origin, which might be supposed, if any bodies could, to come from other parts of the solar system. Chapter 4. Verification and completion of the Newtonian theory. Tables of the moon and planets. The Newtonian discovery of universal gravitation, so remarkable in other respects, is also remarkable as exemplifying the immense extent to which the verification of a great truth may be carried, the amount of human labor which may be requisite to do it justice, and the striking extension of human knowledge to which it may lead. I have said that it is remarked as a beauty in the first fixation of a theory that its measures or elements are established by means of a few 551 data, but that its excellence when established is in the number of observations which it explains. The multiplicity of observations which are explained by astronomy, and which are made because astronomy explains them, is immense, as I have noted in the text. And the multitude of observations thus made is employed for the purpose of correcting the first adopted elements of the theory. I have mentioned some of the examples of this process. I might mention many others in order to continue the history of this part of astronomy up to the present time, but I will notice only those which seem to me the most remarkable. In 1812, Burckhardt's Tables de la Lune were published by the French Bureau des Longitudes. A comparison of these and Berg's with a considerable number of observations gave 9-100 ths of a second as the mean error of the former in the Moon's longitude, while the mean error of Berg's was 18-100 ths. The preference was therefore accorded to Burckhardt's. Yet the lunar tables were still as much as 30 seconds wrong in single observations. This circumstance, and Laplace's expressed wish, induced the French Academy to offer a prize for a complete and purely theoretical determination of the lunar path, instead of determinations resting, as hitherto, partly upon theory and partly upon observations. In 1820, 2 prize essays appeared, the one by Damiso, the other by Plana and Carlini. And some years afterwards, in 1824, and again in 1828, Damiso published Tables de la Lune formées sur la seule théorie d'attraction. These agree very closely with observation. That we may form some notion of the complexity of the problem, I may state that the longitude of the Moon is in these tables affected by no fewer than 47 equations, and the other quantities which determine her place are subject to inequalities not much less in number. Still, I had to state in the second edition, published in 1847, that there remained an unexplained discordance between theory and observation in the motions of the Moon, an inequality of long period as it seemed, which the theory did not give. A careful examination of a long series of the best observations of the Moon, compared throughout with the theory in its most perfect form, would afford the means both of correcting the numerical elements of the theory and of detecting the nature, and perhaps the law, of any still remaining discrepancies. Such a work, however, required vast labor, as well as great skill and profound mathematical knowledge. 552, Mr. Airy undertook the task, employing for that purpose the observations of the Moon made at Greenwich from 1750 to 1830. Above 8,000 observed places of the Moon were compared with theory by the computation of the same number of places, each separately and independently calculated from Plana's formulae. A body of calculators, sometimes 16, at the expense of the British government, was employed for about 8 years in this work. When we take this in conjunction with the labor which the observations themselves imply, it may serve to show on what a scale the verification of the Newtonian theory has been conducted. The first results of this labor were published in 2 quarto volumes. The final deductions as to correction of elements, and c, were given in the Memoirs of the Astronomical Society in 1848. Note 48/A. The total expense of computers, to the end of reading the proof sheets, was 4,300 L. Mr. Airy's estimate of days' works, for the heavy part of calculations only, was 36 years of one computer. This was somewhat exceeded, but not very greatly, in that part. Even while the calculations were going on, it became apparent that there were some differences between the observed places of the Moon, and the theory so far as it had then been developed. M. Hansen, an eminent German mathematician who had devised new and powerful methods for the mathematical determination of the results of the law of gravitation, was thus led to explore still further the motions of the Moon in pursuance of this law. The result was that he found there must exist 2 lunar inequalities, hitherto not known, the one of 273 and the other of 239 years, the coefficients of which are respectively 27 and 23 seconds. Both these originate in the attraction of Venus, one of them being connected with the long inequality in the solar tables, of which Mr. Airy had already proved the existence, as stated in chapter Roman 6. Sect. 6 of this book. These inequalities fell in with the discrepancies between the actual observations and the previously calculated tables, which Mr. Airy had discovered. And again, shortly afterwards, M. Hansen found that there resulted from the theory 2 other new equations of the Moon, one in latitude and one in longitude, agreeing with 2 which were found by Mr. Airy in deducing from the observations the correction of the elements of the lunar tables. And again, a little later, there was detected by these mathematicians a theoretical correction for the 553 motion of the node of the Moon's orbit, coinciding exactly with one which had been found to appear in the observations. Nothing can more strikingly exhibit the confirmation which increased scrutiny brings to light between the Newtonian theory on the one hand and the celestial motions on the other. We have here a very large mass of the best observations which have ever been made, systematically examined, with immense labor, and with the set purpose of correcting at once all the elements of the lunar tables. The corrections of the elements thus deduced imply of course some error in the theory as previously developed. But at the same time, and with the like determination thoroughly to explore the subject, the theory is again pressed to yield its most complete results by the invention of new and powerful mathematical methods. And the event is that residual errors of the old tables, several in number, following the most diverse laws, occurring in several detached parts, agree with the residual results of the theory thus newly extracted from it. And thus every additional exactness of scrutiny into the celestial motions on the one hand and the Newtonian theory on the other has ended, sooner or later, in showing the exactness of their coincidence. The comparison of the theory with observation in the case of the motions of the planets, the motion of each being disturbed by the attraction of all the others, is a subject in some respects still more complicated and laborious. This work also was undertaken by the same indefatigable astronomer, and here also his materials belong to the same period as before, being the admirable observations made at Greenwich from 1750 to 1830, during the time that Bradley, Maskelyne, and Pond were the astronomers royal. These planetary observations were deduced, and the observed places were compared with the tabular places, with Lindenau's tables of Mercury, Venus, and Mars, and with Bouvard's tables of Jupiter, Saturn, and Uranus. And thus, while the received theory and its elements were confirmed, the means of testing any improvement which may hereafter be proposed, either in the form of the theoretical results or in the constant elements which they involved, was placed within the reach of the 554 astronomers of all future time. The work appeared in 1845, the expense of the compilations and the publication being defrayed by the British government. Note 49\A. The observations of stars made by Bradley, who preceded Maskelyne at Greenwich, had already been discussed by Bessel, a great German astronomer, and the results published in 1818 with a title that well showed the estimation in which he held those materials. Fundamenta Astronomiae pro anno, 1775. Deducta ex observationibus viri, incomparabilis, James Bradley in Specula Astronomica Grenovicensi, per annos 1750-1762 institutis. The discovery of Neptune. The theory of gravitation was destined to receive a confirmation more striking than any which could arise from any explanation, however perfect, given by the motions of a known planet. Namely, in revealing the existence of an unknown planet, disclosed to astronomers by the attraction which it exerted upon a known one. The story of the discovery of Neptune by the calculations of Mr. Adams and M. Leverrier was partly told in the former edition of this history. I had there stated, volume Roman II, p. 306, that a deviation of observation from the theory occurs at the very extremity of the solar system, and that its existence appears to be beyond doubt. Uranus does not conform to the tables calculated for him on the theory of gravitation. In 1821, Bouvard said in the preface to the tables of this planet, "The formation of these tables offers to us this alternative, that we cannot satisfy modern observations to the requisite degree of precision without making our tables deviate from the ancient observations. But when we have done this, there is still a discordance between the tables and the more modern observations, and this discordance goes on increasing. At present, the tables make the planet come upon the meridian about 8 seconds later than he really does. This discrepancy has turned the thoughts of astronomers to the effects which would result from a planet external to Uranus. It appears that the observed motion would be explained by applying a planet at twice the distance of Uranus from the Sun to exercise a disturbing force, and it is found that the present longitude of this disturbing body must be about 325 degrees. I added, M. Leverrier, Comps Rendus Jan. 1, 1846, and as I am informed by the Astronomer Royal, Mr. Adams, of St. John's College, Cambridge, have both arrived independently at this result. To this addition I added a postscript, dated Nov. 7, 1846, in which I said, "The planet exterior to Uranus, of which the existence was inferred by M. Leverrier and Mr. Adams from the motions of Uranus, volume Roman II, note L, has since been discovered." This confirmation of calculations, founded upon the doctrine of universal gravitation, may be looked upon as the most remarkable event of the kind since the return of Halley's comet in 1757, and in some respects, as a more striking event, 555, even than that, inasmuch as the new planet had never been seen at all, and was discovered by mathematicians entirely by their feeling of its influence, which they perceived through the organ of mathematical calculation. There can be no doubt that to M. Leverrier belongs the glory of having first published a prediction of the place and appearance of the new planet, and of having thus occasioned its discovery by astronomical observers. M. Leverrier's first prediction was published in the Comps Rendus de l'Acad. Des Sciences, for June 1, 1846, not Jan. 1, as erroneously printed in my note. A subsequent paper on the subject was Red Aug. 31. The planet was seen by M. Gala at the Observatory of Berlin on September 23, on which day he had received an express application from M. Leverrier, recommending him to endeavor to recognize the stranger by its having a visible disk. Professor Challis at the Observatory of Cambridge was looking out for the new planet from July 29 and saw it on August 4 and again on August 12, but without recognizing it, in consequence of his plan of not comparing his observations till he had accumulated a greater number of them. On Sept 29, having read for the first time M. Leverrier's second paper, he altered his plan and paid attention to the physical appearance rather than the position of the star. On that very evening, not having then heard of M. Gala's discovery, he singled out the star by its seeming to have a disk. M. Leverrier's mode of discussing the circumstances of Uranus's motion and inferring the new planet from these circumstances is in the highest degree sagacious and masterly. Justice to him cannot require that the contemporaneous, though unpublished, labors of Mr. Adams, of St. John's College, Cambridge, should not also be recorded. Mr. Adams made his first calculations to account for the anomalies in the motion of Uranus, on the hypothesis of a more distant planet, in 1843. At first he had not taken into account the earlier Greenwich observations, but these were supplied to him by the Astronomer Royal in 1844. In September 1845, Mr. Adams communicated to Professor Challis values of the elements of the supposed disturbing body, namely, its mean distance, mean longitude at a given epoch, longitude of perihelion, eccentricity of orbit, and mass. In the next month, he communicated to the Astronomer Royal values of the same elements, somewhat corrected. The note L, volume Roman II, of the present work 2d ed., in which the names of M. Leverrier and Adams are mentioned in conjunction, was in the press in August 1846, a 556 month before the planet was seen. As I have stated in the text, Mr. Adams and M. Leverrier assigned to the unseen planet nearly the same position. They also assigned to it nearly the same mass, namely, 2.5 times the mass of Uranus. And hence, supposing the density to be not greater than that of Uranus, it followed that the visible diameter would be about 3, an apparent magnitude not much smaller than Uranus himself. M. Leverrier has mentioned for the new planet the name Neptunus, and probably, deference to his authority as its discoverer, will obtain general currency for this name. Mr. Airy has given a very complete history of the circumstances attending the discovery of Neptune in the Memoirs of the Astronomical Society, read November 13, 1846. In this, he shows that the probability of some disturbing body beyond Uranus had suggested itself to M. A. Bouvard and Mr. Hussey as early as 1834. Mr. Airy himself then thought that the time was not ripe for making out the nature of any external action on the planets. But Mr. Adams soon afterwards proceeded to work at the problem. As early as 1841, as he himself informs me, he conjectured the existence of a planet exterior to Uranus, and recorded in a memorandum his design of examining its effect. but deferred the calculations till he had completed his preparations for the university examination, which he was to undergo in January 1843, in order to receive the degree of Bachelor of Arts. He was the senior wrangler of that occasion, and soon afterwards proceeded to carry his design into effect, applying to the Astronomer Royal for recorded observations which might aid him in his task. On one of the last days of October, 1845, Mr. Adams went to the observatory at Greenwich, and finding the Astronomer Royal abroad, he left there a paper containing the elements of the extra-Uranian planet. The longitude was in this paper stated as 323½ degrees. It was, as we have seen, in June 1846, that M. Leverrier's memoir appeared, in which he assigned to the disturbing body a longitude of 325 degrees. The coincidence was striking. "I cannot sufficiently express," says Mr. Airy, "the feeling of delight and satisfaction which I received from the memoir of M. Leverrier. This feeling communicated itself to others. Sir John Herschel said in September 1846, at a meeting of the British Association at Southampton, 'We see it, the probable new planet, as Columbus saw America from the shores of Spain. Its movements have been felt, trembling along the far-reaching line of our analysis, with a certainty hardly inferior to that of ocular demonstration.' 557. In truth, at the moment when this was uttered, the new planet had already been seen by Professor Challis. For, as we have said, he had seen it in the early part of August. He had included it in the net which he had cast among the stars for this very purpose, but employing a slow and cautious process, he had deferred for a time that examination of his capture which would have enabled him to detect the object sought. As soon as he received M. Leverrier's paper of August 31 on September 29, he was so much impressed with the sagacity and clearness of the limitations of the field of observation there laid down, that he instantly changed his plan of observation, and noted the planet as an object having a visible disk on the evening of the same day. In this manner, the theory of gravitation predicted and produced the discovery. Thus, to predict unknown facts found afterwards to be true is, as I have said, a confirmation of a theory which in impressiveness and value goes beyond any explanation of known facts. It is a confirmation which has only occurred a few times in the history of science, and in the case only of the most refined and complete theories, such as those of astronomy and optics. The mathematical skill which was requisite in order to arrive at such a discovery may in some measure be judged of by the account which we have had to give of the previous mathematical progress of the theory of gravitation. It there appeared that the lives of many of the most acute, clear-sighted, and laborious of mankind had been employed for generations in solving the problem. Given the planetary bodies to find their mutual perturbations, but here we have the inverse problem given the perturbations to find the planets. Note 50\A. This may be called the inverse problem with reference to the older and more familiar problem, but we may remark that the usual phraseology of the problem of central forces differs from this analogy. In Newton's Principia, the earlier sections, in which the motion is given to find the force, are spoken of as containing the direct problem of central forces. The 8th section of the first book, where the force is given to find the orbit, is spoken of as containing the inverse problem of central forces. The minor planets. The discovery of the minor planets which revolve between the orbits of Mars and Jupiter was not a consequence or confirmation of the Newtonian theory. That theory gives no reason for the distance of 558 the planets from the Sun, nor does any theory yet devised give such reason. But an empirical formula proposed by the astronomer Bode of Berlin gives a law of these distances, Bode's law, which, to make it coherent, requires a planet between Mars and Jupiter. With such an addition, the distance of Mercury, Venus, Earth, Mars, the missing planet, Jupiter, Saturn, and Uranus are nearly as the numbers 4, 7, 10, 16, 28, 52, 100, 196, in which the excesses of each number above the preceding are the series 3, 3, 6, 12, 24, 48, 96. On the strength of this law, the Germans wrote on the long-expected planet and formed themselves into associations for the discovery of it. Not only did this law stimulate the inquiries for the missing planet and thus lead to the discovery of the minor planets, but it had also a share in the discovery of Neptune. According to the law, a planet beyond Uranus may be expected to be at the distance represented by 388. Mr. Adams and M. Leverrier, both of them, began by assuming a distance of nearly this magnitude for the planet which they sought. That is, a distance more than 38 times the Earth's distance. It was found afterwards that the distance of Neptune is only 30 times that of the Earth. Yet the assumption was of essential use in obtaining the result, and Mr. Airy remarks that the history of the discovery shows the importance of using any received theory as far as it will go, even if the theory can claim no higher merit than that of being plausible. Note 51-A, Account of the Discovery of Neptune, and C. Mem. Ast. Soc. Volume Roman 16, p. 414. The discovery of minor planets in a certain region of the interval between Mars and Jupiter has gone on to such an extent that their number makes them assume in a peculiar manner the character of representatives of a missing planet. At first, as I have said in the text, it was supposed that all these portions must pass through or near a common node. This opinion being founded on the very bold doctrine that the portions must at one time have been united in one planet, and must then have separated. At this node, as I have stated, Albers lay in wait for them, as for a hostile army at a defile. Ceres, Pallas, and Juno had been discovered in this way in the period from 1801 to 1804, and Vesta was caught in 1807. For a time the chase for new planets in this region seemed to have exhausted the stock. But after 38 years, to the astonishment of astronomers, they began to be again detected in extraordinary numbers. In 1845, M. Henke of 559, Dreesen discovered a fifth of these planets, which was termed Astrea. In various quarters the chase was resumed with great ardor. In 1840, 7 were found: Hebe, Iris, and Flora. In 1848, Medes. In 1849, Hygeia. In 1850, Parthenope, Victoria, and Egeria. In 1861, Irene and Eunomia. In 1852, Psyche, Thetis, Melpomene, Fortuna, Massilia, Lutetia, Calliope. To these we have now, at the close of 1856, to add 19 others, making up the whole number of these minor planets at present known to 42. As their enumeration will show, the ancient practice has been continued of giving to the planets mythological names. And for a time, till the numbers became too great, each of the minor planets was designated in astronomical books by some symbol appropriate to the character of the mythological person. As from ancient times, Mars has been denoted by a mark indicating a spear, and Venus by one representing a looking-glass. Thus, when a minor planet was discovered at London in 1851, the year in which the peace of the world was, in a manner, celebrated by the great exhibition of the products of all nations, held at that metropolis, the name Irene was given to the new star, as a memorial of the auspicious time of its discovery. And it was agreed, for a while, that its symbol should be a dove with an olive branch. But the vast multitude of the minor planets, as discovery went on, made any mode of designation, except a numerical one, practically inconvenient. They are now denoted by a small circle enclosing a figure in the order of their discovery. Thus, Ceres is 1, Irene is 14, and Isis is 42. The rapidity with which these discoveries were made was owing in part to the formation of star maps, in which all known fixed stars being represented, the existence of a new and movable star might be recognized by comparison of the sky with the map. These maps were first constructed by astronomers of different countries at the suggestion of the Academy of Berlin. But they have since been greatly extended and now include much smaller stars than were originally laid down. I will mention the number of planets discovered in each year. After the start was once made, by Henke's discovery of Astrea in 1845, the same astronomer discovered Hebe in 1847, and in the same year Mr. Hind of London discovered 2 others, Iris and Flora. The years 1848 and 1849 each supplied 1. The year 1850, 3, 1851, 2. 1852 was marked by the extraordinary discovery of 8 new members of the planetary system. The year 1853 supplied 4, 1854, 6, 1855, 4, and 1856 has already given us 5. 560. These discoveries have been distributed among the observatories of Europe. The bright sky of Naples has revealed 7 new planets to the telescope of Cyner Gasparis. Marseille has given us 1, Germany 4, discovered by M. Luther at Bilk. Paris has furnished 7. And Mr. Hind, in Mr. Bishop's private observatory in London, notwithstanding our turbid skies, has discovered no less than 10 planets. And there also Mr. Marth discovered 29 Amphitrite. Mr. Graham, at the private observatory of Mr. Cooper, in Ireland, discovered 9 Medes. America has supplied its planet, namely 31 Euphrosyne, discovered by Mr. Ferguson at Washington, and the most recent of these discoveries is that by Mr. Pogson, of Oxford, who has found the 42nd of these minor planets, which has been named Isis. Note 52\A. I take this list from a memoir of M. Bruns, Berlin, 1856. I may add that it appears to follow from the best calculations that the total mass of all these bodies is very small. Herschel reckoned the diameters of Ceres at 35 and of Pallas at 26 miles. It has since been calculated that some of them are smaller still, Victoria having a diameter of 9 miles, Lutetia of 8, and Atalanta of little more than 4. It follows from this that the whole mass would probably be less than the 6th part of our moon. Hence their perturbing effects on each other or on other planets are null. But they are not the less disturbed by the action of the other planets, and especially of Jupiter. Anomalies in the action of gravitation. The complete and exact manner in which the doctrine of gravitation explains the motions of the comets as well as of the planets has made astronomers very bold in proposing hypotheses to account for any deviations from the motion which the theory requires. Thus, Encke's comet is found to have its motion accelerated by about 1/8 of a day in every revolution. This result was conceived to be established by former observations and is confirmed by the facts of the appearance of 1852. The hypothesis which is proposed in order to explain this result is that the comet moves in a resisting medium, which makes it fall inwards from its path towards the Sun, and thus, by narrowing its orbit, diminishes its periodic time. On the other hand, M. Leverrier has found that Mercury's mean motion has gone on diminishing. 561, as if the planet were, in the progress of his revolutions, receding further from the Sun. This is explained if we suppose that there is, in the region of Mercury, a resisting medium which moves round the Sun in the same direction as the planets move. Evidence of a kind of nebulous disk surrounding the Sun and extending beyond the orbits of Mercury and Venus appears to be afforded us by the phenomenon called the zodiacal light. And as the Sun itself rotates on its axis, it is most probable that this kind of atmosphere rotates also. On the other hand, M. Leverrier conceives that the comets which now revolve within the ordinary planetary limits have not always done so, but have been caught and detained by the planets among which they move. In this way, the action of Jupiter has brought the comets of Phae and Vico into their present limited orbits, as it drew the comet of Lexell out of its known orbit, when the comet passed over the planet in 1779, since which time it has not been seen. Note 55\A, M. Leverrier, Annales de l'Obs, de Paris, Volume IP, 89. Among the examples of the boldness with which astronomers assume the doctrine of gravitation even beyond the limits of the solar system to be so entirely established, that hypotheses may and must be assumed to explain any apparent irregularity of motion, we may reckon the mode of accounting for certain supposed irregularities in the proper motion of Sirius, which has been proposed by Bessel, and which M. Peters thinks is proved to be true by his recent researches. Astor. Knack. Roman 31. p. 219 and Roman 32. p. 1. The hypothesis is that Sirius has a companion star, dark and therefore invisible to us, and that the two, revolving round their common center as the system moves on, the motion of Sirius is seen to be sometimes quicker and sometimes slower. The Earth's density. Cavendish's experiment, as it is commonly called the measure of the attractions of manageable masses by the torsion balance, in order to determine the density of the Earth has been repeated recently by Professor Reich at Freiburg, and by Mr. Bailey in England, with great attention to the means of attaining accuracy. Professor Reich's result for the density of the Earth is 544. Mr. Bailey's is 592. Cavendish's result was 548. According to recent revisions, it is 552. 562. Note 56\A. The calculation has been revised by M. Edward Schmidt, Humboldt's Cosmos, Roman 2, p. 425. But the statical effect of the attraction of manageable masses, or even of mountains, is very small. The effect of a small change in gravity may be accumulated by being constantly repeated in the oscillations of a pendulum, and thus may become perceptible. Mr. Airy attempted to determine the density of the Earth by a method depending on this view. A pendulum oscillating at the surface was to be compared with an equal pendulum at a great depth below the surface. The difference of their rates would disclose the different force of gravity at the two positions, and hence the density of the Earth. In 1826 and 1828, Mr. Airy attempted this experiment at the copper mine of Dalcoath in Cornwall, but failed from various causes. But in 1854, he resumed it at the Harton coal mine in Durham, the depth of which is 1260 feet. Having in this new trial the advantage of transmitting the time from one station to the other by the instantaneous effect of galvanism, instead of by portable watches. The result was a density of 656, which is much larger than the preceding results, but, as Mr. Airy holds, is entitled to compete with the others on at least equal terms. Tides. I should be wanting in the expression of gratitude to those who have practically assisted me in researches on the tides, if I did not mention the grand series of tide observations made on the coast of Europe and America in June 1835 through the authority of the Board of Admiralty, and the interposition of the late Duke of Wellington, at that time Foreign Secretary. Tide observations were made for a fortnight at all the Coast Guard stations of Great Britain and Ireland in June 1834, and these were repeated in June 1835 with corresponding observations on all the coasts of Europe, from the North Cape of Norway to the Straits of Gibraltar, and from the mouth of the St. Lawrence to the mouth of the Mississippi. The results of these observations, which were very complete so far as the coast tides were concerned, were given in the Philosophical Transactions for 1836. Additional accuracy respecting the tides of the North American coast may be expected from the survey now going on under the direction of Superintendent A. Bach. The tides of the English Channel have been further investigated, and the phenomena presented under a new point of view by Admiral Beechey. 563. The tides of the coast of Ireland have been examined with great care by Mr. Airy. Numerous and careful observations were made with a view, in the first instance, of determining what was to be regarded as the level of the sea. But the results were discussed so as to bring into view the laws and progress, on the Irish coast, of the various inequalities of the tides mentioned in Chapter Roman 4. Sect. 9 of this book. I may notice as one of the curious results of the tide observations of 1836, that it appeared to me, from a comparison of the observations, that there must be a point in the German Ocean, about midway between Lowestoft on the English coast and the Brill on the Dutch coast, where the tide would vanish. And this was ascertained to be the case by observation, the observations being made by Captain Hewitt, then employed in a survey of that sea. Codidal lines supply, as I conceive, a good and simple method of representing the progress and connection of literal tides. But to draw codidal lines across oceans is a very precarious mode of representing the facts, except we had much more knowledge on the subject than we at present possess. In the Phil. Trans for 1848, I have resumed the subject of the tides of the Pacific, and I have there expressed my opinion that while the literal tides are produced by progressive waves, the oceanic tides are more of the nature of stationary undulations. But many points of this kind might be decided, and our knowledge on this subject might be brought to a condition of completeness, if a ship or ships were sent expressly to follow the phenomena of the tides from point to point, as the observations themselves might suggest a course. Till this is done, our knowledge cannot be completed. Detached and casual observations, made aliud agendo, can never carry us much beyond the point where we at present are. Double stars. Sir John Herschel's work, referred to in the History 2d ed. As then about to appear, was published in 1847. In this work, besides a vast amount of valuable observations and reasonings on other subjects, 564, as nebulae, the magnitude of stars, and the like, the orbits of several double stars are computed by the aid of the new observations. But Sir John Herschel's conviction on the point in question, the operation of the Newtonian law of gravitation in the region of the stars, is expressed perhaps more clearly in another work which he published in 1849. He there speaks of double stars, and especially of Gamma Virginis, the one which has been most assiduously watched and has offered phenomena of the greatest interest. He then finds that the two components of this star revolve round each other in a period of 182 years, and says that the elements of the calculated orbit represent the whole series of recorded observations, comprising an angular movement of nearly 9/10 of a complete circuit, both in angle and distance, with a degree of exactness fully equal to that of observation itself. No doubt can therefore, he adds, remain as to the ** prevalence in this remote system of the Newtonian law of gravitation. Note 57 \A. Results of astronomical observations made during the years 1834, 5, 6, 7, 8, at the Cape of Good Hope, being the completion of a telescopic survey of the whole surface of the visible heavens commenced in 1825. Yet M. Yvon de Villarceau has endeavored to show that this conclusion, however probable, is not yet proved. He holds, even for the double stars, which have been most observed, the observations are only equivalent to 7 or 8 really distinct data, and that 7 data are not sufficient to determine that an ellipse is described according to the Newtonian law. Without going into the details of this reasoning, I may remark that the more rapid relative angular motion of the components of a double star when they are more near each other proves, as is allowed on all hands, that they revolve under the influence of a mutual attractive force, obeying the Keplerian law of areas. But that, whether this force follows the law of the inverse square or some other law, can hardly have been rigorously proved as yet, we may easily conceive, when we recollect the manner in which that law was proved for the solar system. It was by means of an error of 8 minutes, observed by Tycho, that Kepler was enabled, as he justly boasted, to reform the scheme of the solar system to show, that is, that the planetary orbits are ellipses with the sun in the focus. Now, the observations of double stars cannot pretend to such accuracy as this, and therefore the Keplerian theorem cannot, as yet, have been fully demonstrated from those observations. But when we know, 565, that double stars are held together by a central force, to prove that this force follows a different law from the only law which has hitherto been found to obtain in the universe, and which obtains between all the known masses of the universe, would require very clear and distinct evidence, of which astronomers have as yet seen no trace. Chapter 6. Sect 1 Instruments 2, Clocks. In page 473, I have described the manner in which astronomers are able to observe the transit of a star and other astronomical phenomena to the exactness of 1/10 of a second of time. The mode of observation there described implies that the observer at the moment of observation compares the impressions of the eye and of the ear. Now it is found that the habit which the observer must form of doing this operates differently in different observers, so that one observer notes the same fact as happening a fraction of a second earlier or later than another observer does, and this in every case. Thus, using the term equation, as we use it in astronomy, to express a correction by which we get regularity from irregularity, there is a personal equation belonging to this mode of observation, showing that it is liable to error. Can this error be got rid of? It is at any rate much diminished by a method of observation recently introduced into observatories and first practiced in America. The essential feature of this mode of observation consists in combining the impression of sight with that of touch, instead of with that of hearing. The observer at the moment of observation presses with his finger so as to make a mark on a machine which by its motion measures time with great accuracy and on a large scale, and thus small intervals of time are made visible. A universal, though not a necessary, part of this machinery, as hitherto adopted, is that a galvanic circuit has been employed in conveying the impression from the finger to the part where time is measured and marked. The facility with which galvanic wires can 566 thus lead the impression by any path to any distance, and increase its force in any degree, has led to this combination, and almost identification, of observation by touch with its record by galvanism. The method having been first used by Mr. Bond at Cambridge, in North America, has been adopted elsewhere, and especially at Greenwich, where it is used for all the instruments. And consequently, a collection of galvanic batteries is thus as necessary a part of the apparatus of the establishment as its graduated circles and arcs. End of Volume I. History of the Inductive Sciences. Volume II. History of the Inductive Sciences from the Earliest to the Present Time. By William Whewell, D.D., Master of Trinity College, Cambridge, the third edition with additions, in 2 volumes. Volume II. New York D. Appleton and Company, 549 and 551 Broadway, 1875. Contents of the second volume. The Secondary Mechanical Sciences. Book 8. History of Acoustics. Page Introduction. Chapter 1, Prelude to the Solution of Problems in Acoustics. Chapter 2, Problem of the Vibrations of Strings. Chapter 3, Problem of the Propagation of Sound. Chapter 4, Problem of Different Sounds of the Same String. Chapter 5, Problem of the Sounds of Pipes. Chapter 6, Problem of Different Modes of Vibration of Bodies in General. Book 9. History of Optics, Formal and Physical. Introduction, 8. Formal Optics. Chapter 1, Primary Induction of Optics Rays of Light and Laws of Reflection. Chapter 2, Discovery of the Law of Refraction. Chapter 3, Discovery of the Law of Dispersion by Refraction. Chapter 4, Discovery of Achromatism. Chapter 5, Discovery of the Laws of Double Refraction. Chapter 6, Discovery of the Laws of Polarization. Chapter 7, Discovery of the Laws of the Colors of Thin Plates, 76. Chapter 8, Attempts to discover the laws of other phenomena, 78. Chapter 9, Discovery of the Laws of Phenomena of Dipolarized Light. Physical Optics. Chapter 10, Prelude to the Epoch of Young and Fresnel. Chapter 11, Epoch of Young and Fresnel. Sect 1, Introduction. Sect 2, Explanation of the periodical colors of thin plates and shadows by the undulatory theory. Sect 3, Explanation of double refraction by the undulatory theory. Sect 4, Explanation of polarization by the undulatory theory. 100. Sect 5, Explanation of dipolarization by the undulatory theory. 9. Chapter 12, Sequel to the Epoch of Young and Fresnel, Reception of the undulatory theory. Chapter 13, Confirmation and Extension of the undulatory theory. 1. Double refraction of compressed glass. 2. Circular polarization. 3. Elliptical polarization in quartz. 4. Differential equations of elliptical polarization. 5. Elliptical polarization of metals. 6. Newton's rings by polarized light. 7. Conical refraction. 8. Fringes of shadows. 9. Objections to the theory. 10. Dispersion on the undulatory theory. 11. Conclusion. Book 10. History of Thermotics and Atmology. Introduction. Thermotics proper. Chapter 1, The Doctrines of Conduction and Radiation. Sect 1, Introduction of the Doctrine of Conduction. Sect 2, Radiation. Sect 3, Verification of the Doctrines of Conduction and Radiation. Sect 4, The Geological and Cosmological Application of Thermotics, Effect of Solar Heat on the Earth, Climate, Temperature of the Interior of the Earth, Heat of the Planetary Spaces. Sect 5, Correction of Newton's Law of Cooling. Sect 6, Other Laws of Phenomena with Respect to Radiation. Sect 7, Fourier's Theory of Radiant Heat. Sect 8, Discovery of the Polarization of Heat. 10. Chapter 2, The Laws of Changes Occasioned by Heat. Sect 1, Expansion by Heat, the Law of Dalton and Gay-Lussac for gases. Sect 2, Specific Heat Change of Consistence. Sect 3, The Doctrine of Latent Heat. Atmology. Chapter 3, The Relation of Vapor and Air. Sect 1, The Boylean Law of the Air's Elasticity. Sect 2, Prelude to Dalton's Doctrine of Evaporation. Sect 3, Dalton's Doctrine of Evaporation. Sect 4, Determination of the Laws of the Elastic Force of Steam. Sect 5, Consequences of the Doctrine of Evaporation, Explanation of Rain, Dew, and Clouds. Chapter 4, Physical Theories of Heat. Thermotical Theories, Atmological Theories, Conclusion. The Mechanico-Chemical Sciences. Book 11. History of Electricity. Introduction. Chapter 1, Discovery of Laws of Electric Phenomena. Chapter 2, The Progress of Electrical Theory. Question of one or two fluids. Question of the material reality of the electric fluid. 11. Book 12. History of Magnetism. Chapter 1, Discovery of Laws of Magnetic Phenomena. Chapter 2, Progress of Magnetic Theory. Theory of Magnetic Action, Theory of Terrestrial Magnetism. Conclusion. Book 13. History of Galvanism or Voltaic Electricity. Chapter 1, Discovery of Voltaic Electricity. Chapter 2, Reception and Confirmation of the Discovery of Voltaic Electricity. Chapter 3, Discovery of the Laws of the Mutual Attraction and Repulsion of Voltaic Currents. Ampere. Chapter 4, Discovery of Electromagnetic Action Ørsted. Chapter 5, Discovery of the Laws of Electromagnetic Action. Chapter 6, Theory of Electrodynamical Action. Ampere's Theory, Reception of Ampere's Theory. Chapter 7, Consequences of the Electrodynamic Theory. Discovery of Diamagnetism. 12. Chapter 8, Discovery of the Laws of Magnetoelectric Induction. Faraday. Chapter 9, Transition to Chemical Science. The Analytical Science. Book 14. History of Chemistry. Chapter 1, Improvement of the Notion of Chemical Analysis and Recognition of it as the Spagyric Art. Chapter 2, Doctrine of Acid and Alkali, Sylvius. Chapter 3, Doctrine of Elective Attractions, Geoffroy, Bergman. Chapter 4, Doctrine of Acidification and Combustion, Phlogistic Theory. Publication of the theory by Becker and Stahl, Reception and Application of the theory. Chapter 5, Chemistry of Gases, Black, Cavendish. Chapter 6, Epoch of the Theory of Oxygen, Lavoisier. Sect. 1, Prelude to the Theory, its publication. Sect. 2, Reception and Confirmation of the Theory of Oxygen. Sect. 3, Nomenclature of the Oxygen Theory. Chapter 7, Application and Correction of the Oxygen Theory. 13. Chapter 8, Theory of Definite, Reciprocal, and Multiple Proportions. Sect. 1, Prelude to the Atomic Theory and its publication by Dalton. Sect. 2, Reception and Confirmation of the Atomic Theory. Sect. 3, The Theory of Volumes, Gay-Lussac. Chapter 9, Epoch of Davy and Faraday. Sect. 1, Promulgation of the Electrochemical Theory by Davy. 291. Sect. 2, Establishment of the Electrochemical Theory by Faraday. Sect. 3, Consequences of Faraday's discoveries. Sect. 4, Reception of the Electrochemical Theory. Chapter 10, Transition from the Chemical to the Classificatory Sciences. The Analytico-Classificatory Science. Book 15. History of Mineralogy. Introduction. Sect. 1 of the Classificatory Sciences. Sect. 2 of Mineralogy as the Analytico-Classificatory Science. Crystallography. Chapter 1, Prelude to the Epoch of Delisle and Hauy. Chapter 2, Epoch of Ramée, Delisle and Hauy. Establishment of the fixity of crystalline angles and the simplicity of the laws of derivation. Chapter 3, Reception and Corrections of the Hauyan crystallography. 14. Chapter 4, Establishment of the distinction of systems of crystallization, Weiss and Mohs. Chapter 5, Reception and Confirmation of the distinction of systems of crystallization. Diffusion of the distinction of systems, confirmation of the distinction of systems by the optical properties of minerals. Brewster. Chapter 6, Correction of the law of the same angle for the same substance. Discovery of isomorphism, Mitscherlich, dimorphism. Chapter 7, Attempts to establish the fixity of other physical properties, Werner. Systematic mineralogy. Chapter 8, Attempts at the classification of minerals. Sect. 1, Proper object of classification. Sect. 2, Mixed systems of classification. Chapter 9, Attempts at the reform of mineralogical systems, separation of the chemical and natural history methods. Sect. 1, Natural history system of Mohs. Sect. 2, Chemical system of Berzelius and others. Sect. 3, Failure of the attempts at systematic reform. Sect. 4, Return to mixed systems with improvements. Classificatory Sciences. Book 16. History of Systematic Botany and zoology. Introduction 15. Chapter 1 Imaginary Knowledge of Plants. Chapter 2 Unsystematic Knowledge of Plants. Chapter 3 Formation of a System of Arrangement of Plants. Sect 1 Prelude to the Epoch of Caesalpinnis. Sect 2 Epoch of Caesalpinnis, Formation of a System of Arrangement. Sect 3 Stationary Interval. Sect 4 Sequel to the Epoch of Caesalpinnis, Further Formation and Adoption of Systematic Arrangement. Chapter 4 The Reform of Linnaeus. Sect 1 Introduction of the Reform. Sect 2 Linnaean Reform of Botanical Terminology. Sect 3 Nomenclature. Sect 4 Linnaeus's Artificial Systems. Sect 5 Linnaeus's Views on a Natural Method. Sect 6 Reception and Diffusion of the Linnaean Reform. Chapter 5 Progress towards a Natural System of Botany. Chapter 6 The Progress of Systematic Zoology. Chapter 7 The Progress of Ichthyology. Period of unsystematic knowledge, period of erudition, period of accumulation of materials, exotic collections, epoch of the fixation of characters, Ray and Willoughby, improvement of the system, artidi, separation of the artificial and natural methods in ichthyology. 426. Organical Sciences. Book 17. History of Physiology and Comparative Anatomy. Introduction 16. Chapter 1 Discovery of the Organs of Voluntary Motion. Sect 1 Knowledge of Galen and his predecessors. Sect 2 Recognition of Final Causes in Physiology. Galen. Chapter 2 Discovery of the Circulation of the Blood. Sect 1 Prelude to the Discovery. Sect 2 The Discovery of the Circulation made by Harvey. Sect 3 Reception of the Discovery. Sect 4 Bearing of the Discovery on the Progress of Physiology. Chapter 3 Discovery of the Motion of the Chyle and Consequent Speculations. Sect 1 The Discovery of the Motion of the Chyle. Sect 2 The Consequent Speculations, Hypotheses of Digestion. 453. Chapter 4 Examination of the Process of Reproduction in Animals and Plants and Consequent Speculations. Sect 1 The Examination of the Process of Reproduction in Animals. Sect 2 In Vegetables. Sect 3 The Consequent Speculations, Hypotheses of Generation. Chapter 5 Examination of the Nervous System and Consequent Speculations. Sect 1 The Examination of the Nervous System. Sect 2 The Consequent Speculations, Hypotheses respecting life, sensation, and volition. Chapter 6 Introduction of the Principle of Developed and Metamorphosed Symmetry. Sect 1 Vegetable Morphology. Goth, de Candolle. Sect 2 Application of Vegetable Morphology. Chapter 7 Progress of Animal Morphology. Sect 1 Rise of Comparative Anatomy. Sect 2 Distinction of the General Types of the Forms of Animals. Cuvier. Sect 3 Attempts to establish the identity of the types of animal forms. 17. Chapter 8 The Doctrine of Final Causes in Physiology. Sect 1 Assertion of the Principle of Unity of Plan. Sect 2 Estimate of the Doctrine of Unity of Plan. Sect 3 Establishment and Application of the Principle of the Conditions of Existence of Animals. Cuvier. The Paleontological Sciences. Book 18. History of Geology. Introduction. Descriptive Geology. Chapter 1 Prelude to Systematic Descriptive Geology. Sect 1 Ancient Notices of Geological Facts. Sect 2 Early Descriptions and Collections of Fossils. Sect 3 First Construction of Geological Maps. Chapter 2 Formation of Systematic Descriptive Geology. Sect 1 Discovery of the Order and Stratification of the Materials of the Earth. Sect 2 Systematic Form given to Descriptive Geology. Werner. Sect 3 Application of Organic Remains as a Geological Character. Smith. Sect 4 Advances in Paleontology. Cuvier. Sect 5 Intellectual Characters of the Founders of Systematic Descriptive Geology. Chapter 3 Sequel to the Formation of Systematic Descriptive Geology. Sect 1 Reception and Diffusion of Systematic Geology. Sect 2 Application of Systematic Geology, Geological Surveys and Maps. Sect 3 Geological Nomenclature. Sect 4 Geological synonymy or determination of geological equivalence. 18. Chapter 4, attempts to discover general laws in geology. Sect 1, general geological phenomena. Sect 2, transition to geological dynamics. Geological dynamics. Chapter 5, inorganic geological dynamics. Sect 1, necessity and object of a science of geological dynamics. Sect 2, aqueous causes of change. Sect 3, igneous causes of change motions of the Earth's surface. Sect 4, the doctrine of central heat. Sect 5, problems respecting elevations and crystalline forces. Sect 6, theories of changes of climate. Chapter 6, progress of the geological dynamics of organized beings. Sect 1, objects of this science. Sect 2, geography of plants and animals. Sect 3, questions of the transmutation of species. Sect 4, hypothesis of progressive tendencies. Sect 5, question of creation as related to science. Sect 6, the hypothesis of the regular creation and extinction of species. Creation of species. Extinction of species. Sect 7, the embedding of organic remains. Physical geology. Chapter 7, progress of physical geology. Sect 1, object and distinctions of physical geology. Sect 2, of fanciful geological opinions. Sect 3, of premature geological theories. Chapter 8, the two antagonist doctrines of geology. Sect 1, of the doctrine of geological catastrophes. Sect 2, uniformity. 19. Additions to the third edition. Book 8, acoustics. Sound. The velocity of sound in water. Book 9, optics. Photography, fluorescence. Undulatory theory. Direction of the transverse vibrations in polarization. Final disproof of the emission theory. Book 10, thermotics, atmology. The relation of vapor and air. Force of steam, temperature of the atmosphere. Theories of heat. The dynamical theory of heat. Book 11, electricity. General remarks. Dr. Faraday's views of statical electrical induction. Book 12, magnetism. Recent progress of terrestrial magnetism, correction of ships' compasses. 20. Book 13, voltaic electricity. Magnetoelectric induction. Diamagnetic polarity, magneto-optic effects and magnocrystallic polarity, magnetoelectric machines. Applications of electrodynamic discoveries. Book 14, chemistry. The electrochemical theory. The number of elementary substances. Book 15, mineralogy. Crystallography, optical properties of minerals, classification of minerals. Book 16, classificatory sciences. Recent views of botany, zoology. Book 17, physiological and comparative anatomy. Vegetable morphology, animal morphology, final causes. Book 18, geology. 21, Book 8, the secondary mechanical sciences. History of acoustics. Go, demand of mighty nature, if 'twas ever meant that we should pry far off and be unraised, that we should pour and dwindle as we pour, viewing all objects unremittingly in disconnection dead and spiritless, and still dividing and dividing still, break down all grandeur, still unsatisfied with the perverse attempt, while littleness may yet become more little, waging thus an impious warfare, gainst the very life of our own souls. Wordsworth, Excursion. Letter 1 F10 sigma sigma epsilon mu eta delta. Letter 1 F72. Letter 1 F20 epsilon rho iota eta nu. Letter 1 F00. Psi letter 1 FD6 delta alpha delta iota epsilon. Letter 1 FE4. Letter 1 FE5 omicron iota zeta eta sigma epsilon pi epsilon delta iota lambda. Letter 1 FF3 epsilon. Letter 1 F30 sigma delta omicron mu. Letter 1 F01 rho mu omicron nu eta sigma pi alpha mu eta tau omicron rho omicron sigma. Letter 1 F4 on pi omicron theta iota nu epsilon mu phi eta. Letter 1 F34 kappa epsilon lambda omicron nu omicron. Letter 1 F36 kappa omicron nu. Letter 1 F10 nu alpha iota epsilon tau epsilon pi. Letter 1 FF3 tau epsilon tau rho alpha zeta epsilon gamma iota kappa omicron sigma mu omicron epsilon alpha. Letter 1 F50 tau omicron pi alpha gamma. Letter 1 FC6 non nus. Dionysiac. Roman 41, 275. Along the ski arch the goddess trode, and sought Harmonia's august abode, the universal plan, the mystic four, defines the figure of the palace floor. Solid and square, the ancient fabric stands, raised by the labors of unnumbered hands. 23. Book 8. Introduction. The secondary mechanical sciences. In the sciences of mechanics and physical astronomy, motion and force are the direct and primary objects of our attention. But there is another class of sciences in which we endeavor to reduce phenomena, not evidently mechanical, to a known dependence upon mechanical properties and laws. In the cases to which I refer, the facts do not present themselves to the senses as modifications of position and motion, but as secondary qualities, which are found to be in some way derived from those primary attributes. Also, in these cases, the phenomena are reduced to their mechanical laws and causes in a secondary manner. Namely, by treating them as the operation of a medium interposed between the object and the organ of sense. These, then, we may call secondary mechanical sciences. The sciences of this kind which require our notice are those which treat of the sensible qualities, sound, light, and heat, that is, acoustics, optics, and thermotics. It will be recollected that our object is not by any means to give a full statement of all the additions which have been successively made to our knowledge on the subjects under review, or a complete list of the persons by whom such additions have been made, but to present a view of the progress of each of those branches of knowledge as a theoretical science, to point out the epochs of the discovery of those general principles which reduce many facts to one theory, and to note all that is most characteristic and instructive in the circumstances and persons which bear upon such epochs. A history of any science, written with such objects, will not need to be long, but it will fail in its purpose altogether if it do not distinctly exhibit some well-marked and prominent features. 24. We begin our account of the secondary mechanical sciences with acoustics, because the progress towards right theoretical views was, in fact, made much earlier in the science of sound than in those of light and of heat, and also because a clear comprehension of the theory to which we are led in this case is the best preparation for the difficulties, by no means inconsiderable, of the reasonings of theorists on the other subjects. Chapter 1. Prelude to the solution of problems in acoustics. In some measure, the true theory of sound was guessed by very early speculators on the subject, though undoubtedly conceived in a very vague and wavering manner. That sound is caused by some motion of the sounding body, and conveyed by some motion of the air to the ear, is an opinion which we trace to the earliest times of physical philosophy. We may take Aristotle as the best expounder of this stage of opinion. In his treatise on sound and hearing, he says, sound takes place when bodies strike the air, not by the air having a form impressed upon it, sigma chi eta mu alpha tau o to zeta omicron mu epsilon nu omicron u, as some think, but by its being moved in a corresponding manner. Probably he means in a manner corresponding to the impulse, the air being contracted and expanded and overtaken, and again struck by the impulses of the breath and of the strings. For when the breath falls upon and strikes the air which is next it, the air is carried forwards with an impetus, and that which is contiguous to the first is carried onwards, so that the same voice spreads every way as far as the motion of the air takes place. As is the case with all such specimens of ancient physics, different persons would find in such a statement very different measures of truth and distinctness. The admirers of antiquity might easily, by pressing the language closely, and using the light of modern discovery, detect in this passage an exact account of the production and propagation of sound, while others might maintain that in Aristotle's own mind there were only vague notions and verbal generalizations. This 25 latter opinion is very emphatically expressed by Bacon. The collision or thrusting of air, which they will have to be the cause of sound, neither denotes the form nor the latent process of sound, but is a term of ignorance and of superficial contemplation. Nor can it be justly denied that an exact and distinct apprehension of the kind of motion of the air by which sound is diffused was beyond the reach of the ancient philosophers and made its way into the world long afterwards. It was by no means easy to reconcile the nature of such motion with obvious phenomena, for the process is not evident as motion, since, as Bacon also observes, it does not visibly agitate the flame of a candle, or a feather, or any light floating substance, by which the slightest motions of the air are betrayed. Still, the persuasion that sound is some motion of the air continued to keep hold of men's minds and acquired additional distinctness. The illustration employed by Vitruvius in the following passage is even now one of the best we can offer. Voice is breath, flowing and made sensible to the hearing by striking the air. It moves in infinite circumferences of circles, as when, by throwing a stone into still water, you produce innumerable circles of waves, increasing from the center and spreading outwards, till the boundary of the space, or some obstacle, prevents their outlines from going further. In the same manner, the voice makes its motion in circles. But in water, the circle moves breadthways upon a level plane. The voice proceeds in breadth and also successively ascends in height. Both the comparison and the notice of the difference of the two cases prove the architect to have had very clear notions on the subject, which he further shows by comparing the resonance of the walls of a building to the disturbance of the outline of the waves of water when they meet with a boundary and are thrown back. Therefore, as in the outlines of waves in water, so in the voice, if no obstacle interrupt the foremost, it does not disturb the second and the following ones, so that all come to the ears of persons, whether high up or low down, without resonance. But when they strike against obstacles, the foremost, being thrown back, disturb the lines of those which follow. Similar analogies were employed by the ancients in order to explain the occurrence of echoes. Aristotle says, "An echo takes place when the air, being as one body in consequence of the vessel which bounds it, and being prevented from being thrust forwards, is reflected 26 back like a ball." Nothing material was added to such views till modern times. Thus the first conjectures of those who philosophized concerning sound led them to an opinion concerning its causes and laws, which only required to be distinctly understood, and traced to mechanical principles, in order to form a genuine science of acoustics. It was, no doubt, a work which required a long time and sagacious reasoners to supply what was thus wanting. But still, in consequence of this peculiar circumstance, in the early condition of the prevalent doctrine concerning sound, the history of acoustics assumes a peculiar form. Instead of containing, like the history of astronomy or of optics, a series of generalizations, each including and rising above preceding generalizations. In this case, the highest generalization is in view from the first, and the object of the philosopher is to determine its precise meaning and circumstances in each example. Instead of having a series of inductive truths successively dawning on men's minds, we have a series of explanations in which certain experimental facts and laws are reconciled as to their mechanical principles and their measures with the general doctrine already in our possession. Instead of having to travel gradually towards a great discovery, like universal gravitation or luminiferous undulations, we take our stand upon acknowledged truths, the production and propagation of sound by the motion of bodies and of air, and we connect these with other truths, the laws of motion and the known properties of bodies, as, for instance, their elasticity. Instead of epochs of discovery, we have solutions of problems, and to these we must now proceed. We must, however, in the first place, notice that these problems include other subjects than the mere production and propagation of sound generally. For such questions as these obviously occur: what are the laws and cause of the differences of sounds, of acute and grave, loud and low, continued and instantaneous, and, again, of the differences of articulate sounds, and of the quality of different voices and different instruments? The first of these questions, in particular, the real nature of the difference of acute and grave sounds, could not help attracting attention, since the difference of notes in this respect was the foundation of one of the most remarkable mathematical sciences of antiquity. Accordingly, we find attempts to explain this difference in the ancient writers on music. In Ptolemy's Harmonics, the third chapter of the first book is entitled, "How the 27 Acuteness and Graveness of Notes is Produced." And in this, after noting generally the difference of sounds and the causes of difference, which he states to be the force of the striking body, the physical constitution of the body struck, and other causes, he comes to the conclusion that the things which produce acuteness in sounds are a greater density and a smaller size. The things which produce graveness are a greater rarity and a bulkier form. He afterwards explains this so as to include a considerable portion of truth. Thus he says that in strings and in pipes, other things remaining the same, those which are stopped at the smaller distance from the bridge give the most acute note, and in pipes, those notes which come through holes nearest to the mouth hole are most acute. He even attempts a further generalization and says that the greater acuteness arises, in fact, from the body being more tense, and that thus, hardness may counteract the effect of greater density, as we see that brass produces a more acute sound than lead. But this author's notions of tension, since they were applied so generally as to include both the tension of a string and the tension of a piece of solid brass, must necessarily have been very vague. And he seems to have been destitute of any knowledge of the precise nature of the motion or impulse by which sound is produced, and of course, still more ignorant of the mechanical principles by which these motions are explained. The notion of vibrations of the parts of sounding bodies does not appear to have been dwelt upon as an essential circumstance, though in some cases, as in sounding strings, the fact is very obvious. And the notion of vibrations of the air does not at all appear in ancient writers, except so far as it may be conceived to be implied in the comparison of aerial and watery waves, which we have quoted from Vitruvius. It is, however, very unlikely that, even in the case of water, the motions of the particles were distinctly conceived, for such conception is far from obvious. The attempts to apprehend distinctly, and to explain mechanically, the phenomena of sound gave rise to a series of problems, of which we must now give a brief history. The questions which more peculiarly constitute the science of acoustics are the questions concerning those motions or affections of the air by which it is the medium of hearing. But the motions of sounding bodies have both so much connection with those of the medium and so much resemblance to them that we shall include in our survey researches on that subject also. 28. Chapter 2. Problem of the vibrations of strings. That the continuation of sound depends on a continued minute and rapid motion, a shaking or trembling of the parts of the sounding body, was soon seen. Thus Bacon says, the duration of the sound of a bell or a string when struck, which appears to be prolonged and gradually extinguished, does not proceed from the first percussion, but the trepidation of the body struck perpetually generates a new sound. For if that trepidation be prevented, and the bell or string be stopped, the sound soon dies. As in spinets, as soon as the spine is let fall so as to touch the string, the sound ceases. In the case of a stretched string, it is not difficult to perceive that the motion is a motion back and forwards across the straight line which the string occupies when at rest. The further examination of the quantitative circumstances of this oscillatory motion was an obvious problem, and especially after oscillations, though of another kind, those of a pendulous body, had attracted attention, as they had done in the school of Galileo. Mersenne, one of the promulgators of Galileo's philosophy in France, is the first author in whom I find an examination of the details of this case. Harmonicorum Liber, Paris, 1636. He asserts that the differences and concords of acute and grave sounds depend on the rapidity of vibrations and their ratio, and he proves this doctrine by a series of experimental comparisons. Thus he finds that the note of a string is as its length, by taking a string first twice, and then 4 times as long as the original string, other things remaining the same. This, indeed, was known to the ancients, and was the basis of that numerical indication of the notes which the proposition expresses. Mersenne further proceeds to show the effect of thickness and tension. He finds, Prop 7, that a string must be 4 times as thick as another to give the octave below. He finds, also Prop 8, that the tension must be about 4 times as great in order to produce the octave above. From these proportions, various others are deduced, and the law of the 29 phenomena of this kind may be considered as determined. Mersenne also undertook to measure the phenomena numerically, that is, to determine the number of vibrations of the string in each of such cases, which at first might appear difficult, since it is obviously impossible to count with the eye the passages of a sounding string backwards and forwards. But Mersenne rightly assumed that the number of vibrations is the same so long as the tone is the same, and that the ratios of the numbers of vibrations of different strings may be determined from the numerical relations of their notes. He had, therefore, only to determine the number of vibrations of one certain string or one known note to know those of all others. He took a musical string of 3/4 of a foot long, stretched with a weight of 6 pounds and 5/8, which he found gave him by its vibrations a certain standard note in his organ. He found that a string of the same material and tension, 15 feet, that is, 20 times as long, made 10 recurrences in a second. And he inferred that the number of vibrations of the shorter string must also be 20 times as great. And thus such a string must make in 1 second of time 200 vibrations. This determination of Mersenne does not appear to have attracted due notice, but some time afterwards attempts were made to ascertain the connection between the sound and its elementary pulsations in a more direct manner. Hooke, in 1681, produced sounds by the striking of the teeth of brass wheels, and Stankery, in 1706, by whirling round a large wheel in air, showed, before the Academy of Bologna, how the number of vibrations in a given note might be known. Sauveur, who, though deaf for the first 7 years of his life, was one of the greatest promoters of the science of sound, and gave it its name of acoustics, endeavored also, about the same time, to determine the number of vibrations of a standard note, or, as he called it, fixed sound. He employed 2 methods, both ingenious and both indirect. The first was the method of beats. 2 organ pipes, which form a discord, are often heard to produce a kind of howl or wavy noise, the sound swelling and declining at small intervals of time. This was readily and rightly ascribed to the coincidences of the pulsations of sound of the 2 notes after certain cycles. Thus, if the number of vibrations of the notes were as 15 to 16 in the same time, every 15th vibration of the one would coincide with every 16th vibration of the other, while all the intermediate vibrations of the 2 tones would, in various degrees, disagree with each other. And thus every such cycle, of 15 and 16 vibrations, might be heard as a separate beat of sound. Now, Sauveur wished to take a case in which these beats were so slow as to be counted, and in which the ratio of the vibrations of the notes was known from a knowledge of their musical relations. Thus, if the 2 notes form an interval of a semitone, their ratio will be that above supposed, 15 to 16. And if the beats be found to be 6 in a second, we know that, in that time, the graver note makes 90 and the acuter 96 vibrations. In this manner, Sauveur found that an open organ pipe, 5 feet long, gave 100 vibrations in a second. Sauveur's other method is more recondite and approaches to a mechanical view of the question. He proceeded on this basis. A string, horizontally stretched, cannot be drawn into a mathematical straight line, but always hangs in a very flat curve or festoon. Hence Sauveur assumed that its transverse vibrations may be conceived to be identical with the lateral swingings of such a festoon. Observing that the string C in the middle of a harpsichord hangs in such a festoon to the amount of 1/323 of an inch, he calculates, by the laws of pendulums, the time of oscillation, and finds it 1/122nd of a second. Thus this C, his fixed note, makes 122 vibrations in a second. It is curious that this process, seemingly so arbitrary, is capable of being justified on mechanical principles, though we can hardly give the author credit for the views which this justification implies. It is, therefore, easy to understand that it agreed with other experiments in the laws which it gave for the dependence of the tone on the length and tension. The problem of satisfactorily explaining this dependence on mechanical principles naturally pressed upon the attention of mathematicians when the law of the phenomena was thus completely determined by Mersenne and Sauveur. It was desirable to show that both the circumstances and the measure of the phenomena were such as known mechanical causes and laws would explain. But this problem, as might be expected, was not attacked till mechanical principles, and the modes of applying them had become tolerably familiar. As the vibrations of a string are produced by its tension, it appeared to be necessary, in the first place, to determine the law of the tension, 31, which is called into action by the motion of the string. For it is manifest that, when the string is drawn aside from the straight line into which it is stretched, there arises an additional tension, which aids in drawing it back to the straight line as soon as it is let go. Hooke on Spring, 1678, determined the law of this additional tension, which he expressed in his noted formula, ut tensio sic vis. The force is as the tension. Or rather, to express his meaning more clearly, the force of tension is as the extension, or, in a string, as the increase of length. But in reality, this principle, which is important in many acoustical problems, is, in the one now before us, unimportant. The force which urges the string towards the straight line depends, with such small extensions as we have now to consider, not on the extension, but on the curvature. And the power of treating the mathematical difficulty of curvature and its mechanical consequences was what was requisite for the solution of this problem. The problem, in its proper aspect, was first attacked and mastered by Brooke Taylor, an English mathematician of the school of Newton, by whom the solution was published in 1715 in his Methodus Incrementorum. Taylor's solution was indeed imperfect, for it only pointed out a form and a mode of vibration with which the string might move consistently with the laws of mechanics, not the mode in which it must move, supposing its form to be any whatever. It showed that the curve might be of the nature of that which is called the companion to the cycloid. And, on the supposition of the curve of the string being of this form, the calculation confirmed the previously established laws by which the tone, or the time of vibration, had been discovered to depend on the length, tension, and bulk of the string. The mathematical incompleteness of Taylor's reasoning must not prevent us from looking upon his solution of the problem as the most important step in the progress of this part of the subject. For the difficulty of applying mechanical principles to the question being once overcome, the extension and correction of the application was sure to be undertaken by succeeding mathematicians, and, accordingly, this soon happened. We may add, moreover, that the subsequent and more general solutions require to be considered with reference to Taylor's, in order to apprehend distinctly their import. And further, that it was almost evident to a mathematician, even before the general solution had appeared, that the dependence of the time of vibration on the length and tension would be the same in the general case as in the 32 Taylorian curve. So that, for the ends of physical philosophy, the solution was not very incomplete. John Bernoulli, a few years afterwards, solved the problem of vibrating chords on nearly the same principles and suppositions as Taylor. But a little later, in 1747, the next generation of great mathematicians, D'Alembert, Euler, and Daniel Bernoulli, applied the increased powers of analysis to give generality to the mode of treating this question, and especially the calculus of partial differentials, invented for this purpose. But at this epoch, the discussion, so far as it bore on physics, belonged rather to the history of another problem, which comes under our notice hereafter, that of the composition of vibrations. We shall, therefore, defer the further history of the problem of vibrating strings till we have to consider it in connection with new experimental facts. Chapter 3. Problem of the propagation of sound. We have seen that the ancient philosophers, for the most part, held that sound was transmitted as well as produced by some motion of the air, without defining what kind of motion this was. That some writers, however, applied to it a very happy similitude, the expansive motion of the circular waves produced by throwing a stone into still water. But that notwithstanding, some rejected this mode of conception, as, for instance, Bacon, who ascribed the transmission of sound to certain spiritual species. Though it was an obvious thought to ascribe the motion of sound to some motion of air. To conceive what kind of motion could and did produce this effect must have been a matter of grave perplexity at the time of which we are speaking, and is far from easy to most persons even now. We may judge of the difficulty of forming this conception when we recollect that John Bernoulli the younger declared that he could not understand Newton's proposition on this subject. The difficulty consists in this, that the movement of the parts of air in which sound consists travels along, but that the parts 33 of air themselves do not so travel. Accordingly, Otto Guericke, the inventor of the air pump, asks, how can sound be conveyed by the motion of the air, when we find that it is better conveyed through air that is still than when there is a wind? We may observe, however, that he was partly misled by finding, as he thought, that a bell could be heard in the vacuum of his air pump, a result which arose, probably, from some imperfection in his apparatus. Attempts were made to determine, by experiment, the circumstances of the motion of sound, and especially its velocity. Gassendi was one of the first who did this. He employed firearms for the purpose, and thus found the velocity to be 1473 Paris feet in a second. Roberval found a velocity so small, 560 feet, that it threw uncertainty upon the rest, and affected Newton's reasonings subsequently. Cassini, Huygens, Picard, Romer, found a velocity of 1172 Paris feet, which is more accurate than the former. Gassendi had been surprised to find that the velocity with which sounds travel is the same whether they are loud or gentle. The explanation of this constant velocity of sound, and of its amount, was one of the problems of which a solution was given in the great charter of modern science, Newton's Principia, 1687. There, for the first time, were explained the real nature of the motions and mutual action of the parts of the air through which sound is transmitted. It was shown that a body vibrating in an elastic medium will propagate pulses through the medium. That is, the parts of the medium will move forwards and backwards, and this motion will affect successively those parts which are at a greater and greater distance from the origin of motion. The parts, in going forwards, produce condensation. In returning to their first places, they allow extension. And the play of the elasticities developed by these expansions and contractions supplies the forces which continue to propagate the motion. The idea of such a motion as this is, as we have said, far from easy to apprehend distinctly. But a distinct apprehension of it is a step essential to the physical part of the sciences now under notice. For it is by means of such pulses or undulations that not only sound, but light and probably heat are propagated. We constantly meet with evidence of the difficulty which men have in conceiving this undulatory motion, and in separating it from a local motion of the medium as a 34 mass. For instance, it is not easy at first to conceive the waters of a great river flowing constantly down towards the sea, while waves are rolling up the very same part of the stream. And while the great elevation, which makes the tide, is traveling from the sea perhaps with a velocity of 50 miles an hour. The motion of such a wave, or elevation, is distinct from any stream, and is of the nature of undulations in general. The parts of the fluid stir for a short time and for a small distance, so as to accumulate themselves on a neighboring part, and then retire to their former place. And this movement affects the parts in the order of their places. Perhaps if the reader looks at a field of standing corn when gusts of wind are sweeping over it in visible waves, he will have his conception of this matter aided. For he will see that here, where each ear of grain is anchored by its stalk, there can be no permanent local motion of the substance, but only a successive stooping and rising of the separate straws, producing hollows and waves, closer and laxer strips of the crowded ears. Newton had, moreover, to consider the mechanical consequences which such condensations and rarefactions of the elastic medium, air, would produce in the parts of the fluid itself. Employing known laws of the elasticity of air, he showed, in a very remarkable proposition, the law according to which the particles of air might vibrate. We may observe that in this solution, as in that of the vibrating string already mentioned, a rule was exhibited according to which the particles might oscillate, but not the law to which they must conform. It was proved that, by taking the motion of each particle to be perfectly similar to that of a pendulum, the forces, developed by contraction and expansion, were precisely such as the motion required. But it was not shown that no other type of oscillation would give rise to the same accordance of force and motion. Newton's reasoning also gave a determination of the speed of propagation of the pulses. It appeared that sound ought to travel with the velocity which a body would acquire by falling freely through half the height of a homogeneous atmosphere. The height of a homogeneous atmosphere, being the height which the air must have in order to produce, at the Earth's surface, the actual atmospheric pressure, supposing no diminution of density to take place in ascending. This height is about 29,000 feet, and hence it followed that the velocity was 968 feet. This velocity is really considerably less than that of sound, but at the time of which, 35, we speak, no accurate measure had been established, and Newton persuaded himself, by experiments made in the cloister of Trinity College, his residence, that his calculation was not far from the fact. When, afterwards, more exact experiments showed the velocity to be 1142 English feet, Newton attempted to explain the difference by various considerations, none of which were adequate to the purpose, as the dimensions of the solid particles of which the fluid air consists or the vapors which are mixed with it. Other writers offered other suggestions, but the true solution of the difficulty was reserved for a period considerably subsequent. Newton's calculation of the motion of sound, though logically incomplete, was the great step in the solution of the problem. for mathematicians could not but presume that his result was not restricted to the hypothesis on which he had obtained it, and the extension of the solution required only mere ordinary talents. The logical defect of his solution was assailed, as might have been expected. Cranmer, professor at Geneva, in 1741, conceived that he was destroying the conclusiveness of Newton's reasoning by showing that it applied equally to other modes of oscillation. This, indeed, contradicted the enunciation of the 48th prop of the second book of the Principia, but it confirmed and extended all the general results of the demonstration, for it left even the velocity of sound unaltered, and thus showed that the velocity did not depend mechanically on the type of the oscillation. But the satisfactory establishment of this physical generalization was to be supplied from the vast generalizations of analysis, which mathematicians were now becoming able to deal with. Accordingly, this task was performed by the great master of analytical generalization, Lagrange, in 1759, when, at the age of 23, he and two friends published the first volume of the Turin Memoirs. Euler, as his manner was, at once perceived the merit of the new solution and pursued the subject on the views thus suggested. Various analytical improvements and extensions were introduced into the solution by the two great mathematicians, but none of these at all altered the formula by which the velocity of sound was expressed, and the discrepancy between calculation and observation, about 1/6 of the whole, which had perplexed Newton, remained still unaccounted for. The merit of satisfactorily explaining this discrepancy belongs to Laplace. He was the first to remark that the common law of the 36 changes of elasticity in the air, as dependent on its compression, cannot be applied to those rapid vibrations in which sound consists, since the sudden compression produces a degree of heat which additionally increases the elasticity. The ratio of this increase depended on the experiments by which the relation of heat and air is established. Laplace, in 1816, published the theorem on which the correction depends. On applying it, the calculated velocity of sound agreed very closely with the best antecedent experiments, and was confirmed by more exact ones instituted for that purpose. This step completes the solution of the problem of the propagation of sound as a mathematical induction, obtained from and verified by facts. Most of the discussions concerning points of analysis to which the investigations on this subject gave rise, as, for instance, the admissibility of discontinuous functions into the solutions of partial differential equations, belong to the history of pure mathematics. Those which really concern the physical theory of sound may be referred to the problem of the motion of air in tubes, to which we shall soon have to proceed. But we must first speak of another form which the problem of vibrating strings assumed. It deserves to be noticed that the ultimate result of the study of the undulations of fluids seems to show that the comparison of the motion of air in the diffusion of sound with the motion of circular waves from a center in water, which is mentioned at the beginning of this chapter, though pertinent in a certain way, is not exact. It appears by Mr. Scott's recent investigations concerning waves that the circular waves are oscillating waves of the second order and are gregarious. The sound wave seems rather to resemble the great solitary wave of translation of the first order, of which we have already spoken in Book 6. Chapter 6. Chapter 4. Problem of different sounds of the same string. It had been observed at an early period of acoustical knowledge that one string might give several sounds. Mersenne and others, 37, had noticed that when a string vibrates, one which is in unison with it vibrates without being touched. He was also aware that this was true if the second string was an octave or a twelfth below the first. This was observed as a new fact in England in 1674 and communicated to the Royal Society by Wallis. But the later observers ascertained further that the longer string divides itself into two or into three equal parts, separated by nodes or points of rest. This they proved by hanging bits of paper on different parts of the string. The discovery so modified was again made by Sauveur about 1700. The sounds thus produced in one string by the vibration of another have been termed sympathetic sounds. Similar sounds are often produced by performers on stringed instruments, by touching the string at one of its aliquot divisions, and are then called the acute harmonics. Such facts were not difficult to explain on Taylor's view of the mechanical condition of the string, but the difficulty was increased when it was noticed that a sounding body could produce these different notes at the same time. Mersenne had remarked this, and the fact was more distinctly observed and pursued by Sauveur. The notes thus produced in addition to the genuine note of the string have been called secondary notes. Those usually heard are the octave, the 12th, and the 17th above the note itself. To supply a mode of conceiving distinctly and explaining mechanically vibrations which should allow of such an effect was therefore a requisite step in acoustics. This task was performed by Daniel Bernoulli in a memoir published in 1755. He there stated and proved the principle of the coexistence of small vibrations. It was already established that a string might vibrate either in a single swelling, if we use this word to express the curve between two nodes which Bernoulli calls a venter, or in 2 or 3 or any number of equal swellings with immovable nodes between. Daniel Bernoulli showed further that these nodes might be combined, each taking place as if it were the only one. This appears sufficient to explain the coexistence of the harmonic sounds just noticed. D'Alembert, indeed, in the article Fundamental in the French Encyclopédie, and Lagrange in his dissertation on sound in the Turin Memoirs, offer several objections to this explanation, and it cannot be denied that the subject has its difficulties. But 38. Still, these do not deprive Bernoulli of the merit of having pointed out the principle of coexistent vibrations, or divest that principle of its value in physical science. Daniel Bernoulli's memoir, of which we speak, was published at a period when the clouds which involve the general analytical treatment of the problem of vibrating strings were thickening about Euler and D'Alembert and darkening into a controversial hue. And as Bernoulli ventured to interpose his view as a solution of these difficulties, which in a mathematical sense it is not, we can hardly be surprised that he met with a rebuff. The further prosecution of the different modes of vibration of the same body need not be here considered. The sounds which are called grave harmonics have no analogy with the acute harmonics above mentioned, nor do they belong to this section. For in the case of grave harmonics, we have one sound from the cooperation of two strings instead of several sounds from one string. These harmonics are, in fact, connected with beats, of which we have already spoken, the beats becoming so close as to produce a note of definite musical quality. The discovery of the grave harmonics is usually ascribed to Tartini, who mentions them in 1754, but they are first noticed in the work of Sorge on tuning organs, 1744. He there expresses this discovery in a query. Whence comes it that if we tune a fifth, 2, 3, a third sound is faintly heard, the octave below the lower of the two notes? Nature shows that with 2, 3, she still requires the unity to perfect the order 1, 2, 3. The truth is that these numbers express the frequency of the vibrations, and thus there will be coincidences of the notes 2 and 3, which are of the frequency 1, and consequently give the octave below the sound 2. This is the explanation given by Lagrange, and is indeed obvious. Chapter 5. Problem of the sounds of pipes. It was taken for granted by those who reasoned on sounds that the sounds of flutes, organ pipes, and wind instruments in general, 39, consisted in vibrations of some kind, but to determine the nature and laws of these vibrations and to reconcile them with mechanical principles was far from easy. The leading facts which had been noticed were that the note of a pipe was proportional to its length, and that a flute and similar instruments might be made to produce some of the acute harmonics, as well as the genuine note. It had further been noticed that pipes closed at the end, instead of giving the series of harmonics 1, a half, 1/3, a quarter, and C, would give only those notes which answer to the odd numbers 1, 1/3, and C. In this problem also, Newton made the first step to the solution. At the end of the propositions respecting the velocity of sound, of which we have spoken, he noticed that it appeared by taking Mersenne's or Sauveur's determination of the number of vibrations corresponding to a given note, that the pulse of air runs over twice the length of the pipe in the time of each vibration. He does not follow out this observation, but it obviously points to the theory that the sound of a pipe consists of pulses which travel back and forwards along its length and are kept in motion by the breath of the player. This supposition would account for the observed dependence of the note on the length of the pipe. The subject does not appear to have been again taken up in a theoretical way till about 1760, when Lagrange in the second volume of the Turin Memoirs and de Bernoulli in the Memoirs of the French Academy for 1762 published important essays in which some of the leading facts were satisfactorily explained, and which may therefore be considered as the principal solutions of the problem. In these solutions, there was necessarily something hypothetical. In the case of vibrating strings, as we have seen, the form of the vibrating curve was guessed at only, but the existence and position of the nodes could be rendered visible to the eye. In the vibrations of air, we cannot see either the places of nodes or the mode of vibration, but several of the results are independent of these circumstances. Thus, both of the solutions explain the fact that a tube closed at one end is in unison with an open tube of double the length. And by supposing nodes to occur, they account for the existence of the odd series of harmonics alone, 1, 3, 5, in closed tubes, while the whole series 1, 2, 3, 4, 5, and C occurs in open ones. Both views of the nature of the vibration appear to be nearly the same, though Lagrange's is expressed with an analytical generality which renders it obscure, and Bernoulli has perhaps, 40, laid down an hypothesis more special than was necessary. Lagrange considers the vibration of open flutes as the oscillations of a fiber of air, under the condition that its elasticity at the two ends is, during the whole oscillation, the same as that of the surrounding atmosphere. Bernoulli supposes the whole inertia of the air in the flute to be collected into one particle, and this to be moved by the whole elasticity arising from this displacement. It may be observed that both these modes of treating the matter come very near to what we have stated as Newton's theory. For though Bernoulli supposes all the air in the flute to be moved at once, and not successively, as by Newton's pulse, in either case the whole elasticity moves the whole air in the tube, and requires more time to do this according to its quantity. Since that time, the subject has received further mathematical development from Euler, Lambert, and Poisson, but no new explanation of facts has arisen. Attempts have, however, been made to ascertain experimentally the places of the nodes. Bernoulli himself had shown that this place was affected by the amount of the opening, and Lambert had examined other cases with the same view. Savart traced the node in various musical pipes under different conditions, and very recently Mr. Hopkins, of Cambridge, has pursued the same experimental inquiry. It appears from these researches that the early assumptions of mathematicians with regard to the position of the nodes are not exactly verified by the facts. When the air in a pipe is made to vibrate so as to have several nodes which divide it into equal parts, it had been supposed by acoustical writers that the part adjacent to the open end was half of the other parts. The outermost node, however, is found experimentally to be displaced from the position thus assigned to it, by a quantity depending on several collateral circumstances. Since our purpose was to consider this problem only so far as it has tended towards its mathematical solution, we have avoided saying anything of the dependence of the mode of vibration on the cause by which the sound is produced. And consequently, the researches on the effects of reeds, embouchures, and the like, by Chladni, Savart, Willis, and others, do not belong to our subject. It is easily seen that the complex effect of the elasticity and other properties of the reed and of the air together is a problem of which we can hardly, 41, hope to give a complete solution till our knowledge has advanced much beyond its present condition. Indeed, in the science of acoustics there is a vast body of facts to which we might apply what has just been said. But for the sake of pointing out some of them, we shall consider them as the subjects of one extensive and yet unsolved problem. Chapter 6. Problem of different modes of vibration of bodies in general. Not only the objects of which we have spoken hitherto, strings and pipes, but almost all bodies are capable of vibration. Bells, gongs, tuning forks are examples of solid bodies, drums and tambourines of membranes. If we run a wet finger along the edge of a glass goblet, we throw the fluid which it contains into a regular vibration. And the various character which sounds possess according to the room in which they are uttered shows that large masses of air have peculiar modes of vibration. Vibrations are generally accompanied by sound, and they may, therefore, be considered as acoustical phenomena, especially as the sound is one of the most decisive facts in indicating the mode of vibration. Moreover, every body of this kind can vibrate in many different ways, the vibrating segments being divided by nodal lines and surfaces of various form and number. The mode of vibration, selected by the body in each case, is determined by the way in which it is held, the way in which it is set in vibration, and the like circumstances. The general problem of such vibrations includes the discovery and classification of the phenomena, the detection of their formal laws, and, finally, the explanation of these on mechanical principles. We must speak very briefly of what has been done in these ways. The facts which indicate nodal lines had been remarked by Galileo on the sounding board of a musical instrument, and Hooke had proposed to observe the vibrations of a bell by strewing flour upon it. But it was Chladni, a German philosopher, who enriched acoustics with the discovery of the vast variety of symmetrical figures of nodal lines, which are exhibited on plates of regular forms when 42 made to sound. His first investigations on this subject, Entdeckungen über die Theorie des Klangs, were published 1787, and in 1802 and 1817 he added other discoveries. In these works, he not only related a vast number of new and curious facts, but in some measure reduced some of them to order and law. For instance, he has traced all the vibrations of square plates to a resemblance with those forms of vibration in which nodal lines are parallel to one side of the square, and those in which they are parallel to another side, and he has established a notation for the modes of vibration founded on this classification. Thus, 5-2 denotes a form in which there are 5 nodal lines parallel to one side and 2 to another, or a form which can be traced to a disfigurement of such a standard type. Savart pursued this subject still further, and traced, by actual observation, the forms of the nodal surfaces which divide solid bodies and masses of air when in a state of vibration. The dependence of such vibrations upon their physical cause, namely, the elasticity of the substance, we can conceive in a general way. But the mathematical theory of such cases is, as might be supposed, very difficult, even if we confine ourselves to the obvious question of the mechanical possibility of these different modes of vibration, and leave out of consideration their dependence upon the mode of excitation. The transverse vibrations of elastic rods, plates, and rings had been considered by Euler in 1779. But his calculation concerning plates had foretold only a small part of the curious phenomena observed by Chladni, and the several notes which, according to his calculation, the same ring ought to give, were not in agreement with experiment. Indeed, researches of this kind, as conducted by Euler and other authors, rather were, and were intended for, examples of analytical skill than explanations of physical facts. James Bernoulli, after the publication of Chladni's experiments in 1787, attempted to solve the problem for plates by treating a plate as a collection of fibers. But, as Chladni observes, the justice of this mode of conception is disproved by the disagreement of the results with experiment. The Institute of France, which had approved of Chladni's labors, proposed in 1809 the problem now before us as a prize question, to give the mathematical theory of the vibrations of elastic, 43 surfaces, and to compare it with experiment. Only one memoir was sent in as a candidate for the prize, and this was not crowned, though honorable mention was made of it. The formulae of James Bernoulli were, according to M. Poisson's statement, defective, in consequence of his not taking into account the normal force which acts at the exterior boundary of the plate. The author of the anonymous memoir corrected this error, and calculated the note corresponding to various figures of the nodal lines, and he found an agreement with experiment sufficient to justify his theory. He had not, however, proved his fundamental equation, which M. Poisson demonstrated in a memoir, read in 1814. At a more recent period also, Poisson and Cauchy, as well as a lady, Emil, Sophie Germain, have applied to this problem the artifices of the most improved analysis. M. Poisson determined the relation of the notes given by the longitudinal and the transverse vibrations of a rod, and solved the problem of vibrating circular plates when the nodal lines are concentric circles. In both these cases, the numerical agreement of his results with experience seemed to confirm the justice of his fundamental views. He proceeds upon the hypothesis that elastic bodies are composed of separate particles held together by the attractive forces which they exert upon each other, and distended by the repulsive force of heat. M. Cauchy has also calculated the transverse, longitudinal, and rotatory vibrations of elastic rods, and has obtained results agreeing closely with experiment through a considerable list of comparisons. The combined authority of two profound analysts, Asmpoyson and Cauchy, leads us to believe that, for the simpler cases of the vibrations of elastic bodies, mathematics has executed her task, but most of the more complex cases remain as yet unsubdued. The two brothers, Ernest and William Weber, made many curious observations on undulations, which are contained in their Wellenlehre, Doctrine of Waves, published at Leipzig in 1825. They were led to suppose, as Young had suggested at an earlier period, that Chladni's figures of nodal lines in plates were to be accounted for by the superposition of undulations. Mr. Wheatstone has undertaken to account for Chladni's figures of vibrating square plates by this, 44, superposition of two or more simple and obviously allowable modes of nodal division, which have the same time of vibration. He assumes, for this purpose, certain primary figures, containing only parallel nodal lines, and by combining these, first in twos and then in fours, he obtains most of Chladni's observed figures and accounts for their transitions and deviations from regularity. The principle of the superposition of vibrations is so solidly established as a mechanical truth that we may consider an acoustical problem as satisfactorily disposed of when it is reduced to that principle, as well as when it is solved by analytical mechanics. But at the same time, we may recollect that the right application and limitation of this law involves no small difficulty. And in this case, as in all advances in physical science, we cannot but wish to have the new ground which has been gained gone over by some other person in some other manner, and thus secured to us as a permanent possession. Savart's laws in what has preceded, the vibrations of bodies have been referred to certain general classes, the separation of which was suggested by observation. For example, the transverse, longitudinal, and rotatory vibrations of rods. The transverse vibrations, in which the rod goes backwards and forwards across the line of its length, were the only ones noticed by the earlier acousticians. The others were principally brought into notice by Chladni. As we have already seen in the preceding pages, this classification serves to express important laws, as, for instance, a law obtained by M. Poisson, which gives the relation of the notes produced by the transverse and longitudinal vibrations of a rod. But this distinction was employed by M. Felix Savart to express laws of a more general kind. And then, as often happens in the progress of science, by pursuing these laws to a higher point of generality, the distinction again seemed to vanish. A very few words will explain these steps. It was long ago known that vibrations may be communicated by contact. The distinction of transverse and longitudinal vibrations being established, Savart found that if one rod touched another perpendicularly, the longitudinal vibrations of the first occasion, transverse vibrations in the second, and vice versa. This is the more remarkable, since the two sets of vibrations are not equal in rapidity, and therefore cannot sympathize in any obvious manner. Savart found himself, 45, able to generalize this proposition, and to assert that in any combination of rods, strings, and laminae at right angles to each other, the longitudinal and transverse vibrations affect respectively the rods in the one and other direction, so that when the horizontal rods, for example, vibrate in the one way, the vertical rods vibrate in the other. This law was thus expressed in terms of that classification of vibrations of which we have spoken. Yet we easily see that we may express it in a more general manner, without referring to that classification, by saying that vibrations are communicated so as always to be parallel to their original direction. And by following it out in this shape by means of experiment, M. Savart was led, a short time afterwards, to deny that there is any essential distinction in these different kinds of vibration. We are thus led, he says in 1822, to consider normal vibrations as only one circumstance in a more general motion common to all bodies, analogous to tangential vibrations. That is, as produced by small molecular oscillations, and differently modified according to the direction which it affects, relatively to the dimensions of the vibrating body. These inductions, as he properly calls them, are supported by a great mass of ingenious experiments and may be considered as well established when they are limited to molecular oscillations, employing this phrase in the sense in which it is understood in the above statement, and also when they are confined to bodies in which the play of elasticity is not interrupted by parts more rigid than the rest, as the sound post of a violin. And before I quit the subject, I may notice a consequence which M. Savart has deduced from his views, and which, at first sight, appears to overturn most of the earlier doctrines respecting vibrating bodies. It was formerly held that tense strings and elastic rods could vibrate only in a determinate series of modes of division, with no intermediate steps. But M. Savart maintains, on the contrary, that they produce sounds which are gradually transformed into one another by indefinite intermediate degrees. The reader may naturally ask, what is the solution of this apparent, 46, contradiction between the earliest and the latest discoveries in acoustics? And the answer must be that these intermediate modes of vibration are complex in their nature and difficult to produce, and that those which were formerly believed to be the only possible vibrating conditions are so eminent above all the rest by their features, their simplicity, and their facility that we may still, for common purposes, consider them as a class apart. Although for the sake of reaching a general theorem, we may associate them with the general mass of cases of molecular vibrations. And thus we have no exception here, as we can have none in any case, to our maxim that what formed part of the early discoveries of science forms part of its latest systems. Note 53/8. For the suggestion of the necessity of this limitation, I am indebted to Mr. Willis. We have thus surveyed the progress of the science of sound up to recent times, with respect both to the discovery of laws of phenomena and the reduction of these to their mechanical causes. The former branch of the science has necessarily been inductively pursued, and therefore has been more peculiarly the subject of our attention. And this consideration will explain why we have not dwelt more upon the deductive labors of the great analysts who have treated of this problem. To those who are acquainted with the high and deserved fame which the labors of D'Alembert, Euler, Lagrange, and others, upon this subject, enjoy among mathematicians, it may seem as if we had not given them their due prominence in our sketch. But it is to be recollected here, as we have already observed in the case of hydrodynamics, that even when the general principles are uncontested, mere mathematical deductions from them do not belong to the history of physical science, except when they point out laws which are intermediate between the general principle and the individual facts, and which observation may confirm. The business of constructing any science may be figured as the task of forming a road on which our reason can travel through a certain province of the external world. We have to throw a bridge which may lead from the chambers of our own thoughts, from our speculative principles, to the distant shore of material facts. But in all cases, the abyss is too wide to be crossed, except we can find some intermediate points on which the piers of our structure may rest. Mere facts without connection or law are only the rude stones hewn from the opposite bank, of which our arches may, at some time, be built. But mere hypothetical mathematical calculations are only plans of projected structures, and those plans which exhibit only one vast, 47, and single arch, or which suppose no support but that which our own position supplies, will assuredly never become realities. We must have a firm basis of intermediate generalizations in order to frame a continuous and stable edifice. In the subject before us, we have no want of such points of intermediate support, although they are in many instances irregularly distributed and obscurely seen. The number of observed laws and relations of the phenomena of sound is already very great, and though the time may be distant, there seems to be no reason to despair of one day uniting them by clear ideas of mechanical causation, and thus of making acoustics a perfect secondary mechanical science. The historical sketch just given includes only such parts of acoustics as have been in some degree reduced to general laws and physical causes, and thus excludes much that is usually treated of under that head. Moreover, many of the numerical calculations connected with sound belong to its agreeable effect upon the ear, as the properties of the various systems of temperament. These are parts of theoretical music, not of acoustics, of the philosophy of the fine arts, not of physical science, and may be referred to in a future portion of this work so far as they bear upon our object. The science of acoustics may, however, properly consider other differences of sound than those of acute and grave, for instance, the articulate differences, or those by which the various letters are formed. Some progress has been made in reducing this part of the subject to general rules, for though Kempellen's talking machine was only a work of art, Mr. Willis's machine, which exhibits the relation among the vowels, gives us a law such as forms a step in science. We may, however, consider this instrument as a phthangometer or measure of vowel quality, and in that point of view we shall have to refer to it again when we come to speak of such measures. Note 55/8 on the vowel sounds and on reed organ pipes. Cam. Trans. Roman 3, 237. 49, Book 9. Secondary Mechanical Sciences. Continued. History of Optics. Formal and Physical. Omega delta iota letter 1f78, sigma letter 1f51 psi iota mu epsilon lambda alpha theta rho omicron u, letter 1f14 chi omega nu, cap rho alpha tau omicron sigma, alpha letter 1f30, letter 1f72, nu letter 1f00, tau epsilon iota rho letter 1f72, sigma letter 1f04 sigma tau rho omega nu, letter 1f20 epsilon lambda iota omicron upsilon, tau epsilon, sigma epsilon lambda eta nu alpha iota eta sigma, tau epsilon mu epsilon rho iota sigma mu alpha, pi alpha nu delta alpha mu alpha tau omega rho, pi epsilon rho iota pi nu omicron upsilon, pi letter 1f b6, sigma iota nu zeta omega omicron letter 1f d6, sigma iota nu letter 1f14 nu alpha epsilon sigma mu alpha, asterisk letter 1f51 psi iota phi alpha nu eta sigma, letter 1f04 I theta eta rho. Cap omicron sigma mu omicron upsilon, sigma tau omicron iota chi, epsilon letter 1f d6, omicron nu, asterisk letter 1f04 rho iota sigma tau omicron nu letter 1f00, gamma lambda alpha letter 1f78, nu letter 1f66, beta lambda alpha sigma tau eta mu alpha, sigma epsilon lambda alpha sigma phi omicron rho omicron u, letter 1f00, sigma tau, epsilon rho omicron phi, epsilon gamma gamma letter 1f72, sigma kappa iota kappa lambda eta sigma kappa omega nu, lambda iota tau omicron mu alpha iota, sigma epsilon, cap epsilon kappa rho alpha mu epsilon nu omicron u, asterisk epsilon, letter 1f54 delta iota omicron, nu epsilon letter 1f36, nu alpha iota Orpheus. Hymn. O thou who fillest the palaces of Jove, who flowest round moon and sun and stars above, pervading, bright, life-giving element, supernal ether, fair and excellent, fountain of hope and joy, of light and day, we own at length thy tranquil, steady sway. 51. Introduction. Formal and Physical Optics. The history of the science of optics, written at length, would be very voluminous, but we shall not need to make our history so, since our main object is to illustrate the nature of science and the conditions of its progress. In this way, optics is peculiarly instructive, the more so, as its history has followed a course in some respects different from both the sciences previously reviewed. Astronomy, as we have seen, advanced with a steady and continuous movement from one generation to another, from the earliest time, till her career was crowned by the great unforeseen discovery of Newton. Acoustics had her extreme generalization in view from the first, and her history consists in the correct application of it to successive problems. Optics advanced through a scale of generalizations as remarkable as those of astronomy, but for a long period she was almost stationary, and at last was rapidly impelled through all those stages by the energy of 2 or 3 discoverers. The highest point of generality which optics has reached is little different from that which acoustics occupied at once. But in the older and earlier science, we still want that palpable and pointed confirmation of the general principle, which the undulatory theory receives from optical phenomena. Astronomy has amassed her vast fortune by long-continued industry and labor. Optics has obtained hers in a few years by sagacious and happy speculations. Acoustics, having early acquired a competence, has since been employed rather in improving and adorning than in extending her estate. The successive inductions by which optics made her advances might, of course, be treated in the same manner as those of astronomy, each having its prelude and its sequel. But most of the discoveries in optics are of a smaller character and have less employed the minds of men than those of astronomy, and it will not be necessary to exhibit them in this detailed manner till we come to the great generalization by which the theory was established. I shall, therefore, now pass rapidly and review the earlier optical discoveries without any such division of the series. 52. Optics, like astronomy, has for its object of inquiry, first, the laws of phenomena and next, their causes. And we may hence divide this science, like the other, into formal optics and physical optics. The distinction is clear and substantive, but it is not easy to adhere to it in our narrative. For, after the theory had begun to make its rapid advance, many of the laws of phenomena were studied and discovered in immediate reference to the theoretical cause, and do not occupy a separate place in the history of science, as in astronomy they do. We may add that the reason why formal astronomy was almost complete before physical astronomy began to exist was that it was necessary to construct the science of mechanics in the meantime in order to be able to go on. Whereas, in optics, mathematicians were able to calculate the results of the undulatory theory as soon as it had suggested itself from the earlier facts, and while the great mass of facts were only becoming known. We shall then, in the first 9 chapters of the History of Optics, treat of the formal science, that is, the discovery of the laws of phenomena. The classes of phenomena which will thus pass under our notice are numerous, namely reflection, refraction, chromatic dispersion, achromatization, double refraction, polarization, depolarization, the colors of thin plates, the colors of thick plates, and the fringes and bands which accompany shadows. All these cases had been studied, and, in most of them, the laws had been in a great measure discovered, before the physical theory of the subject gave to our knowledge a simpler and more solid form. 53. Formal Optics. Chapter 1. Primary Induction of Optics, Rays of Light, and Laws of Reflection. In speaking of the ancient history of physics, we have already noticed that the optical philosophers of antiquity had satisfied themselves that vision is performed in straight lines, that they had fixed their attention upon those straight lines, or rays, as the proper object of the science. They had ascertained that rays reflected from a bright surface make the angle of reflection equal to the angle of incidence, and they had drawn several consequences from these principles. We may add to the consequences already mentioned the art of perspective, which is merely a corollary from the doctrine of rectilinear visual rays. For if we suppose objects to be referred by such rays to a plane interposed between them and the eye, all the rules of perspective follow directly. The ancients practiced this art, as we see in the pictures which remain to us, and we learn from Vitruvius that they also wrote upon it. Agatharchus, who had been instructed by Aeschylus in the art of making decorations for the theater, was the first author on this subject, and Anaxagoras, who was a pupil of Agatharchus, also wrote an actinographia, or doctrine of drawing by rays. But none of these treatises are come down to us. The moderns reinvented the art in the flourishing times of the art of painting, that is, about the end of the 15th century, and, belonging to that period also, we have treatises upon it. But these are only deductive applications of the most elementary optical doctrines. We must proceed to the inductions by which further discoveries were made. 54. Chapter 2. Discovery of the Law of Refraction. We have seen in the former part of this history that the Greeks had formed a tolerably clear conception of the refraction as well as the reflection of the rays of light, and that Ptolemy had measured the amount of refraction of glass and water at various angles. If we give the names of the angle of incidence and the angle of refraction respectively to the angles which a ray of light makes with the line perpendicular to surface of glass or water, or any other medium, within and without the medium, Ptolemy had observed that the angle of refraction is always less than the angle of incidence. He had supposed it to be less in a given proportion, but this opinion is false, and was afterwards rightly denied by the Arabian mathematician Alhazen. The optical views which occur in the work of Alhazen are far sounder than those of his predecessors, and the book may be regarded as the most considerable monument which we have of the scientific genius of the Arabians, for it appears, for the most part, not to be borrowed from Greek authorities. The author not only asserts, lib. Roman 7, that refraction takes place towards the perpendicular, and refers to experiment for the truth of this, and that the quantities of the refraction differ according to the magnitudes of the angles which the directions of the incidental rays, primi linei, make with the perpendiculars to the surface. But he also says distinctly and decidedly that the angles of refraction do not follow the proportion of the angles of incidence. There appears to be good ground to assent to the assertion of Alhazen's originality, made by his editor Rissner, who says, Euclideum hic vel tolmacum nihil fear est. Besides the doctrine of reflection and refraction of light, the Arabian author gives a description of the eye. He distinguishes 3 fluids, humor acus, crystallinus, vitreous, and 4 coats of the eye, tunica adherens, cornea, uvea, tunica redi similes. He distinguishes also 3 kinds of vision: visibile percipitor, aut solo visu et syllogismo, aut visu et anticipata notion. He has several propositions relating to what we sometimes call the philosophy of vision. For instance this, e visibili sepius viso remanet in anima generalis notio, NC 55. The assertion that the angles of refraction are not proportional to the angles of incidence was an important remark. And if it had been steadily kept in mind, the next thing to be done with regard to refraction was to go on experimenting and conjecturing till the true law of refraction was discovered, and in the meantime to apply the principle as far as it was known. Alhazen, though he gives directions for making experimental measures of refraction, does not give any table of the results of such experiments, as Ptolemy had done. Vitalo, a Pole, who in the 13th century published an extensive work upon optics, does give such a table, and asserts it to be deduced from experiment, as I have already said, volume I. But this assertion is still liable to doubt in consequence of the table containing impossible observations. As I have already stated, Vitalo asserts that his tables were derived from his own observations. Their near agreement with those of Ptolemy does not make this improbable, for where the observations were only made to half a degree, there was not much room for observers to differ. It is not unlikely that the observations of refraction out of air into water and glass, and out of water into glass, were actually made, while the impossible values which accompany them, of the refraction out of water and glass into air, and out of glass into water, were calculated, and calculated from an erroneous rule. The principle that a ray refracted in glass or water is turned towards the perpendicular, without knowing the exact law of refraction, enabled mathematicians to trace the effects of transparent bodies in various cases. Thus, in Roger Bacon's works, we find a tolerably distinct explanation of the effect of a convex glass. And in the work of Vitalo, the effect of refraction at the 2 surfaces of a glass globe is clearly traceable. Notwithstanding Alhazen's assertion of the contrary, the opinion was still current among mathematicians that the angle of refraction was proportional to the angle of incidence. But when Kepler's attention was drawn to the subject, he saw that this was plainly inconsistent with the observations of Vitalo for large angles, and he convinced himself by his own experiments that the true law was something different from the one commonly supposed. The discovery of this true law excited in him an eager curiosity, and this point had the more interest for him in consequence of the introduction of a correction for atmospheric refraction into astronomical calculations, which had been made by Tycho, and of the invention of the telescope. In 56, his supplement to Vitalo, published in 1604, Kepler attempts to reduce to a rule the measured quantities of refraction. The reader who recollects what we have already narrated, the manner in which Kepler attempted to reduce to law the astronomical observations of Tycho, devising an almost endless variety of possible formulae tracing their consequences with undaunted industry, and relating, with a vivacious garrulity, his disappointments and his hopes, will not be surprised to find that he proceeded in the same manner with regard to the tables of observed refractions. He tried a variety of constructions by triangles, conic sections, and without being able to satisfy himself, and he at last is obliged to content himself with an approximate rule, which makes the refraction partly proportional to the angle of incidence, and partly to the secant of that angle. In this way, he satisfies the observed refractions with an A difference of less than half a degree each way. When we consider how simple the law of refraction is, that the ratio of the sines of the angles of incidence and refraction is constant for the same medium, it appears strange that a person attempting to discover it and drawing triangles for the purpose should fail. But this lot of missing what afterwards seems to have been obvious is a common one in the pursuit of truth. The person who did discover the law of the signs was Willebrord Snell, about 1621, but the law was first published by Descartes, who had seen Snell's papers. Descartes does not acknowledge this law to have been first detected by another, and after his manner, instead of establishing its reality by reference to experiment, he pretends to prove a priori that it must be true, comparing for this purpose the particles of light to balls striking a substance which accelerates them. Huygens says of Snell's papers, "Qui et nos vidimus aliquando, et Cartesium quoque vidus excepimus, et hinc fortas mensuram elam qui in sinibus consistit alicurit." Isaac Vossius, De Lucis Natura et Proprietate, says that he also had seen this law in Snell's unpublished optical treatise. The same writer says, "Quod itac Cartesius habet, refractionem momenta non exigenda es ad angulos sed ad lineas, id tuo Snellio, exceptum fair debuisset, cujus nomen more solido dissimulavit." Cartesius got his law from Snell, and in his usual way concealed it. 57. Huygens' assertion that Snell did not attend to the proportion of the signs is very captious, and becomes absurdly so when it is made to mean that Snell did not know the law of the signs. It is not denied that Snell knew the true law, or that the true law is the law of the signs. Snell does not use the trigonometrical term sign, but he expresses the law in a geometrical form more simply. Even if he had attended to the law of the signs, he might reasonably have preferred his own way of stating it. James Gregory also independently discovered the true law of refraction, and, in publishing it, states that he had learnt that it had already been published by Descartes. But though Descartes does not, in this instance, produce any good claims to the character of an inductive philosopher, he showed considerable skill in tracing the consequences of the principle when once adopted. In particular, we must consider him as the genuine author of the explanation of the rainbow. It is true that Flescher and Kepler had previously ascribed this phenomenon to the rays of sunlight which, falling on drops of rain, are refracted into each drop, reflected at its inner surface, and refracted out again. Antonio de Dominis had found that a glass globe of water, when placed in a particular position with respect to the eye, exhibited bright colors, and had hence explained the circular form of the bow, which, indeed, Aristotle had done before. But none of these writers had shown why there was a narrow bright circle of a definite diameter. For the drops which send rays to the eye after two refractions and a reflection occupy a much wider space in the heavens. Descartes assigned the reason for this in the most satisfactory manner, by showing that the rays which, after two refractions and a reflection, come to the eye at an angle of about 41 degrees with their original direction, are far more dense than those in any other position. He showed, in the same manner, that the existence and position of the secondary bow resulted from the same laws. This is the complete and adequate account of the state of things, so far as the brightness of the bows only is concerned. The explanation of the colors belongs to the next article of our survey. The explanation of the rainbow and of its magnitude, afforded by Snell's law of signs, was perhaps one of the leading points in the verification of the law. The principle, being once established, was applied by the aid of mathematical reasoning to atmospheric refractions, 58 optical instruments, diacoustic curves, that is, the curves of intense light produced by refraction, and to various other cases, and was, of course, tested and confirmed by such applications. It was, however, impossible to pursue these applications far without a due knowledge of the laws by which, in such cases, colors are produced. To these we now proceed. I have omitted many interesting parts of the history of optics about this period, because I was concerned with the inductive discovery of laws, rather than with mathematical deductions from such laws when established, or applications of them in the form of instruments. I might otherwise have noticed the discovery of spectacle glasses, of the telescope, of the microscope, of the camera obscura, and the mathematical explanation of these and other phenomena, as given by Kepler and others. I might also have noticed the progress of knowledge respecting the eye and vision. We have seen that Alhazen described the structure of the eye. The operation of the parts was gradually made out. Baptista Porta compares the eye to his camera obscura, Magia Naturalis, 1579. Scheiner, in his Oculus, published 1652, completed the theory of the eye. and Kepler discussed some of the questions even now often agitated. As the causes and conditions of our seeing, objects single with two eyes and erect with inverted images. Chapter 3. Discovery of the law of dispersion by refraction. Early attempts were made to account for the colors of the rainbow and various other phenomena in which colors are seen to arise from transient and unsubstantial combinations of media. Thus, Aristotle explains the colors of the rainbow by supposing that it is light seen through a dark medium. Now, says he, the bright seen through the dark appears red, as, for instance, the fire of green wood seen through the smoke, and the sun through mist. Also, the weaker is the light, or the visual power, and the nearer the color approaches to the black, becoming first red, then green, then purple. But the 59 vision is strongest in the outer circle, because the periphery is greater, thus we shall have a gradation from red through green to purple in passing from the outer to the inner circle. This account would hardly have deserved much notice, if it had not been for a strange attempt to revive it, or something very like it, in modern times. The same doctrine is found in the work of de Dominis. According to him, light is white, but if we mix with the light something dark, the colors arise first red, then green, then blue or violet. He applies this to explain the colors of the rainbow, by means of the consideration that, of the rays which come to the eye from the globes of water, some go through a larger thickness of the globe than others, whence he obtains the gradation of colors just described. Note 12/9, Cap Roman 3, p. 9. See also Goth Farbinal, Volume Roman 2, p. 251. Descartes came far nearer the true philosophy of the iridal colors. He found that a similar series of colors was produced by refraction of light bounded by shade, through a prism, and he rightly inferred that neither the curvature of the surface of the drops of water, nor the reflection, nor the repetition of refraction, were necessary to the generation of such colors. In further examining the course of the rays, he approaches very near to the true conception of the case, and we are led to believe that he might have anticipated Newton in his discovery of the unequal refrangibility of different colors, if it had been possible for him to reason any otherwise than in the terms and notions of his preconceived hypotheses. The conclusion which he draws is that the particles of the subtile matter which transmit the action of light endeavor to rotate with so great a force and impetus that they cannot move in a straight line, whence comes refraction, and that those particles which endeavor to revolve much more strongly produce a red color, those which endeavor to move only a little more strongly produce yellow. Here we have a clear perception that colors and unequal refraction are connected, though the cause of refraction is expressed by a gratuitous hypothesis. And we may add that he applies this notion rightly, so far as he explains himself, to account for the colors of the rainbow. It appears to me that Newton and others have done Descartes injustice in ascribing to de Dominis the true theory of the rainbow. There are two main points of this theory, namely, the showing that a bright circular band of a certain definite diameter arises from the 60 great intensity of the light returned at a certain angle, and the referring the different colors to the different quantity of the refraction, and both these steps appear indubitably to be the discoveries of Descartes. And he informs us that these discoveries were not made without some exertion of thought. At first, he says, I doubted whether the iridal colors were produced in the same way as those in the prism, but at last, taking my pen and carefully calculating the course of the rays which fell on each part of the drop, I found that many more come at an angle of 41 degrees than either at a greater or a less angle. So that there is a bright bow terminated by a shade, and hence the colors are the same as those produced through a prism. The subject was left nearly in the same state, in the work of Grimaldi, Physico-Mathesius, de Lumine, Coloribus et Irid, published at Bologna in 1665. There is in this work a constant reference to numerous experiments and a systematic exposition of the science in an improved state. The author's calculations concerning the rainbow are put in the same form as those of Descartes, but he is further from seizing the true principle on which its coloration depends. He rightly groups together a number of experiments in which colors arise from refraction, and explains them by saying that the color is brighter where the light is denser, and the light is denser on the side from which the refraction turns the ray, because the increments of refraction are greater in the rays that are more inclined. This way of treating the question might be made to give a sort of explanation of most of the facts, but is much more erroneous than a development of Descartes's view would have been. At length, in 1672, Newton gave the true explanation of the facts, namely, that light consists of rays of different colors and different refrangibility. This now appears to us so obvious a mode of interpreting the phenomena that we can hardly understand how they can be conceived in any other manner. But yet the impression which this discovery made, both upon Newton and upon his contemporaries, shows how remote it was from the then accepted opinions. There appears to have been a general persuasion that the coloration was produced, not by any peculiarity in the law of refraction itself, but by some collateral circumstance, some dispersion or variation of density of the light, in addition to the refraction. Newton's discovery consisted in 61 teaching distinctly that the law of refraction was to be applied, not to the beam of light in general, but to the colors in particular. When Newton produced a bright spot on the wall of his chamber, by admitting the sun's light through a small hole in his window shutter and making it pass through a prism, he expected the image to be round. Which, of course, it would have been if the colors had been produced by an equal dispersion in all directions. But to his surprise, he saw the image, or spectrum, 5 times as long as it was broad. He found that no consideration of the different thickness of the glass, the possible unevenness of its surface, or the different angles of rays proceeding from the two sides of the sun, could be the cause of this shape. He found, also, that the rays did not go from the prism to the image in curves. He was then convinced that the different colors were refracted separately and at different angles, and he confirmed this opinion by transmitting and refracting the rays of each color separately. The experiments are so easy and common, and Newton's interpretation of them so simple and evident, that we might have expected it to receive general assent. Indeed, as we have shown, Descartes had already been led very near the same point. In fact, Newton's opinions were not long in obtaining general acceptance, but they met with enough of cavil and misapprehension to annoy extremely the discoverer, whose clear views and quiet temper made him impatient alike of stupidity and of contentiousness. We need not dwell long on the early objections which were made to Newton's doctrine. A Jesuit, of the name of Ignatius Pardies, professor at Clermont, at first attempted to account for the elongation of the image by the difference of the angles made by the rays from the two edges of the sun, which would produce a difference in the amount of refraction of the two borders. But when Newton pointed out the calculations which showed the insufficiency of this explanation, he withdrew his opposition. Another more pertinacious opponent appeared in Francis Linus, a physician of Liege, who maintained that having tried the experiment, he found the sun's image when the sky was clear to be round and not oblong, and he ascribed the elongation noticed by Newton to the effect of clouds. Newton for some time refused to reply to this contradiction of his assertions, though obstinately persisted in, and his answer was at last sent just about the time of Linus's death in 1675. But Gascoigne, a friend of Linus, still maintained that he and others had seen what the Dutch physician had described. And Newton, who was pleased with the candor of 62 Gascoigne's letter, suggested that the Dutch experimenters might have taken one of the images reflected from the surfaces of the prism, of which there are several, instead of the proper refracted one. By the aid of this hint, Lucas of Liege repeated Newton's experiments and obtained Newton's result, except that he never could obtain a spectrum whose length was more than 3.5 times its breadth. Newton, on his side, persisted in asserting that the image would be 5 times as long as it was broad if the experiment were properly made. It is curious that he should have been so confident of this, as to conceive himself certain that such would be the result in all cases. We now know that the dispersion, and consequently the length, of the spectrum is very different for different kinds of glass, and it is very probable that the Dutch prism was really less dispersive than the English one. The erroneous assumption which Newton made in this instance, he held by to the last, and was thus prevented from making the discovery of which we have next to speak. Newton was attacked by persons of more importance than those we have yet mentioned, namely Hooke and Huygens. These philosophers, however, did not object so much to the laws of refraction of different colors as to some expressions used by Newton, which they conceived conveyed false notions respecting the composition and nature of light. Newton had asserted that all the different colors are of distinct kinds, and that, by their composition, they form white light. This is true of colors as far as their analysis and composition by refraction are concerned. But Hooke maintained that all natural colors are produced by various combinations of two primary ones, red and violet, and Huygens held a similar doctrine, taking, however, yellow and blue for his basis. Newton answers that such compositions as they speak of are not compositions of simple colors in his sense of the expressions. These writers also had both of them adopted an opinion that light consisted in vibrations, and objected to Newton that his language was erroneous, as involving the hypothesis that light was a body. Newton appears to have had a horror of the word hypothesis, and protests against its being supposed that his theory rests on such a foundation. Note 22/9, Brewster's Newton, p. 54. Phil, trans. Roman 8, 5084, 6086. The doctrine of the unequal refrangibility of different rays is clearly exemplified in the effects of lenses, which produce images more or 63, less bordered with color, in consequence of this property. The improvement of telescopes was, in Newton's time, the great practical motive for aiming at the improvement of theoretical optics. Newton's theory showed why telescopes were imperfect, namely, in consequence of the different refraction of different colors, which produces a chromatic aberration. And the theory was confirmed by the circumstances of such imperfections. The false opinion of which we have already spoken, that the dispersion must be the same when the refraction is the same, led him to believe that the imperfection was insurmountable, that achromatic refraction could not be obtained. And this view made him turn his attention to the construction of reflecting instead of refracting telescopes. But the rectification of Newton's error was a further confirmation of the general truth of his principles in other respects. And since that time, the soundness of the Newtonian law of refraction has hardly been questioned among physical philosophers. It has, however, in modern times, been very vehemently controverted in a quarter from which we might not readily have expected a detailed discussion on such a subject. The celebrated Goethe has written a work on the doctrine of colors, Farbenlehre, Tübingen, 1810, one main purpose of which is to represent Newton's opinions and the work in which they are formally published. His optics, as utterly false and mistaken, and capable of being assented to only by the most blind and obstinate prejudice. Those who are acquainted with the extent to which such an opinion, promulgated by Goethe, was likely to be widely adopted in Germany, will not be surprised that similar language is used by other writers of that nation. Thus Schelling says, Newton's optics is the greatest proof of the possibility of a whole structure of fallacies, which, in all its parts, is founded upon observation and experiment. Goethe, however, does not concede even so much to Newton's work. He goes over a large portion of it, page by page, quarreling with the experiments, diagrams, reasoning, and language without intermission, and holds that it is not reconcilable with the most simple facts. He declares that the first time he looked through a prism, he saw the white walls of the room still look white, and though alone, I pronounced, as by an instinct, that the Newtonian doctrine is false. We need not here point out how inconsistent with the Newtonian doctrine it was to expect, as Goethe expected, that the wall should be all overcolored various colors. 64. Goethe not only adopted and strenuously maintained the opinion that the Newtonian theory was false, but he framed a system of his own to explain the phenomena of color. As a matter of curiosity, it may be worth our while to state the nature of this system. Although undoubtedly it forms no part of the progress of physical science, Goethe's views are, in fact, little different from those of Aristotle and Antonio de Dominis, though more completely and systematically developed. According to him, colors arise when we see through a dim medium, ein trubs Mittel. Light in itself is colorless, but if it be seen through a somewhat dim medium, it appears yellow. If the dimness of the medium increases, or if its depth be augmented, we see the light gradually assume a yellow-red color, which finally is heightened to a ruby red. On the other hand, if darkness is seen through a dim medium which is illuminated by a light falling on it, a blue color is seen, which becomes clearer and paler, the more the dimness of the medium increases, and darker and fuller, as the medium becomes more transparent. And when we come to the smallest degree of the purest dimness, we see the most perfect violet. In addition to this doctrine of the dim medium, we have a second principle asserted concerning refraction. In a vast variety of cases, images are accompanied by accessory images, as when we see bright objects in a looking glass. Now, when an image is displaced by refraction, the displacement is not complete, clear and sharp, but incomplete, so that there is an accessory image along with the principal one. From these principles, the colors produced by refraction in the image of a bright object on a dark ground are at once derivable. The accessory image is semi-transparent, and hence that border of it which is pushed forwards is drawn from the dark over the bright, and there the yellow appears. On the other hand, where the clear border laps over the dark ground, the blue is seen. And hence we easily see that the image must appear red and yellow at one end, and blue and violet at the other. We need not explain this system further, or attempt to show how vague and loose, as well as baseless, are the notions and modes of conception which it introduces. Perhaps it is not difficult to point out the peculiarities in God's intellectual character, which led to his singularly unphilosophical views on this subject. One important, 65, circumstance is that he appears, like many persons in whom the poetical imagination is very active, to have been destitute of the talent and the habit of geometrical thought. In all probability, he never apprehended clearly and steadily those relations of position on which the Newtonian doctrine depends. Another cause of his inability to accept the doctrine probably was that he had conceived the composition of colors in some way altogether different from that which Newton understands by composition. What God expected to see, we cannot clearly collect, but we know, from his own statement, that his intention of experimenting with a prism arose from his speculations on the roles of coloring in pictures, and we can easily see that any notion of the composition of colors which such researches would suggest would require to be laid aside before he could understand Newton's theory of the composition of light. Other objections to Newton's theory, of a kind very different, have been recently made by that eminent master of optical science, Sir David Brewster. He contests Newton's opinion that the colored rays into which light is separated by refraction are altogether simple and homogeneous, and incapable of being further analyzed and modified. For he finds that by passing such rays through colored media, as blue glass for instance, they are not only absorbed and transmitted in very various degrees, but that some of them have their color altered, which effect he conceives as a further analysis of the rays, one component color being absorbed and the other transmitted. And on this subject, we can only say, as we have before said, that Newton has incontestably and completely established his doctrine, so far as analysis and decomposition by refraction are concerned. But that with regard to any other analysis, which absorbing media or other agents may produce, we have no right from his experiments to assert that the colors of the spectrum are incapable of such decomposition. The whole subject of the colors of objects, both opaque and transparent, is still in obscurity. Newton's conjectures concerning the causes of the colors of natural bodies appear to help us little, and his opinions on that subject are to be separated altogether from the important step which he made in optical science, by the establishment of the true doctrine of refractive dispersion. Note 30/9. This latter fact has, however, been denied by other experimenters. After a careful reconsideration of Sir D. Brewster's asserted analysis of the solar light into three colors by means of 66 absorbing media, I cannot consider that he has established his point as an exception to Newton's doctrine. In the first place, the analysis of light into three colors appears to be quite arbitrary, granting all his experimental facts. I do not see why, using other media, he might not just as well have obtained other elementary colors. In the next place, this cannot be called an analysis in the same sense as Newton's analysis, except the relation between the two is shown. Is it meant that Newton's experiments prove nothing, or is Newton's conclusion allowed to be true of light which has not been analyzed by absorption? And where are we to find such light, since the atmosphere absorbs? But I must add, in the third place, that with a very sincere admiration of Sir D. Brewster's skill as an experimenter, I think his experiment requires not only limitation, but confirmation by other experimenters. Mr. Airy repeated the experiments with about 30 different absorbing substances and could not satisfy himself that in any case they changed the color of a ray of given refractive power. These experiments were described by him at a meeting of the Cambridge Philosophical Society. We now proceed to the corrections, which the next generation introduced into the details of this doctrine. Chapter 4. Discovery of achromatism. The discovery that the laws of refractive dispersion of different substances were such as to allow of combinations which neutralize the dispersion without neutralizing the refraction, is one which has hitherto been of more value to art than to science. The property has no definite bearing, which has yet been satisfactorily explained, upon the theory of light, but it is of the greatest importance in its application to the construction of telescopes, and it excited the more notice in consequence of the prejudices and difficulties which for a time retarded the discovery. Newton conceived that he had proved by experiment that light, 67, is white after refraction, when the emergent rays are parallel to the incident and in no other case. If this were so, the production of colorless images by refracting media would be impossible, and such, in deference to Newton's great authority, was for some time the general persuasion. Euler observed that a combination of lenses which does not color the image must be possible, since we have an example of such a combination in the human eye, and he investigated mathematically the conditions requisite for such a result. Klingenstierna, a Swedish mathematician, also showed that Newton's rule could not be universally true. Finally, John Dalland, in 1757, repeated Newton's experiment and obtained an opposite result. He found that when an object was seen through two prisms, one of glass and one of water, of such angles that it did not appear displaced by refraction, it was colored. Hence it followed that without being colored, the rays might be made to undergo refraction, and that thus, substituting lenses for prisms, a combination might be formed, which should produce an image without coloring it and make the construction of an achromatic telescope possible. Euler at first hesitated to confide in Dalland's experiments, but he was assured of their correctness by Clairaut, who had throughout paid great attention to the subject. And those two great mathematicians, as well as D'Alembert, proceeded to investigate mathematical formulae which might be useful in the application of the discovery. The remainder of the deductions, which were founded upon the laws of dispersion of various refractive substances, belongs rather to the history of art than of science. Dalland used at first for his achromatic object glass a lens of crown glass and one of flint glass. He afterwards employed two lenses of the former substance, including between them one of the latter, adjusting the curvatures of his lenses in such a way as to correct the imperfections arising from the spherical form of the glasses, as well as the fault of color. Afterwards, Blair used fluid media along with glass lenses in order to produce improved object glasses. This has more recently been done in another form by Mr. Barlow. The inductive laws of refraction being established, their results have been deduced by various mathematicians, as Sir J. Herschel and Professor Airy among ourselves, who have simplified and extended the investigation of the formulae, which determine the best combination of lenses in the object glasses and eyeglasses of 68 telescopes, both with reference to spherical and to chromatic aberrations. According to Dalland's discovery, the colored spectra produced by prisms of two substances, as flint glass and crown glass, would be of the same length when the refraction was different. But a question then occurred. When the whole distance from the red to the violet in one spectrum was the same as the whole distance in the other, were the intermediate colors, yellow, green, and C, in corresponding places in the two? This point also could not be determined any otherwise than by experiment. It appeared that such a correspondence did not exist, and therefore, when the extreme colors were corrected by combinations of the different media, there still remained an uncorrected residue of color arising from the rest of the spectrum. This defect was a consequence of the property that the spectra belonging to different media were not divided in the same ratio by the same colors, and was hence termed the irrationality of the spectrum. By using 3 prisms, or 3 lenses, 3 colors may be made to coincide instead of 2, and the effects of this irrationality greatly diminished. For the reasons already mentioned, we do not pursue this subject further, but turn to those optical facts which finally led to a great and comprehensive theory. Note 35/9. The discovery of the fixed lines in the spectrum by Wollaston and Fraunhofer has more recently supplied the means of determining, with extreme accuracy, the corresponding portions of the spectrum in different refracting substances. Mr. Chester Morehall of Morehall in Essex is said to have been led by the study of the human eye, which he conceived to be achromatic, to construct achromatic telescopes as early as 1729. Mr. Hall, however, kept his invention a secret. David Gregory, in his Catoptrics, 1713, had suggested that it would perhaps be an improvement of telescopes if, in imitation of the human eye, the object glass were composed of different media. Sic. Brit. Art. Optics. It is said that Clairaut first discovered the irrationality of the colored spaces in the spectrum. In consequence of this irrationality, it follows that when two refracting media are so combined as to correct each other's extreme dispersion, the separation of the red and violet rays. This first step of correction still leaves a residue of 69 coloration arising from the unequal dispersion of the intermediate rays, the green and C. These outstanding colors, as they were termed by Professor Robison, form the residual or secondary spectrum. Dr. Blair, by very ingenious devices, succeeded in producing an object glass, corrected by a fluid lens, in which this aberration of color was completely corrected, and which performed wonderfully well. The dispersion produced by a prism may be corrected by another prism of the same substance and of a different angle. In this case, also, there is an irrationality in the colored spaces, which prevents the correction of color from being complete, and hence a new residuary spectrum, which has been called the tertiary spectrum, by Sir David Brewster, who first noticed it. I have omitted, in the notice of discoveries respecting the spectrum, many remarkable trains of experimental research, and especially the investigations respecting the power of various media to absorb the light of different parts of the spectrum, prosecuted by Sir David Brewster with extraordinary skill and sagacity. The observations are referred to in Chapter 3. Sir John Herschel, Prof. Miller, Mr. Daniel, Dr. Faraday, and Mr. Talbot have also contributed to this part of our knowledge. Chapter 5. Discovery of the laws of double refraction. The laws of refraction which we have hitherto described were simple and uniform, and had a symmetrical reference to the surface of the refracting medium. It appeared strange to men, when their attention was drawn to a class of phenomena in which this symmetry was wanting, and in which a refraction took place which was not even in the plane of incidence. The subject was not unworthy the notice and admiration it attracted, for the prosecution of it ended in the discovery of the general laws of light. The phenomena of which I now speak are those exhibited by various kinds of crystalline bodies, but observed for a long time in one kind only, namely the rhombohedral calcspar, or, as it was usually termed, from the country which supplied the largest and clearest crystals, Iceland's spar. These 70 rhombohedral crystals are usually very smooth and transparent, and often of considerable size, and it was observed on looking through them that all objects appeared double. The phenomena, even as early as 1669, had been considered so curious that Erasmus Bartholin published a work upon them at Copenhagen, Experimenta Crystalli Islandici, Hafnii, 1669. He analyzed the phenomena into their laws, so far as to discover that one of the two images was produced by refraction after the usual rule, and the other by an unusual refraction. This latter refraction Bartholin found to vary in different positions, to be regulated by a line parallel to the sides of the rhombohedron, and to be greatest in the direction of a line bisecting two of the angles of the rhombic face of the crystal. These rules were exact as far as they went, and when we consider how geometrically complex the law is, which really regulates the unusual or extraordinary refraction, that Newton altogether mistook it, and that it was not verified till the experiments of Hoy and Wollaston in our own time, we might expect that it would not be soon or easily detected. But Huygens possessed a key to the secret, in the theory, which he had devised, of the propagation of light by undulations, and which he conceived with perfect distinctness and correctness, so far as its application to these phenomena is concerned. Hence he was enabled to lay down the law of the phenomena, the only part of his discovery which we have here to consider, with a precision and success which excited deserved admiration, when the subject, at a much later period, regained its due share of attention. His treatise was written in 1678, but not published till 1690. The laws of the ordinary and the extraordinary refraction in Iceland's spar are related to each other. They are, in fact, similar constructions made in the one case by means of an imaginary sphere, in the other by means of a spheroid. The spheroid being of such oblateness as to suit the rhombohedral form of the crystal, and the axis of the spheroid being the axis of symmetry of the crystal. Huygens followed this general conception into particular positions and conditions, and thus obtained rules which he compared with observation, for cutting the crystal and transmitting the rays in various manners. I have examined in detail, says he, the properties of the 71 extraordinary refraction of this crystal, to see if each phenomenon which is deduced from theory would agree with what is really observed. And this being so, it is no slight proof of the truth of our suppositions and principles, but what I am going to add here confirms them still more wonderfully. That is, the different modes of cutting this crystal, in which the surfaces produced give rise to refractions exactly such as they ought to be, and as I had foreseen them, according to the preceding theory. Note 38/9, see Mazur's Tracts on Optics, p. 250, or Huygens tr. Sur l'Homme, ch. v. Art, 43. Statements of this kind, coming from a philosopher like Huygens, were entitled to great confidence. Newton, however, appears not to have noticed or to have disregarded them. In his Optics, he gives a rule for the extraordinary refraction of Iceland's spar which is altogether erroneous, without assigning any reason for rejecting the law published by Huygens, and, so far as appears, without having made any experiments of his own. The Huygenian doctrine of double refraction fell, along with his theory of undulations, into temporary neglect, of which we shall have hereafter to speak. But in 1788, Hoy showed that Huygens's rule agreed much better than Newton's with the phenomena, and in 1802, Wollaston, applying a method of his own for measuring refraction, came to the same result. He made, says Young, a number of accurate experiments with an apparatus singularly well calculated to examine the phenomena, but could find no general principle to connect them until the work of Huygens was pointed out to him. In 1808, the subject of double refraction was proposed as a prize question by the French Institute, and Malus, whose memoir obtained the prize, says, I began by observing and measuring a long series of phenomena on natural and artificial faces of Iceland's spar. Then, testing by means of these observations the different laws proposed up to the present time by physical writers, I was struck with the admirable agreement of the law of Huygens with the phenomena, and I was soon convinced that it is really the law of nature. Pursuing the consequences of the law, he found that it satisfied phenomena which Huygens himself had not observed. From this time, then, the truth of the Huygenian law was universally allowed, and soon afterwards, the theory by which it had been suggested was generally received. The property of double refraction had been first studied only in Iceland's spar, in which it is very obvious. The same property belongs, 72 though less conspicuously, to many other kinds of crystals. Huygens had noticed the same fact in rock crystal, and Malus found it to belong to a large list of bodies besides. For instance, aragonite, sulfate of lime, of baryta, of strontia, of iron, carbonate of lead, zircon, corundum, cymophane, emerald, euclase, felspar, mesotype, peridote, sulfur, and melite. Attempts were made with imperfect success to reduce all these to the law which had been established for Iceland's spar. In the first instance, Malus took for granted that the extraordinary refraction depended always upon an oblate spheroid. But M. Biot pointed out a distinction between two classes of crystals, in which this spheroid was oblong and oblate respectively, and these he called attractive and repulsive crystals. With this correction, the law could be extended to a considerable number of cases, but it was afterwards proved by Sir D. Brewster's discoveries that even in this form, it belonged only to substances of which the crystallization has relation to a single axis of symmetry, as the rhombohedron or the square pyramid. In other cases, as the rhombic prism, in which the form, considered with reference to its crystalline symmetry, is biaxial, the law is much more complicated. In that case, the sphere and the spheroid, which are used in the construction for uniaxial crystals, transform themselves into the two successful convolutions of a single continuous curved surface. Neither of the two rays follows the law of ordinary refraction, and the formula which determines their position is very complex. It is, however, capable of being tested by measures of the refractions of crystals cut in a peculiar manner for the purpose, and this was done by Fresnel and Arago. But this complex law of double refraction was only discovered through the aid of the theory of a luminiferous ether, and therefore we must now return to the other facts which led to such a theory. Chapter 6. Discovery of the laws of polarization. If the extraordinary refraction of Iceland's spar had appeared strange, another phenomenon was soon noticed in the same 73 substance, which appeared stranger still, and which in the sequel was found to be no less important. I speak of the facts which were afterwards described under the term polarization. Huygens was the discoverer of this class of facts. At the end of the treatise which we have already quoted, he says, "Before I quit the subject of this crystal, I will add one other marvelous phenomenon, which I have discovered since writing the above. For though hitherto I have not been able to find out its cause, I will not, on that account, omit pointing it out, that I may give occasion to others to examine it." He then states the phenomena, which are that when two rhombohedrons of Iceland spar are in parallel positions, a ray doubly refracted by the first is not further divided when it falls on the second. The ordinarily refracted ray is ordinarily refracted only, and the extraordinary ray is only extraordinarily refracted by the second crystal, neither ray being doubly refracted. The same is still the case if the two crystals have their principal planes parallel, though they themselves are not parallel. But if the principal plane of the second crystal be perpendicular to that of the first, the reverse of what has been described takes place. The ordinarily refracted ray of the first crystal suffers, at the second, extraordinary refraction only, and the extraordinary ray of the first suffers ordinary refraction only at the second. Thus, in each of these positions, the double refraction of each ray at the second crystal is reduced to single refraction, though in a different manner in the two cases. But in any other position of the crystals, each ray produced by the first is doubly refracted by the second, so as to produce four rays. A step in the right conception of these phenomena was made by Newton in the second edition of his Optics, 1717. He represented them as resulting from this, that the rays of light have sides, and that they undergo the ordinary or extraordinary refraction, according as these sides are parallel to the principal plane of the crystal, or at right angles to it, query 26. In this way, it is clear that those rays which, in the first crystal, had been selected for extraordinary refraction, because their sides were perpendicular to the principal plane, would all suffer extraordinary refraction at the second crystal for the same reason, if its principal plane were parallel to that of the first, and would all suffer ordinary refraction if the principal plane of the second crystal were perpendicular to that of the first, and 74 consequently parallel to the sides of the refracted ray. This view of the subject includes some of the leading features of the case, but still leaves several considerable difficulties. No material advance was made in the subject till it was taken up by Malus, along with the other circumstances of double refraction, about 100 years afterwards. He verified what had been observed by Huygens and Newton on the subject of the variations which light thus exhibits, but he discovered that this modification, in virtue of which light undergoes the ordinary, or the extraordinary, refraction, according to the position of the plane of the crystal, may be impressed upon it many other ways. One part of this discovery was made accidentally. In 1808, Malus happened to be observing the light of the setting sun, reflected from the windows of the Luxembourg through a rhombohedron of Iceland's spar, and he observed that in turning round the crystal, the two images varied in their intensity. Neither of the images completely vanished, because the light from the windows was not properly modified, or, to use the term which Malus soon adopted, was not completely polarized. The complete polarization of light by reflection from glass, or any other transparent substance, was found to take place at a certain definite angle, different for each substance. It was found also that in all crystals in which double refraction occurred, the separation of the refracted rays was accompanied by polarization. The two rays, the ordinary and the extraordinary, being always polarized oppositely, that is, in planes at right angles to each other. The term poles, used by Malus, conveyed nearly the same notion as the term sides which had been employed by Newton, with the additional conception of a property which appeared or disappeared according as the poles of the particles were or were not in a certain direction. A property thus resembling the polarity of magnetic bodies. When a spot of polarized light is looked at through a transparent crystal of Iceland spar, each of the two images produced by the double refraction varies in brightness as the crystal is turned round. If, for the sake of example, we suppose the crystal to be turned round in the direction of the points of the compass, N, E, S, W, and if one image be brightest when the crystal marks N and S, it will disappear when the crystal marks E and W. And on the contrary, the second image will vanish when the crystal marks N and S, 75, and will be brightest when the crystal marks E and W. The first of these images is polarized in the plane NS passing through the ray, and the second in the plane U perpendicular to the other. And these rays are oppositely polarized. It was further found that whether the ray were polarized by reflection from glass, or from water, or by double refraction, the modification of light so produced, or the nature of the polarization, was identical in all these cases, that the alternatives of ordinary and extraordinary refraction and non-refraction were the same by whatever crystal they were tested, or in whatever manner the polarization had been impressed upon the light. In short, that the property, when once acquired, was independent of everything except the sides or poles of the ray. And thus, in 1811, the term polarization was introduced. This being the state of the subject, it became an obvious question, by what other means, and according to what laws this property was communicated. It was found that some crystals, instead of giving, by double refraction, two images oppositely polarized, give a single polarized image. This property was discovered in the agate by Sir D. Brewster and in tourmaline by M. Biot and Dr. Seebeck. The latter mineral became, in consequence, a very convenient part of the apparatus used in such observations. Various peculiarities bearing upon this subject were detected by different experimenters. It was in a short time discovered that light might be polarized by refraction, as well as by reflection, at the surface of uncrystallized bodies, as glass, the plane of polarization being perpendicular to the plane of refraction. Further, that when a portion of a ray of light was polarized by reflection, a corresponding portion was polarized by transmission, the planes of the two polarizations being at right angles to each other. It was found also that the polarization which was incomplete with a single plate, either by reflection or refraction, might be made more and more complete by increasing the number of plates. Among an accumulation of phenomena like this, it is our business to inquire what general laws were discovered. To make such discoveries without possessing the general theory of the facts required no ordinary sagacity and good fortune. Yet several laws were detected at this stage of the subject. Malus, in 1811, obtained the important generalization that, whenever we obtain, by any means, a polarized ray of light, we produce also another ray, polarized in a contrary, 76 direction. Thus, when reflection gives a polarized ray, the companion ray is refracted polarized oppositely, along with a quantity of unpolarized light. And we must particularly notice Sir D. Brewster's rule for the polarizing angle of different bodies. Malus had said that the angle of reflection from transparent bodies, which most completely polarizes the reflected ray, does not follow any discoverable rule with regard to the order of refractive or dispersive powers of the substances. Yet the rule was in reality very simple. In 1815, Sir D. Brewster stated as the law, which in all cases determines this angle, that the index of refraction is the tangent of the angle of polarization. It follows from this that the polarization takes place when the reflected and refracted rays are at right angles to each other. This simple and elegant rule has been fully confirmed by all subsequent observations, as by those of Biot and Seebeck, and must be considered one of the happiest and most important discoveries of the laws of phenomena in optics. The rule for polarization by one reflection being thus discovered, tentative formulae were proposed by Sir D. Brewster and M. Biot, for the cases in which several reflections or refractions take place. Fresnel also in 1817 and 1818 traced the effect of reflection in modifying the direction of polarization, which Malus had done inaccurately in 1810. But the complexity of the subject made all such attempts extremely precarious, till the theory of the phenomena was understood, a period which now comes under notice. The laws which we have spoken of were important materials for the establishment of the theory, but in the meantime, its progress at first had been more forwarded by some other classes of facts, of a different kind, and of a longer-standing notoriety, to which we must now turn our attention. Chapter 7. Discovery of the laws of the colors of thin plates. The facts which we have now to consider are remarkable, inasmuch as the colors are produced merely by the smallness of dimensions of the bodies employed. The light is not analyzed by any peculiar, 77, property of the substances, but dissected by the minuteness of their parts. On this account, these phenomena give very important indications of the real structure of light, and at an early period suggested views which are, in a great measure, just. Hooke appears to be the first person who made any progress in discovering the laws of the colors of thin plates. In his Micrographia, printed by the Royal Society in 1664, he describes, in a detailed and systematic manner, several phenomena of this kind, which he calls fantastical colors. He examined them in Muscovy glass or mica, a transparent mineral which is capable of being split into the exceedingly thin films which are requisite for such colors. He noticed them also in the fissures of the same substance, in bubbles blown of water, rosin, gum, glass, in the films on the surface of tempered steel, between two plain pieces of glass, and in other cases. He perceived also that the production of each color required a plate of determinate thickness, and he employed this circumstance as one of the grounds of his theory of light. Newton took up the subject where Hooke had left it, and followed it out with his accustomed skill and clearness in his discourse on light and colors communicated to the Royal Society in 1675. He determined, what Hooke had not ascertained, the thickness of the film which was requisite for the production of each color, and in this way explained, in a complete and admirable manner, the colored rings which occur when two lenses are pressed together, and the scale of color which the rings follow. A step of the more consequence, as the same scale occurs in many other optical phenomena. It is not our business here to state the hypothesis with regard to the properties of light which Newton founded on these facts, the fits of easy transmission and reflection. We shall see hereafter that his attempted induction was imperfect, and his endeavor to account, by means of the laws of thin plates, for the colors of natural bodies is altogether unsatisfactory. But notwithstanding these failures in the speculations on this subject, he did make in it some very important steps, for he clearly ascertained that when the thickness of the plate was about 178,000th of an inch, or 3 times, 5 times, 7 times that magnitude, there was a bright color produced. But blackness, when the thickness was exactly intermediate between those magnitudes. He found also that the thicknesses which gave red and 78 violet were as 14 to 9, and the intermediate colors of course corresponded to intermediate thicknesses, and therefore, in his apparatus, consisting of 2 lenses pressed together, appeared as rings of intermediate sizes. His mode of confirming the rule, by throwing upon this apparatus differently colored homogeneous light, is striking and elegant. It was very pleasant, he says, to see the rings gradually swell and contract as the color of the light was changed. It is not necessary to enter further into the detail of these phenomena, or to notice the rings seen by transmission and other circumstances. The important step made by Newton in this matter was the showing that the rays of light, in these experiments, as they pass onwards go periodically through certain cycles of modification, each period occupying nearly the small fraction of an inch mentioned above, and this interval being different for different colors. Although Newton did not correctly disentangle the conditions under which this periodical character is manifestly disclosed, the discovery that, under some circumstances, such a periodical character does exist was likely to influence, and did influence materially and beneficially, the subsequent progress of optics towards a connected theory. We must now trace this progress, but before we proceed to this task, we will briefly notice a number of optical phenomena which had been collected, and which waited for the touch of sound theory to introduce among them that rule and order which mere observation had sought for in vain. Chapter 8. Attempts to discover the laws of other phenomena. The phenomena which result from optical combinations, even of a comparatively simple nature, are extremely complex. The theory which is now known accounts for these results with the most curious exactness and points out the laws which pervade the apparent confusion. But without this key to the appearances, it was scarcely possible that any rule or order should be detected. The undertaking was of 79, the same kind as it would have been, to discover all the inequalities of the moon's motion without the aid of the doctrine of gravity. We will enumerate some of the phenomena which thus employed and perplexed the cultivators of optics. The fringes of shadows were one of the most curious and noted of such classes of facts. These were first remarked by Grimaldi, 1665, and referred by him to a property of light which he called diffraction. When shadows are made in a dark room, by light admitted through a very small hole, these appearances are very conspicuous and beautiful. Hooke, in 1672, communicated similar observations to the Royal Society, as a new property of light not mentioned by any optical writer before, by which we see that he had not heard of Grimaldi's experiments. Newton, in his Optics, treats of the same phenomena, which he ascribes to the inflection of the rays of light. He asks, 3. Are not the rays of light, in passing by the edges and sides of bodies, bent several times backward and forward with a motion like that of an eel? And do not the 3 fringes of colored light in shadows arise from 3 such bendings? It is remarkable that Newton should not have noticed that it is impossible, in this way, to account for the facts, or even to express their laws, since the light which produces the fringes must, on this theory, be propagated, even after it leaves the neighborhood of the opaque body, in curves, and not in straight lines. Accordingly, all who have taken up Newton's notion of inflection have inevitably failed in giving anything like an intelligible and coherent character to these phenomena. This is, for example, the case with Mr. now Lord Brougham's attempts in the Philosophical Transactions for 1796. The same may be said of other experimenters, as Marin and Dufour, who attempted to explain the facts by supposing an atmosphere about the opaque body. Several authors, as Maraldi and Comparetti, repeated or varied these experiments in different ways. Note 50/9. Physicomathesis de lumine coloribus et irid, Bologna, 1665. Note 54/9. Observations optici de luz inflexa et coloribus, Padua, 1787. Newton had noticed certain rings of color produced by a glass speculum, which he called colors of thick plates, and which he attempted to connect with the colors of thin plates. His reasoning is by no means satisfactory, but it was of use by pointing out this as a case in which his fits, the small periods or cycles in the rays of light, of 80, which we have spoken, continued to occur for a considerable length of the ray. But other persons, attempting to repeat his experiments, confounded with them extraneous phenomena of other kinds, as the Duc de Chaulnes, who spread muslin before his mirror, and Dr. Herschel, who scattered hair powder before his. The colors produced by the muslin were those belonging to shadows of gratings, afterwards examined more successfully by Fraunhofer, when in possession of the theory. We may mention here also the colors which appear on finely striated surfaces and on mother-of-pearl, feathers, and similar substances. These had been examined by various persons, as Boyle, Mazias, Lord Brougham, but could still, at this period, be only looked upon as insulated and lawless facts. Chapter 9. Discovery of the laws of phenomena of dipolarized light. Besides the above-mentioned perplexing cases of colors produced by common light, cases of periodical colors produced by polarized light began to be discovered, and soon became numerous. In August 1811, M. Arago communicated to the Institute of France an account of colors seen by passing polarized light through mica, and analyzing it with a prism of Iceland spar. It is remarkable that the light which produced the colors in this case was the light polarized by the sky, a cause of polarization not previously known. The effect which the mica thus produced was termed depolarization, not a very happy term, since the effect is not the destruction of the polarization, but the combination of a new polarizing influence with the former. The word depolarization, which has since been proposed, is a much more appropriate expression. Several other curious phenomena of the same kind were observed in quartz and in flint glass. M. Arago was not able to reduce these phenomena to laws, but he had a full conviction of their value and ventures to class them with the great steps in 81, this part of optics. To Bartholin we owe the knowledge of double refraction, to Huygens that of the accompanying polarization, to Malus polarization by reflection, to Arago depolarization. Sir D. Brewster was at the same time engaged in a similar train of research, and made discoveries of the same nature, which, though not published till some time after those of Arago, were obtained without a knowledge of what had been done by him. Sir D. Brewster's treatise on New Philosophical Instruments, published in 1813, contains many curious experiments on the depolarizing properties of minerals. Both these observers noticed the changes of color which are produced by changes in the position of the ray, and the alternations of color in the two oppositely polarized images. And Sir D. Brewster discovered that, in topaz, the phenomena had a certain reference to lines which he called the neutral and depolarizing axes. M. Biot had endeavored to reduce the phenomena to a law, and had succeeded so far that he found that in the plates of sulfate of lime, the place of the tint, estimated in Newton's scale, see ante, chapter Roman 7, was as the square of the sine of the inclination. But the laws of these phenomena became much more obvious when they were observed by Sir D. Brewster with a larger field of view. He found that the colors of topaz, under the circumstances now described, exhibited themselves in the form of elliptical rings, crossed by a black bar, the most brilliant class of phenomena, as he justly says, in the whole range of optics. In 1814 also, Wollaston observed the circular rings with a black cross, produced by similar means in calcspar, and M. Biot in 1815 made the same observation. The rings in several of these cases were carefully measured by M. Biot and Sir D. Brewster, and a great mass of similar phenomena was discovered. These were added to by various persons, as M. Seebeck and Sir John Herschel. Note 57/9. The prism of Iceland spar produces the colors by separating the transmitted rays according to the laws of double refraction. Hence it is said to analyze the light. Sir D. Brewster, in 1818, discovered a general relation between the crystalline form and the optical properties, which gave an incalculable impulse and a new clearness to these researches. He found that there was a correspondence between the degree of symmetry of the optical phenomena and the crystalline form. Those crystals which are uniaxial in the crystallographical sense are also uniaxial in their optical properties and give circular rings. Those which are of other forms are, generally speaking, biaxial. They give oval and knotted isochromatic lines with two poles. He also discovered a rule for the tint at each point, 82, in such cases, and thus explained, so far as an empirical law of phenomena went, the curious and various forms of the colored curves. This law, when simplified by M. Biot, made the tint proportional to the product of the distances of the point from the two poles. In the following year, Sir J. Herschel confirmed this law by showing, from actual measurement, that the curve of the isochromatic lines in these cases was the curve termed the lemniscata, which has, for each point, the product of the distances from two fixed poles equal to a constant quantity. He also reduced to rule some other apparent anomalies in phenomena of the same class. M. Biot, too, gave a rule for the directions of the planes of polarization of the two rays produced by double refraction in biaxial crystals, a circumstance which has a close bearing upon the phenomena of depolarization. His rule was that the one plane of polarization bisects the dihedral angle formed by the two planes which pass through the optic axes, and that the other is perpendicular to such a plane. When, however, Fresnel had discovered from the theory the true laws of double refraction, it appeared that the above rule is inaccurate, although in a degree which observation could hardly detect without the aid of theory. There were still other classes of optical phenomena which attracted notice, especially those which are exhibited by plates of quartz cut perpendicular to the axis. M. Arago had observed, in 1811, that this substance produced a twist of the plane of polarization to the right or left hand, the amount of this twist being different for different colors, a result which was afterwards traced to a modification of light different both from common and from polarized light, and subsequently known as circular polarization. Sir J. Herschel had the good fortune and sagacity to discover that this peculiar kind of polarization in quartz was connected with an equally peculiar modification of crystallization. The plagiahedral faces which are seen, on some crystals, obliquely disposed, and, as it were, following each other round the crystal from left to right or from right to left. Sir J. Herschel found that the right-handed or left-handed character of the circular polarization corresponded, in all cases, to that of the crystal. In 1815, M. Biot, in his researches on the subject of circular polarization, was led to the unexpected and curious discovery that this 83 property, which seemed to require for its very conception a crystalline structure in the body, belonged nevertheless to several fluids and in different directions for different fluids. Oil of turpentine and an essential oil of laurel gave the plane of polarization a rotation to the left hand. Oil of citron, syrup of sugar, and a solution of camphor gave a rotation to the right hand. Soon after, the like discovery was made independently by Dr. Seebeck of Berlin. It will easily be supposed that all those brilliant phenomena could not be observed, and the laws of many of the phenomena discovered, without attempts on the part of philosophers to combine them all under the dominion of some wide and profound theory. Endeavors to ascend from such knowledge as we have spoken of to the general theory of light were, in fact, made at every stage of the subject, and with a success which at last won almost all suffrages. We are now arrived at the point at which we are called upon to trace the history of this theory, to pass from the laws of phenomena to their causes, from formal to physical optics. The undulatory theory of light, the only discovery which can stand by the side of the theory of universal gravitation, as a doctrine belonging to the same order, for its generality, its fertility, and its certainty, may properly be treated of with that ceremony which we have hitherto bestowed only on the great advances of astronomy. And I shall therefore now proceed to speak of the prelude to this epoch, the epoch itself, and its sequel, according to the form of the preceding book which treats of astronomy. I ought to have stated, in the beginning of this chapter, that Malus discovered the depolarization of white light in 1811. He found that a pencil of light which, being polarized, refused to be reflected by a surface properly placed, recovered its power of being reflected after being transmitted through certain crystals and other transparent bodies. Malus intended to pursue this subject, when his researches were terminated by his death, Feb. 7, 1812. M. Arago, about the same time, announced his important discovery of the depolarization of colors by crystals. I may add, to what is above said of M. Biot's discoveries respecting the circular polarizing power of fluids, that he pursued his researches so as to bring into view some most curious relations among the elements of bodies. It appeared that certain substances, as sugar of canes, had a right-handed effect, and certain other substances, as gum, a left-handed effect, and that the molecular value of this effect was not altered by dilution. It appeared also that a certain element of the 84 substance of fruits, which had been supposed to be gum, and which is changed into sugar by the operation of acids, is not gum, and has a very energetic right-handed effect. This substance M. Biot called dextrine, and he has since traced its effects into many highly curious and important results. 85. Physical Optics. Chapter 10. Prelude to the Epoch of Young and Fresnel. By physical optics we mean, as has already been stated, the theories which explain optical phenomena on mechanical principles. No such explanation could be given till true mechanical principles had been obtained, and, accordingly, we must date the commencement of the essays towards physical optics from Descartes, the founder of the modern mechanical philosophy. His hypothesis concerning light is that it consists of small particles emitted by the luminous body. He compares these particles to balls, and endeavors to explain, by means of this comparison, the laws of reflection and refraction. In order to account for the production of colors by refraction, he ascribes to these balls an alternating rotatory motion. This form of the emission theory was, like most of the physical speculations of its author, hasty and gratuitous, but was extensively accepted, like the rest of the Cartesian doctrines, in consequence of the love which men have for sweeping and simple dogmas and deductive reasonings from them. In a short time, however, the rival optical theory of undulations made its appearance. Hooke in his Micrographia, 1664, propounds it, upon occasion of his observations already noticed, chapter Roman 7, on the colors of thin plates. He there asserts light to consist in a quick, short, vibrating motion, and that it is propagated in a homogeneous medium, in such a way that every pulse or vibration of the luminous body will generate a sphere, which will continually increase and grow bigger, just after the same manner, though indefinitely swifter, as the waves or rings on the surface of water do swell into bigger and bigger circles about a point in it. He applies this to the explanation of refraction. 86, by supposing that the rays in a denser medium move more easily, and hence that the pulses become oblique. A far less satisfactory and consistent hypothesis than that of Huygens, of which we shall next have to speak. But Hooke has the merit of having also combined with his theory, though somewhat obscurely, the principle of interferences in the application which he makes of it to the colors of thin plates. Thus he supposes the light to be reflected at the first surface of such plates, and he adds, after 2 refractions and 1 reflection from the second surface, there is propagated a kind of fainter ray, which comes behind the other reflected pulse, so that hereby, the surfaces ob and f being so near together that the eye cannot discriminate them from one, this compound or duplicated pulse does produce on the retina the sensation of a yellow. The reason for the production of this particular color, in the case of which he here speaks, depends on his views concerning the kind of pulses appropriate to each color. And, for the same reason, when the thickness is different, he finds that the result will be a red or a green. This is a very remarkable anticipation of the explanation ultimately given of these colors. And we may observe that if Hooke could have measured the thickness of his thin plates, he could hardly have avoided making considerable progress in the doctrine of interferences. But the person who is generally, and with justice, looked upon as the great author of the undulatory theory, at the period now under notice, is Huygens, whose Traité de la Lumière, containing a development of his theory, was written in 1678, though not published till 1690. In this work he maintained, as Hooke had done, that light consists in undulations and expands itself spherically, nearly in the same manner as sound does. And he referred to the observations of Roemer on Jupiter's satellites, both to prove that this difference takes place successively and to show its exceeding swiftness. In order to trace the effect of an undulation, Huygens considers that every point of a wave diffuses its motion in all directions, and hence he draws the conclusion, so long looked upon as the turning point of the combat between the rival theories, that the light will not be diffused beyond the rectilinear space, when it passes through an aperture. For, says he, although the partial waves, produced by the particles comprised in the aperture, do diffuse themselves beyond the rectilinear space, these waves do not concur anywhere except in front of the 87 aperture. He rightly considers this observation as of the most essential value. This, he says, was not known by those who began to consider the waves of light, among whom are Mr. Hooke in his Micrography and Father Parties, who, in a treatise of which he showed me a part, and which he did not live to finish, had undertaken to prove, by these waves, the effects of reflection and refraction. But the principal foundation, which consists in the remark I have just made, was wanting in his demonstrations. By the help of this view, Huygens gave a perfectly satisfactory and correct explanation of the laws of reflection and refraction, and he also applied the same theory, as we have seen, to the double refraction of Iceland's spar with great sagacity and success. He conceived that in this crystal, besides the spherical waves, there might be others of a spheroidal form, the axis of the spheroid being symmetrically disposed with regard to the faces of the rhombohedron, for to these faces the optical phenomena are symmetrically related. He found that the position of the refracted ray, determined by such spheroidal undulations, would give an oblique refraction, which would coincide in its laws with the refraction observed in Iceland's spar. And, as we have stated, this coincidence was long after fully confirmed by other observers. Since Huygens, at this early period, expounded the undulatory theory with so much distinctness, and applied it with so much skill, it may be asked why we do not hold him up as the great author of the induction of undulations of light, the person who marks the epoch of the theory. To this we reply that though Huygens discovered strong presumptions in favor of the undulatory theory, it was not established till a later era, when the fringes of shadows, rightly understood, made the waves visible, and when the hypothesis which had been assumed to account for double refraction was found to contain also an explanation of polarization. It is then that this theory of light assumes its commanding form, and the persons who gave it this form we must make the great names of our narrative, without, however, denying the genius and merit of Huygens, who is, undoubtedly, the leading character in the prelude to the discovery. The undulatory theory, from this time to our own, was unfortunate in its career. It was by no means destitute of defenders, but these were not experimenters, and none of them thought of applying it to 88 Grimaldi's experiments on fringes, of which we have spoken a little while ago. And the great authority of the period, Newton, adopted the opposite hypothesis, that of emission, and gave it a currency among his followers which kept down the sounder theory for above a century. Newton's first disposition appears to have been by no means averse to the assumption of an ether as the vehicle of luminiferous undulations. When Hooke brought against his prismatic analysis of light some objections, founded on his own hypothetical notions, Newton, in his reply, said, "The hypothesis has a much greater affinity with his own hypothesis than he seems to be aware of, the vibrations of the ether being as useful and necessary in this as in his." This was in 1672, and we might produce, from Newton's writing, passages of the same kind, of a much later date. Indeed, it would seem that, to the last, Newton considered the assumption of an ether as highly probable, and its vibrations important parts of the phenomena of light. But he also introduced into his system the hypothesis of emission, and having followed this hypothesis into mathematical detail, while he has left all that concerns the ether in the form of queries and conjectures, the emission theory has naturally been treated as the leading part of his optical doctrines. The principal propositions of the Principia, which bear upon the question of optical theory, are those of the 14th section of the first book, in which the law of the signs in refraction is proved on the hypothesis that the particles of bodies act on light only at very small distances, and the proposition of the 8th section of the second book, in which it is pretended to be demonstrated that the motion propagated in a fluid must diverge when it has passed through an aperture. The former proposition shows that the law of refraction, an optical truth which mainly affected the choice of a theory, for about reflection there is no difficulty on any mechanical hypothesis, follows from the theory of emission. The latter proposition was intended to prove the inadmissibility of the rival hypothesis, that of undulations. As to the former point, the hypothetical explanation of refraction, on the assumptions there made, the conclusion is quite satisfactory. But the reasoning in the latter case, respecting the propagation of undulations, is certainly inconclusive and vague, and something better might the more reasonably have been expected, since Huygens had at least 89 endeavored to prove the opposite proposition. But supposing we leave these properties, the rectilinear course, the reflection, and the refraction of light, as problems in which neither theory has a decided advantage, what is the next material point? The colors of thin plates. Now, how does Newton's theory explain these? By a new and special supposition, that of fits of easy transmission and reflection. A supposition which, though it truly expresses these facts, is not borne out by any other phenomena. But passing over this, when we come to the peculiar laws of polarization in Iceland's spar, how does Newton's meet this? Again, by a special and new supposition that the rays of light have sides. Thus, we find no fresh evidence in favor of the emission hypothesis springing out of the fresh demands made upon it. It may be urged in reply that the same is true of the undulatory theory, and it must be allowed that, at the time of which we now speak, its superiority in this respect was not manifested, though Hooke, as we have seen, had caught a glimpse of the explanation which this theory supplies of the colors of thin plates. At a later period, Newton certainly seems to have been strongly disinclined to believe light to consist in undulations merely. Are not, he says, in question 28 of the Optics, all hypotheses erroneous, in which light is supposed to consist in pression or motion propagated through a fluid medium? The arguments which most weighed with him to produce this conviction appear to have been the one already mentioned that, on the undulatory hypothesis, undulations passing through an aperture would be diffused, and again his conviction that the properties of light, developed in various optical phenomena, depend not upon new modifications, but upon the original and unchangeable properties of the rays. Question 27. But yet, even in this state of his views, he was very far from abandoning the machinery of vibrations altogether. He is disposed to use such machinery to produce his fits of easy transmission. In his 17th query, he says, when a ray of light falls upon the surface of any pellucid body, and is there refracted or reflected, may not waves of vibrations or tremors be thereby excited in the refracting or reflecting medium at the point of incidence? And do not these vibrations overtake the rays of light, and by overtaking them successively, do they not put them into the fits of easy reflection and easy 90 transmission described above? Several of the other queries imply the same persuasion of the necessity for the assumption of an ether and its vibrations. And it might have been asked whether any good reason could be given for the hypothesis of an ether as a part of the mechanism of light, which would not be equally valid in favor of this being the whole of the mechanism, especially if it could be shown that nothing more was wanted to produce the results. The emission theory was, however, embraced in the most strenuous manner by the disciples of Newton. That propositions existed in the Principia which proceeded on this hypothesis was, with many of these persons, ground enough for adopting the doctrine, and it had also the advantage of being more ready of conception, for though the propagation of a wave is not very difficult to conceive, at least by a mathematician, the motion of a particle is still easier. On the other hand, the undulation theory was maintained by no less a person than Euler, and the war between the two opinions was carried on with great earnestness. The arguments on one side and on the other soon became trite and familiar, for no person explained any new class of facts by either theory. Thus it was urged by Euler against the system of emission that the perpetual emanation of light from the sun must have diminished the mass, that the stream of matter thus constantly flowing must affect the motions of the planets and comets, that the rays must disturb each other, that the passage of light through transparent bodies is, on this system, inconceivable. All such arguments were answered by representations of the exceeding minuteness and velocity of the matter of light. On the other hand, there was urged against the theory of waves, the favorite Newtonian argument, that on this theory the light passing through an aperture ought to be diffused, as sound is. It is curious that Euler does not make to this argument the reply which Huygens had made before. The fact really was that he was not aware of the true ground of the difference of the result in the cases of sound and light, namely, that any ordinary aperture bears an immense ratio to the length of an undulation of light, but does not bear a very great ratio to the length of an undulation of sound. The demonstrable consequence of this difference is that light darts through such an orifice in straight rays, while sound is diffused in all directions. Euler, not perceiving this difference, rested his answer mainly upon a circumstance by no means, 91, unimportant, that the partitions usually employed are not impermeable to sound, as opaque bodies are to light. He observes that the sound does not all come through the aperture, for we hear, though the aperture be stopped. These were the main original points of attack and defense, and they continued nearly the same for the whole of the last century. The same difficulties were over and over again proposed, and the same solutions given, much in the manner of the disputations of the schoolmen of the Middle Ages. The struggle being thus apparently balanced, the scale was naturally turned by the general ascendancy of the Newtonian doctrines, and the emission theory was the one most generally adopted. It was still more firmly established, in consequence of the turn generally taken by the scientific activity of the latter half of the 18th century. For while nothing was added to our knowledge of optical laws, the chemical effects of light were studied to a considerable extent by various inquirers, and the opinions at which these persons arrived, they found that they could express most readily, in consistency with the reigning chemical views, by assuming the materiality of light. It is, however, clear that no reasonings of the inevitably vague and doubtful character, which belong to these portions of chemistry, ought to be allowed to interfere with the steady and regular progress of induction and generalization, founded on relations of space and number, by which procedure the mechanical sciences are formed. We reject, therefore, all these chemical speculations as belonging to other subjects, and consider the history of optical theory as a blank, till we arrive at some very different events of which we have now to speak. 92. Note 74/9. As Scheele, Sell, Lavoisier, Deluc, Richter, Leonhardi, Gren, Gertner, Link, Hagen, Voigt, de la Metherie, Schurer, Dizet, Brugnatelli. See Fisher, Roman 7. p. 20. Chapter 11. Epoch of Young and Fresnel. Sect 1 Introduction. The man whose name must occupy the most distinguished place in the history of physical optics, in consequence of what he did in reviving and establishing the undulatory theory of light, is Dr. Thomas Young. He was born in 1773 at Milverton in Somersetshire, of Quaker parents, and after distinguishing himself during youth by the variety and accuracy of his attainments, he settled in London as a physician in 1801, but continued to give much of his attention to general science. His optical theory for a long time made few proselytes, and several years afterwards, Auguste Fresnel, an eminent French mathematician, an engineer officer, took up similar views, proved their truth, and traced their consequences by a series of labors almost independent of those of Dr. Young. It was not till the theory was thus re-echoed from another land that it was able to take any strong hold on the attention of the countrymen of its earlier promulgator. The theory of undulations, like that of universal gravitation, may be divided into several successive steps of generalization. In both cases, all these steps were made by the same persons, but there is this difference. All the parts of the law of universal gravitation were worked out in one burst of inspiration by its author, and published at one time. In the doctrine of light, on the other hand, the different steps of the advance were made and published at separate times, with intervals between. We see the theory in a narrower form and in detached portions before the widest generalizations and principles of unity are reached. We see the authors struggling with the difficulties before we see them successful. They appear to us as men like ourselves, liable to perplexity and failure, instead of coming before us, as Newton does in the history of physical astronomy, as the irresistible and almost supernatural hero of a philosophical romance. 93. The main subdivisions of the great advance in physical optics, of which we have now to give an account, are the following. 1. The explanation of the periodical colors of thin plates, thick plates, fringed shadows, striated surfaces, and other phenomena of the same kind, by means of the doctrine of the interference of undulations. 2. The explanation of the phenomena of double refraction, by the propagation of undulations in a medium of which the optical elasticity is different in different directions. 3. The conception of polarization as the result of the vibrations being transverse, and the consequent explanation of the production of polarization and the necessary connection between polarization and double refraction on mechanical principles. 4. The explanation of the phenomena of depolarization by means of the interference of the resolved parts of the vibrations after double refraction. The history of each of these discoveries will be given separately to a certain extent, by which means the force of proof arising from their combination will be more apparent. Sect 2. Explanation of the periodical colors of thin plates and shadows by the undulatory theory. The explanation of periodical colors by the principle of interference of vibrations was the first step which Young made in his confirmation of the undulatory theory. In a paper on sound and light, dated Emmanuel College, Cambridge, 9th July, 1799, and read before the Royal Society in January following, he appears to incline strongly to the Huyghenian theory, not however offering any new facts or calculations in its favor, but pointing out the great difficulties of the Newtonian hypothesis. But in a paper read before the Royal Society, November 12, 1801, he says, "A further consideration of the colors of thin plates has converted that prepossession which I before entertained for the undulatory theory of light into a very strong conviction of its truth and efficiency, a conviction which has since been most strikingly confirmed by an analysis of the colors of striated surfaces." He here states the general principle of interferences in the form of a proposition. Prop. Roman 8. When two undulations from different origins coincide either perfectly or very nearly in direction, their joint effect is a combination of the motions belonging to them. He explains, by the help of this proposition, the colors which were observed in Coventry's 94 micrometers, in which instrument lines were drawn on glass at a distance of 1/500th of an inch. The interference of the undulations of the rays reflected from the two sides of these fine lines produced periodical colors. In the same manner, he accounts for the colors of thin plates by the interference of the light partially reflected from the two surfaces of the plates. We have already seen that Hooke had long before suggested the same explanation, and Young says at the end of his paper, "It was not till I had satisfied myself respecting all these phenomena that I found in Hooke's Micrographia a passage which might have led me earlier to a similar opinion." He also quotes from Newton many passages which assume the existence of an ether, of which, as we have already seen, Newton suggests the necessity in these very phenomena, though he would apply it in combination with the emission of material light. In July 1802, Young explained, on the same principle, some facts in indistinct vision and other similar appearances. And in 1803, he speaks more positively still. "In making," he says, "some experiments on the fringes of colors accompanying shadows, I have found so simple and so demonstrative a proof of the general law of interference of two portions of light, which I have already endeavored to establish, that I think it right to lay before the Royal Society a short statement of the facts which appear to me to be thus decisive." The two papers just mentioned certainly ought to have convinced all scientific men of the truth of the doctrine thus urged, for the number and exactness of the explanations is very remarkable. They include the colored fringes which are seen with the shadows of fibers, the colors produced by a dew between two pieces of glass, which, according to the theory, should appear when the thickness of the plate is 6 times that of thin plates, and which do so, the changes resulting from the employment of other fluids than water, the effect of inclining the plates. Also the fringes and bands which accompany shadows, the phenomena observed by Grimaldi, Newton, Maraldi, and others, and hitherto never at all reduced to rule. Young observes, very justly, whatever may be thought of the theory, we have got a simple and general law of the phenomena. He moreover calculated the length of an undulation from the measurements of fringes of shadows, as he had done before from the colors of thin plates, and found a very close accordance of the results of the various cases with one another. 95. There is one difficulty, and one inaccuracy, in Young's views at this period, which it may be proper to note. The difficulty was that he found it necessary to suppose that light, when reflected at a rarer medium, is retarded by half an undulation. This assumption, though often urged at a later period as an argument against the theory, was fully justified as the mechanical principles of the subject were unfolded, and the necessity of it was clear to Young from the first. On the strength of this, says he, I ventured to predict that if the reflections were of the same kind, made at the surfaces of a thin plate, of a density intermediate between the densities of the mediums surrounding it, the central spot would be white. And I have now the pleasure of stating that I have fully verified this prediction by interposing a drop of oil of sassafras between a prism of flint glass and a lens of crown glass. The inaccuracy of his calculations consisted in his considering the external fringe of shadows to be produced by the interference of a ray reflected from the edge of the object, with a ray which passes clear of it, instead of supposing all the parts of the wave of light to corroborate or interfere with one another. The mathematical treatment of the question on the latter hypothesis was by no means easy. Young was a mathematician of considerable power in the solution of the problems which came before him, though his methods possessed none of the analytical elegance which, in his time, had become general in France. But it does not appear that he ever solved the problem of undulations as applied to fringes, with its true conditions. He did, however, rectify his conceptions of the nature of the interference, and we may add that the numerical error of the consequences of the defective hypothesis is not such as to prevent their confirming the undulatory theory. Note 76/9. I may mention, in addition to the applications which Young made of the principle of interferences, his areometer, an instrument invented for the purpose of measuring the thickness of the fibers of wood, and the explanation of the supernumerary bands of the rainbow. These explanations involve calculations founded on the length of an undulation of light, and were confirmed by experiment as far as experiment went. But though this theory was thus so powerfully recommended by experiment and calculation, it met with little favor in the scientific world. Perhaps this will be in some measure accounted for when we come, in the next chapter, to speak of the mode of its reception by 96, the supposed judges of science and letters. Its author went on laboring at the completion and application of the theory in other parts of the subject. But his extraordinary success in unraveling the complex phenomena of which we have been speaking appears to have excited none of the notice and admiration which properly belonged to it, till Fresnel's memoir on diffraction was delivered to the Institute in October 1815. Arago and Poinsot were commissioned to make a report upon this memoir, and the former of these philosophers threw himself upon the subject with a zeal and intelligence which peculiarly belonged to him. He verified the laws announced by Fresnel, laws, he says, which appear to be destined to make an epoch in science. He then cast a rapid glance at the history of the subject and recognized, at once, the place which Young occupied in it. Grimaldi, Newton, Maraldi, he states, had observed the facts and tried in vain to reduce them to rule or cause. Such was the state of our knowledge on this difficult question, when Dr. Thomas Young made the very remarkable experiment which is described in the Philosophical Transactions for 1803. Namely, that to obliterate all the bands within the shadow, we need only stop the ray which is going to graze, or has grazed, one border of the object. To this, Arago added the important observation that the same obliteration takes place if we stop the ray with a transparent plate, except the plate be very thin, in which case the bands are displaced and not extinguished. Fresnel, says he, guessed the effect which a thin plate would produce, when I had told him of the effect of a thick glass. Fresnel himself declares that he was not, at the time, aware of Young's previous labors. After stating nearly the same reasonings concerning fringes which Young had put forward in 1801, he adds, "It is therefore the meeting, the actual crossing of the rays, which produces the fringes. This consequence, which is only, so to speak, the translation of the phenomena, seems to me entirely opposed to the hypothesis of emission, and confirms the system which makes light consist in the vibrations of a peculiar fluid." And thus the principle of interferences and the theory of undulations, so far as that principle depends upon the theory, was a second time established by Fresnel in France, 14 years after it had been discovered, fully proved, and repeatedly published by Young in England. 97. In this memoir of Fresnel's, he takes very nearly the same course as Young had done, considering the interference of the direct light with that reflected at the edge as the cause of the external fringes. And he observes that in this reflection it is necessary to suppose half an undulation lost. But a few years later, he considered the propagation of undulations in a more true and general manner, and obtained the solution of this difficulty of the half undulation. His more complete memoir on diffraction was delivered to the Institute of France, July 29, 1818, and had the prize awarded it in 1819. But by the delays which at that period occurred in the publication of the Parisian academical transactions, it was not published till 1826, when the theory was no longer generally doubtful or unknown in the scientific world. In this memoir, Fresnel observes that we must consider the effect of every portion of a wave of light upon a distant point, and must, on this principle, find the illumination produced by any number of such waves together. Hence, in general, the process of integration is requisite, and though the integrals which here offer themselves are of a new and difficult kind, he succeeded in making the calculation for the cases in which he experimented. His table of the correspondences of theory and observation is very remarkable for the closeness of the agreement, the errors being generally less than 1/100th of the whole in the distances of the black bands. He justly adds, a more striking agreement could not be expected between experiment and theory. If we compare the smallness of the differences with the extent of the breadths measured, and if we remark the great variations which A and B, the distance of the object from the luminous point and from the screen, have received in the different observations, we shall find it difficult not to regard the integral which has led us to these results as the faithful expression of the law of the phenomena. A mathematical theory, applied with this success to a variety of cases of very different kinds, could not now fail to take strong hold of the attention of mathematicians, and accordingly, from this time, the undulatory doctrine of diffraction has been generally assented to, and the mathematical difficulties which it involves have been duly studied and struggled with. Among the remarkable applications of the undulatory doctrine to diffraction, we may notice those of Joseph Fraunhofer, a '98 mathematical optician of Munich. He made a great number of experiments on the shadows produced by small holes and groups of small holes very near each other. These were published in his New Modifications of Light in 1823. The greater part of this memoir is employed in tracing the laws of phenomena of the extremely complex and splendid appearances which he obtained. But at the conclusion he observes, "It is remarkable that the laws of the reciprocal influence and of the diffraction of the rays can be deduced from the principles of the undulatory theory. Knowing the conditions, we may, by means of an extremely simple equation, determine the extent of a luminous wave for each of the different colors. And in every case, the calculation corresponds with observation." This mention of an extremely simple equation appears to imply that he employed only Young's and Fresnel's earlier mode of calculating interferences by considering two portions of light and not the method of integration. Both from the late period at which they were published, and from the absence of mathematical details, Fraunhofer's labors had not any strong influence on the establishment of the undulatory theory, although they are excellent verifications of it, both from the goodness of the observations and the complexity and beauty of the phenomena. Note 82/9, in Schumacher's Astronomische Abhandlungen, in French, earlier in German. We have now to consider the progress of the undulatory theory in another of its departments, according to the division already stated. Sect 3. Explanation of double refraction by the undulatory theory. We have traced the history of the undulatory theory applied to diffraction into the period when Young came to have Fresnel for his fellow laborer. But in the meantime, Young had considered the theory in its reference to other phenomena, and especially to those of double refraction. In this case, indeed, Huygens' explanation of the facts of Iceland's spar by means of spheroidal undulations was so complete, and had been so fully confirmed by the measurements of Hoy and Wollaston, that little remained to be done, except to connect the Huygenian hypothesis with the mechanical views belonging to the theory, and to extend his law to other cases. The former part of this task Young executed by remarking that we may conceive the elasticity of the 99 crystal, on which the velocity of propagation of the luminiferous undulation depends, to be different in the direction of the crystallographic axis and in the direction of the planes at right angles to this axis. And from such a difference, he deduces the existence of spheroidal undulations. This suggestion appeared in the Quarterly Review for November, 1809, in a critique upon an attempt of Laplace to account for the same phenomena. Laplace had proposed to reduce the double refraction of such crystals as Iceland's spar to his favorite machinery of forces which are sensible at small distances only. The peculiar forces which produce the effect in this case he conceives to emanate from the crystallographic axis, so that the velocity of light within the crystal will depend only on the situation of the ray with respect to this axis. But the establishment of this condition is, as Young observes, the main difficulty of the problem. How are we to conceive refracting forces, independent of the surface of the refracting medium and regulated only by a certain internal line? Moreover, the law of force which Laplace was obliged to assume, namely, that it varied as the square of the sine of the angle which the ray made with the axis, could hardly be reconciled with mechanical principles. In the critique just mentioned, Young appears to feel that the undulatory theory, and perhaps he himself, had not received justice at the hands of men of science. He complains that a person so eminent in the world of science as Laplace then was, should employ his influence in propagating error, and should disregard the extraordinary confirmations which the Huygenian theory had recently received. The extension of this view, of the different elasticity of crystals in different directions, to other than uniaxial crystals, was a more complex and difficult problem. The general notion was perhaps obvious after what Young had done, but its application and verification involved mathematical calculations of great generality, and required also very exact experiments. In fact, this application was not made till Fresnel, a pupil of the Polytechnic School, brought the resources of the modern analysis to bear upon the problem, till the phenomena of dipolarized light presented the properties of biaxial crystals in a vast variety of forms, until the theory received its grand impulse by the combination of the explanation of polarization with the explanation of double refraction. To the history of this last-mentioned great step, we now proceed. 100. Sect 4. Explanation of polarization by the undulatory theory. Even while the only phenomena of polarization which were known were those which affect the two images in Iceland's spar, the difficulty which these facts seemed at first to throw in the way of the undulatory theory was felt and acknowledged by Young. Malice's discovery of polarization by reflection increased the difficulty, and this Young did not attempt to conceal. In his review of the papers containing this discovery, he says, "The discovery related in these papers appears to us to be by far the most important and interesting which has been made in France concerning the properties of light, at least since the time of Huygens. And it is so much the more deserving of notice, as it greatly influences the general balance of evidence in the comparison of the undulatory and projectile theories of the nature of light." He then proceeds to point out the main features in this comparison, claiming justly a great advantage for the theory of undulations on the 2 points we have been considering, the phenomena of diffraction and of double refraction. And he adds, with reference to the embarrassment introduced by polarization, that we are not to expect the course of scientific discovery to run smooth and uninterrupted, but that we are to lay our account with partial obscurity and seeming contradiction, which we may hope that time and enlarged research will dissipate. And thus he steadfastly held, with no blind prejudice, but with unshaken confidence, his great philosophical trust, the fortunes of the undulatory theory. It is here, after the difficulties of polarization had come into view, and before their solution had been discovered, that we may place the darkest time of the history of the theory. And at this period Young was alone in the field. It does not appear that the light dawned upon him for some years. In the meantime, Young found that his theory would explain dipolarized colors, and he had the satisfaction to see Fresnel rediscover, and M. Arago adopt, his views on diffraction. He became engaged in friendly intercourse with the latter philosopher, who visited him in England in 1816. On January the 12th, 1817, in writing to this gentleman, among other remarks on the subject of optics, he says, "I have also been reflecting on the possibility of giving an imperfect explanation of the affection of light which constitutes polarization. 101, without departing from the genuine doctrine of undulation." He then proceeds to suggest the possibility of a transverse vibration, propagated in the direction of the radius, the motions of the particles being in a certain constant direction with respect to that radius. And this, he adds, is polarization. From his further explanation of his views, it appears that he conceived the motions of the particles to be oblique to the direction of the ray, and not perpendicular, as the theory was afterwards framed. But still, here was the essential condition for the explanation of the facts of polarization, the transverse nature of the vibrations. This idea at once made it possible to conceive how the rays of light could have sides, for the direction in which the vibration was transverse to the ray might be marked by peculiar properties. And after the idea was once started, it was comparatively easy for men like Young and Fresnel to pursue and modify it till it assumed its true and distinct form. We may judge of the difficulty of taking firmly hold of the conception of transverse vibrations of the ether, as those which constitute light, by observing how long the great philosophers of whom we are speaking lingered within reach of it, before they ventured to grasp it. Fresnel says, in 1821, when M. Arago and I had remarked, in 1816, that two rays polarized at right angles always give the same quantity of light by their union, I thought this might be explained by supposing the vibrations to be transverse, and to be at right angles when the rays are polarized at right angles. But this supposition was so contrary to the received ideas on the nature of the vibrations of elastic fluids, that Fresnel hesitated to adopt it till he could reconcile it better to his mechanical notions. Mr. Young, more bold in his conjectures, and less confiding in the views of geometers, published it before me, though perhaps he thought it after me. And M. Arago was afterwards wont to relate that, when he and Fresnel had obtained their joint experimental results of the non-interference of oppositely polarized pencils, and when Fresnel pointed out that transverse vibrations were the only possible translation of this fact into the undulatory theory, he himself protested that he had not courage to publish such a conception, and accordingly, the second part of the memoir was published in Fresnel's name alone. What renders this more remarkable is that it occurred when M. Arago had in his possession the very letter of Young in which he proposed the same suggestion. 102. Note 84/9. I take the liberty of stating this from personal knowledge. Young's first published statement of the doctrine of transverse vibrations was given in the explanation of the phenomena of dipolarization, of which we shall have to speak in the next section. But the primary and immense value of this conception, as a step in the progress of the undulatory theory, was the connection which it established between polarization and double refraction. For it held forth a promise of accounting for polarization, if any conditions could be found which might determine what was the direction of the transverse vibrations. The analysis of these conditions is, in a great measure, the work of Fresnel, a task performed with profound philosophical sagacity and great mathematical skill. Since the double refraction of uniaxial crystals could be explained by undulations of the form of a spheroid, it was perhaps not difficult to conjecture that the undulations of biaxial crystals would be accounted for by undulations of the form of an ellipsoid, which differs from the spheroid in having its three axes unequal, instead of two only, and consequently has that very relation to the other, in respect of symmetry, which the crystalline and optical phenomena have. Or, again, instead of supposing two different degrees of elasticity in different directions, we may suppose three such different degrees in directions at right angles to each other. This kind of generalization was tolerably obvious to a practiced mathematician. But what shall call into play all these elasticities at once, and produce waves governed by each of them? And what shall explain the different polarization of the rays which these separate waves carry with them? These were difficult questions, to the solution of which mathematical calculation had hitherto been unable to offer any aid. It was here that the conception of transverse vibrations came in, like a beam of sunlight, to disclose the possibility of a mechanical connection of all these facts. If transverse vibrations, traveling through a uniform medium, come to a medium not uniform, but constituted so that the elasticity shall be different in different directions, in the manner we have described, what will be the course and condition of the waves in the second medium? Will the effects of such waves agree with the phenomena of doubly refracted light in biaxial crystals? Here was a problem, striking to the mathematician for its generality and difficulty, and of deep interest to the physical philosopher, because the fate of a great theory depended upon its solution. The solution, obtained by great mathematical skill, was laid before the French Institute by Fresnel in November, 1821, and was carried, 103 further in two memoirs presented in 1822. Its import is very curious. The undulations which, coming from a distant center, fall upon such a medium as we have described, are, it appears from the principles of mechanics, propagated in a manner quite different from anything which had been anticipated. The surface of the waves, that is, the surface which would bound undulations diverging from a point, is a very complex yet symmetrical curve surface, which, in the case of uniaxial crystals, resolves itself into a sphere and a spheroid, but which, in general, forms a continuous double envelope of the central point to which it belongs, intersecting itself and returning into itself. The directions of the rays are determined by this curved surface in biaxial crystals, as in uniaxial crystals they are determined by the sphere and the spheroid. And the result is that in biaxial crystals, both rays suffer extraordinary refraction according to determinate laws. And the positions of the planes of polarization of the two rays follow from the same investigation, the plane of polarization in every case being supposed to be that which is perpendicular to the transverse vibrations. Now it appeared that the polarization of the two rays as determined by Fresnel's theory would be in directions, not indeed exactly accordant with the law deduced by M. Biot from experiment, but deviating so little from those directions that there could be small doubt that the empirical formula was wrong and the theoretical one right. The theory was further confirmed by an experiment showing that, in a biaxial crystal topaz, neither of the rays was refracted according to the ordinary law, though it had hitherto been supposed that one of them was so. A natural inaccuracy, since the error was small. Thus this beautiful theory corrected, while it explained, the best of the observations which had previously been made, and offered itself to mathematicians with an almost irresistible power of conviction. The explanation of laws so strange and diverse as those of double refraction and polarization, by the same general and symmetrical theory, could not result from anything but the truth of the theory. Long, says Fresnel, before I had conceived this theory, I had convinced myself by a pure contemplation of the facts that it was not possible to discover the true explanation of double refraction without explaining at the same time the phenomena of polarization which always goes along with it. And accordingly, it was after having found 104 what mode of vibration constituted polarization that I caught sight of the mechanical causes of double refraction. Having thus got possession of the principle of the mechanism of polarization, Fresnel proceeded to apply it to the other cases of polarized light, with a rapidity and sagacity which reminds us of the spirit in which Newton traced out the consequences of the principle of universal gravitation. In the execution of his task, indeed, Fresnel was forced upon several precarious assumptions, which make, even yet, a wide difference between the theory of gravitation and that of light. But the mode in which these were confirmed by experiment compels us to admire the happy apparent boldness of the calculator. The subject of polarization by reflection was one of those which seemed most untractable, but by means of various artifices and conjectures, it was broken up and subdued. Fresnel began with the simplest case, the reflection of light polarized in the plane of reflection, which he solved by means of the laws of collision of elastic bodies. He then took the reflection of light polarized perpendicularly to this plane, and here, adding to the general mechanical principles a hypothetical assumption that the communication of the resolved motion parallel to the refracting surface takes place according to the laws of elastic bodies, he obtains his formula. These results were capable of comparison with experiment, and the comparison, when made by M. Arago, confirmed the formulae. They accounted, too, for Sir D. Brewster's law concerning the polarizing angle, see chapter Roman 6. And this could not but be looked upon as a striking evidence of their having some real foundation. Another artifice which Fresnel and Arago employed, in order to trace the effect of reflection upon common light, was to use a ray polarized in a plane making half a right angle with the plane of reflection. For the quantities of the oppositely polarized light in such an incident ray are equal as they are in common light. But the relative quantities of the oppositely polarized light in the reflected ray are indicated by the new plane of polarization. And thus these relative quantities become known for the case of common light. The results thus obtained were also confirmed by facts, and in this manner, all that was doubtful in the process of Fresnel's reasoning seemed to be authorized by its application to real cases. 105. Note 87/9. It will be recollected all along that oppositely polarized rays are those which are polarized in two planes perpendicular to each other. See above, chapter Roman 6. These investigations were published in 1821. In succeeding years, Fresnel undertook to extend the application of his formulae to a case in which they ceased to have a meaning, or, in the language of mathematicians, became imaginary, namely, to the case of internal reflection at the surface of a transparent body. It may seem strange to those who are not mathematicians, but it is undoubtedly true that in many cases in which the solution of a problem directs impossible arithmetical or algebraical operations to be performed, these directions may be so interpreted as to point out a true solution of the question. Such an interpretation Fresnel attempted in the case of which we now speak, and the result at which he arrived was that the reflection of light through a rhomb of glass of a certain form, since called Fresnel's rhomb, would produce a polarization of a kind altogether different from those which his theory had previously considered, namely, that kind which we have spoken of as circular polarization. The complete confirmation of this curious and unexpected result by trial is another of the extraordinary triumphs which have distinguished the history of the theory at every step since the commencement of Fresnel's labors. But anything further which has been done in this way may be treated of more properly in relating the verification of the theory. And we have still to speak of the most numerous and varied class of facts to which rival theories of light were applied, and of the establishment of the undulatory doctrine in reference to that department. I mean the phenomena of depolarized, or rather, as I have already said, depolarized light. Sect 5 Explanation of depolarization by the undulatory theory. When Arago, in 1811, had discovered the colors produced by polarized light passing through certain crystals, it was natural that attempts should be made to reduce them to theory. M. Biot, animated by the success of malice in detecting the laws of double refraction, and Young, knowing the resources of his own theory, were the first persons to enter upon this undertaking. M. Biot's theory, though in the end displaced by its rival, is well worth notice in the history of the subject. It was what he called the doctrine of movable polarization. He conceived that when the molecules of light pass through 106 thin crystalline plates, the plane of polarization undergoes an oscillation which carries it backwards and forwards through a certain angle, namely, twice the angle contained between the original plane of polarization and the principal section of the crystal. The intervals which this oscillation occupies are lengths of the path of the ray, very minute, and different for different colors, like Newton's fits of easy transmission, on which model, indeed, the new theory was evidently framed. The colors produced in the phenomena of depolarization really do depend, in a periodical manner, on the length of the path of the light through the crystal. And a theory such as M. Biot's was capable of being modified, and was modified so as to include the leading features of the facts as then known. But many of its conditions being founded on special circumstances in the experiments, and not on the real conditions of nature, there were in it several incongruities, as well as the general defect of its being an arbitrary and unconnected hypothesis. Note 91/9, Seam, Arago and Biot's Memoirs Mame, Inst. For 1811, the whole volume for 1812 is a memoir of M. Biot's, published 1814, also Mame. Inst. For 1817, M. Biot's Mem read in 1818, published in 1819, and for 1818. Young's mode of accounting for the brilliant phenomena of depolarization appeared in the Quarterly Review for 1814. After noticing the discoveries of Arago, Brewster, and Biot, he adds, "We have no doubt that the surprise of these gentlemen will be as great as our own satisfaction in finding that they are perfectly reducible, like other causes of recurrent colors, to the general laws of the interference of light which have been established in this country," giving a reference to his former statements. The results are then explained by the interference of the ordinary and extraordinary ray. But, as M. Arago properly observes, in his account of this matter, it must, however, be added that Dr. Young had not explained either in what circumstances the interference of the rays can take place, nor why we see no colors, unless the crystallized plates are exposed to light previously polarized. The explanation of these circumstances depends on the laws of interference of polarized light which Arago and Fresnel established in 1816. They then proved, by direct experiment, that when polarized light was treated so as to bring into view the most marked phenomena of interference, namely, the bands of shadows, pencils of light which have a common origin and which are polarized in the parallel planes interfere completely, while those which are 107 polarized in opposite, that is, perpendicular, planes do not interfere at all. Taking these principles into the account, Fresnel explained very completely, by means of the interference of undulations, all the circumstances of colors produced by crystallized plates, showing the necessity of the polarization in the first instance, the depolarizing effect of the crystal, and the office of the analyzing plate, by which certain portions of each of the two rays in the crystal are made to interfere and produce color. This he did, as he says, without being aware, till Arago told him, that Young had, to some extent, anticipated him. When we look at the history of the emission theory of light, we see exactly what we may consider as the natural course of things in the career of a false theory. Such a theory may, to a certain extent, explain the phenomena which it was at first contrived to meet, but every new class of facts requires a new supposition and addition to the machinery. And as observation goes on, these incoherent appendages accumulate till they overwhelm and upset the original framework. Such was the history of the hypothesis of solid epicycles. Such has been the history of the hypothesis of the material emission of light. In its simple form, it explained reflection and refraction, but the colors of thin plates added to it the hypothesis of fits of easy transmission and reflection. The phenomena of diffraction further invested the particles with complex hypothetical laws of attraction and repulsion. Polarization gave them sides. Double refraction subjected them to peculiar forces emanating from the axes of crystals. Finally, depolarization loaded them with the complex and unconnected contrivance of movable polarization, and even when all this had been assumed, additional mechanism was wanting. There is here no unexpected success, no happy coincidence, no convergence of principles from remote quarters. The philosopher builds the machine, but its parts do not fit. They hold together only while he presses them. This is not the character of truth. In the undulatory theory, on the other hand, all tends to unity and simplicity. We explain reflection and refraction by undulations. When we come to thin plates, the requisite fits are already involved in our fundamental hypothesis, for they are the length of an undulation. The phenomena of diffraction also require such intervals, and the intervals thus required agree exactly with the others in magnitude, 108, so that no new property is needed. Polarization for a moment checks us, but not long, for the direction of our vibrations is hitherto arbitrary. We allow polarization to decide it. Having done this for the sake of polarization, we find that it also answers an entirely different purpose, that of giving the law of double refraction. Truth may give rise to such a coincidence, falsehood cannot. But the phenomena become more numerous, more various, more strange. No matter, the theory is equal to them all. It makes not a single new physical hypothesis, but out of its original stock of principles, it educes the counterpart of all that observation shows. It accounts for, explains, simplifies the most entangled cases, corrects known laws and facts, predicts and discloses unknown ones, becomes the guide of its former teacher, observation, and, enlightened by mechanical conceptions, acquires an insight which pierces through shape and color to force and cause. We thus reach the philosophical moral of this history, so important in reference to our purpose. And here we shall close the account of the discovery and promulgation of the undulatory theory. Any further steps in its development and extension may with propriety be noticed in the ensuing chapters, respecting its reception and verification. In the philosophy of the Inductive Sciences, B's Roman 3. Sect. 11, I have spoken of the consilience of inductions as one of the characters of scientific truth. We have several striking instances of such consilience in the history of the undulatory theory. The phenomena of fringes of shadows and colored bands in crystals jump together in the theory of vibrations. The phenomena of polarization and double refraction jump together in the theory of crystalline vibrations. The phenomena of polarization and of the interference of polarized rays jump together in the theory of transverse vibrations. The proof of what is above said of the undulatory theory is contained in the previous history. This theory has accounted for, explained, and simplified the most entangled cases, as the cases of fringes of shadows, shadows of gratings, colored bands in biaxial crystals, and in quartz. There are no optical phenomena more entangled than these. It has corrected experimental laws, as in the case of M. Biot's law of the direction of polarization in biaxial crystals. It has done this without making any new physical hypothesis. For the transverse direction of vibrations, the different optical elasticities of crystals in different directions, and if it be adopted, the hypothesis of finite, 109 intervals of the particles, see Chapter X and hereafter, Chapter Roman 13, are only limitations of what was indefinite in the earlier form of the hypothesis. And so far as the properties of visible radiant light are concerned, I do not think it at all too much to say, as M. Schwerd has said, that the undulation theory accounts for the phenomena as completely as the theory of gravitation does for the facts of the solar system. This we might say, even if some facts were not yet fully explained, for there were till very lately, if there are not still, such unexplained facts with regard to the theory of gravitation, presented to us by the solar system. With regard to the undulatory theory, these exceptions are, I think, disappearing quite as rapidly and as completely as in the case of gravitation. It is to be observed that no presumption against the theory can with any show of reason be collected from the cases in which classes of phenomena remain unexplained, the theory having never been applied to them by any mathematician capable of tracing its results correctly. The history of the theory of gravitation may show us abundantly how necessary it is to bear in mind this caution. And the results of the undulatory theory cannot be traced without great mathematical skill and great labor, any more than those of gravitation. This remark applies to such cases as that of the transverse fringes of grooved surfaces. The general phenomena of these cases are perfectly explained by the theory. But there is an interruption in the light in an oblique direction, which has not yet been explained. But looking at what has been done in other cases, it is impossible to doubt that this phenomenon depends upon the results of certain integrations, and would be explained if these were rightly performed. The phenomena of crystallized surfaces, and especially their effects upon the plane of polarization, were examined by Sir D. Brewster, and laws of the phenomena made out by him with his usual skill and sagacity. For a time, these were unexplained by the theory. But recently Mr. MacCulloch has traced the consequences of the theory in this case, and obtained a law which represents with much exactness Sir D. Brewster's observation. The phenomena which Sir D. Brewster, in 1837, called a new property of light, certain appearances of the spectrum when the pupil of the eye is half covered with a thin glass or crystal, have been explained by Mr. Airy in the Phil. Trans for 1840. Mr. Airy's explanation of the phenomena termed by Sir D. 110, Brewster, a new property of light, is completed in the Philosophical Magazine for November, 1846. It is there shown that a dependence of the breadth of the bands upon the aperture of the pupil, which had been supposed to result from the theory, and which does not appear in the experiment, did really result from certain limited conditions of the hypothesis, which conditions do not belong to the experiment, and that when the problem is solved without those limitations, the discrepance of theory and observation vanishes. So that, as Mr. Airy says, this very remarkable experiment, which long appeared inexplicable, seems destined to give one of the strongest confirmations to the undulatory theory. I may remark also that there is no force in the objection which has been urged against the admirers of the undulatory theory, that by the fullness of their assent to it, they discourage further researches which may contradict or confirm it. We must, in this point of view also, look at the course of the theory of gravitation and its results. The acceptance of that theory did not prevent mathematicians and observers from attending to the apparent exceptions, but on the contrary, stimulated them to calculate and to observe with additional zeal, and still does so. The acceleration of the Moon, the mutual disturbances of Jupiter and Saturn, the motions of Jupiter's satellites, the effect of the Earth's oblateness on the Moon's motion, the motions of the Moon about her own center, and many other phenomena were studied with the greater attention, because the general theory was deemed so convincing. And the same cause makes the remaining exceptions objects of intense interest to astronomers and mathematicians. The mathematicians and optical experimenters who accept the undulatory theory will, of course, follow out their conviction in the same manner. Accordingly, this has been done and is still doing, as in Mr. Airy's mathematical investigation of the effect of an annular aperture, Mr. Earnshaw's of the effect of a triangular aperture, Mr. Talbot's explanation of the effect of interposing a film of mica between a part of the pupil and the pure spectrum, so nearly approaching to the phenomena which have been spoken of as a new polarity of light, besides other labors of eminent mathematicians elsewhere mentioned in these pages. The phenomena of the absorption of light have no especial bearing upon the undulatory theory. There is not much difficulty in explaining the possibility of absorption upon the theory. When the light is absorbed, it ceases to belong to the theory. 111. For, as I have said, the theory professes only to explain the phenomena of radiant visible light. We know very well that light has other bearings and properties. It produces chemical effects. The optical polarity of crystals is connected with the chemical polarity of their constitution. The natural colors of bodies, too, are connected with their chemical constitution. Light is also connected with heat. The undulatory theory does not undertake to explain these properties and their connection. If it did, it would be a theory of heat and of chemical composition, as well as a theory of light. Dr. Faraday's recent experiments have shown that the magnetic polarity is directly connected with that optical polarity by which the plane of polarization is affected. When the lines of magnetic force pass through certain transparent bodies, they communicate to them a certain kind of circular polarizing power, yet different from the circular polarizing power of quartz and certain fluids mentioned in Chapter 9. Perhaps I may be allowed to refer to this discovery as a further illustration of the views I have offered in the philosophy of the inductive sciences respecting the connection of coexistent polarities. B.V. Chapter Roman 2. Chapter 12. Sequel to the epoch of Young and Fresnel, reception of the undulatory theory. When Young, in 1800, published his assertion of the principle of interferences as the true theory of optical phenomena, the condition of England was not very favorable to a fair appreciation of the value of the new opinion. The men of science were strongly preoccupied in favor of the doctrine of emission, not only from a national interest in Newton's glory and a natural reverence for his authority, but also from deference towards the geometers of France, who were looked up to as our masters in the application of mathematics to physics, and who were understood to be Newtonians in this as in other subjects. A general tendency to an atomic philosophy, which had begun to appear from the time of Newton, operated powerfully. And 112. The hypothesis of emission was so easily conceived that, when recommended by high authority, it easily became popular, while the hypothesis of luminiferous undulations, unavoidably difficult to comprehend, even by the aid of steady thought, was neglected and all but forgotten. Yet the reception which Young's opinions met with was more harsh than he might have expected, even taking into account all these considerations. But there was in England no visible body of men, fitted by their knowledge and character to pronounce judgment on such a question, or to give the proper impulse and bias to public opinion. The Royal Society, for instance, had not for a long time, by custom or institution, possessed or aimed at such functions. The writers of reviews alone, self-constituted and secret tribunals, claimed this kind of authority. Among these publications, by far the most distinguished about this period was the Edinburgh Review and, including among its contributors men of eminent science and great talents, employing also a robust and poignant style of writing, often certainly in a very unfair manner, it naturally exercised great influence. On abstruse doctrines, intelligible to few persons, more than on other subjects, the opinions and feelings expressed in a review must be those of the individual reviewer. The criticism on some of Young's early papers on optics was written by Mr., afterwards Lord Brougham, who, as we have seen, had experimented on diffraction, following the Newtonian view, that of inflection. Mr. Brougham was perhaps at this time young enough to be somewhat intoxicated with the appearance of judicial authority in matters of science, which his office of anonymous reviewer gave him. And even in middle life, he was sometimes considered to be prone to indulge himself in severe and sarcastic expressions. In January 1803 was published his critique on Dr. Young's Bakerian lecture, on the theory of light and colors, in which lecture the doctrine of undulations and the law of interferences was maintained. This critique was an uninterrupted strain of blame and rebuke. This paper, the reviewer said, contains nothing which deserves the name either of experiment or discovery. He charged the writer with dangerous relaxations of the principles of physical logic. We wish, he cried, to recall philosophers to the strict and severe methods of investigation, describing them as those pointed out by Bacon, Newton, and the like. Finally, Dr. Young's speculations, 113, were spoken of as a hypothesis, which is a mere work of fancy, and the critic added, "We cannot conclude our review without entreating the attention of the Royal Society, which has admitted of late so many hasty and unsubstantial papers into its transactions," which habit he urged them to reform. The same aversion to the undulatory theory appears soon after in another article by the same reviewer on the subject of Wollaston's measures of the refraction of Iceland spar. He says, We are much disappointed to find that so acute and ingenious an experimentalist should have adopted the wild optical theory of vibrations. The reviewer showed ignorance as well as prejudice in the course of his remarks, and Young drew up an answer, which was ably written, but being published separately had little circulation. We can hardly doubt that these Edinburgh reviews had their effect in confirming the general disposition to reject the undulatory theory. We may add, however, that Young's mode of presenting his opinions was not the most likely to win them favor, for his mathematical reasonings placed them out of the reach of popular readers, while the want of symmetry and system in his symbolical calculations deprived them of attractiveness for the mathematician. He himself gave a very just criticism of his own style of writing in speaking on another of his works. The mathematical reasoning, for want of mathematical symbols, was not understood, even by tolerable mathematicians. From a dislike of the affectation of algebraical formality which he had observed in some foreign authors, he was led into something like an affectation of simplicity, which was equally inconvenient to a scientific reader. Young appears to have been aware of his own deficiency in the power of drawing public favor or even notice to his discoveries. In 1802, Davy writes to a friend, "Have you seen the theory of my colleague, Dr. Young, on the undulations of an ethereal medium as the cause of light? It is not likely to be a popular hypothesis after what has been said by Newton concerning it. He would be very much flattered if you could offer any observations upon it, whether for or against it." Young naturally felt confident in his power of refuting objections and wanted only the opportunity of a public combat. Dr. Brewster, who was, at this period, enriching optical knowledge with so vast a train of new phenomena and laws, shared the general aversion to the undulatory theory, which, indeed, he hardly overcame, 30 years later. Dr. Wollaston was a person whose character led him to look long at the laws of phenomena before he attempted to determine their causes, and it does not appear that he had decided the claims of the rival theories in his own mind. Herschel, I now speak of the sun, had at first the general mathematical prejudice in favor of the emission doctrine. Even when he had himself studied and extended the laws of dipolarized phenomena, he translated them into the language of the theory of movable polarization. In 1819, he refers to and corrects this theory, and says, "It is now relieved from every difficulty, and entitled to rank with the fits of easy transmission and reflection as a general and simple physical law." A just judgment, but one which now conveys less of praise than he then intended. At a later period, he remarked that we cannot be certain that if the theory of emission had been as much cultivated as that of undulation, it might not have been as successful. An opinion which was certainly untenable after the fair trial of the two theories in the case of diffraction, and extravagant after Fresnel's beautiful explanation of double refraction and polarization. Even in 1827, in a treatise on light, published in the Encyclopaedia Metropolitana, he gives a section to the calculations of the Newtonian theory, and appears to consider the rivalry of the theories as still subsisting. But yet he there speaks with a proper appreciation of the advantages of the new doctrine. After tracing the prelude to it, he says, "But the unpursued speculations of Newton and the opinions of Hooke, however distinct, must not be put in competition, and indeed ought scarcely to be mentioned, with the elegant, simple, and comprehensive theory of Young, a theory which, if not founded in nature, is certainly one of the happiest fictions that the genius of man ever invented to grasp together natural phenomena, which, at their first discovery, seemed in irreconcilable opposition to it. It is, in fact, in all its applications and details, one succession of felicities, insomuch that we may almost be induced to say, if it be not true, it deserves to be so." In France, Young's theory was little noticed or known, except perhaps by M. Arago, till it was revived by Fresnel. And though Fresnel's assertion of the undulatory theory was not so rudely received as Young's had been, it met with no small opposition from the older mathematicians, and made its way slowly to the notice and comprehension of men of science. M. Arago would perhaps have at once adopted the conception of transverse vibrations, when it was suggested by his fellow laborer, Fresnel, if it had not been that he was a member of the 115 Institute, and had to bear the brunt of the war in the frequent discussions on the undulatory theory. to which theory Laplace and other leading members were so vehemently opposed that they would not even listen with toleration to the arguments in its favor. I do not know how far influences of this kind might operate in producing the delays which took place in the publication of Fresnel's papers. We have seen that he arrived at the conception of transverse vibrations in 1816 as the true key to the understanding of polarization. In 1817 and 1818, in a memoir read to the Institute, he analyzed and explained the perplexing phenomena of quartz, which he ascribed to a circular polarization. This memoir had not been printed, nor any extract from it inserted in the scientific journals in 1822, when he confirmed his views by further experiments. His remarkable memoir, which solved the extraordinary and capital problem of the connection of double refraction and crystallization, though written in 1821, was not published till 1827. He appears by this time to have sought other channels of publication. In 1822, he gave, in the Annales de Chimie et de Physique, an explanation of refraction on the principles of the undulatory theory, alleging, as the reason for doing so, that the theory was still little known. And in succeeding years there appeared in the same work his theory of reflection. His memoir on this subject, Mémoire sur la loi des modifications, que la réflexion imprime à la lumière polarisée, was read to the Academy of Sciences in ** 1823. But the original paper was mislaid, and, for a time, supposed to be lost. It has since been recovered among the papers of M. Fourier and printed in the 11th volume of the Memoirs of the Academy. Some of the speculations to which he refers, as communicated to the Academy, have never yet appeared. Note 101/9, Lloyd, Report on Optics, p. 363, 4th Rep of Brit. As. Still Fresnel's labors were, from the first, duly appreciated by some of the most eminent of his countrymen. His memoir on diffraction was, as we have seen, crowned in 1819, and in 1822, a report upon his memoir on double refraction was drawn up by a commission consisting of Ampère, Fourier, and Arago. In this report, Fresnel's theory is spoken of as confirmed by the most delicate tests. The reporters add, respecting his theoretical ideas on the particular kind of undulations, which, according to him, constitute light, that it would be impossible for them to pronounce at present a decided 116 judgment, but that they have not thought it right to delay any longer making known a work of which the difficulty is attested by the fruitless efforts of the most skillful philosophers, and in which are exhibited in the same brilliant degree the talent for experiment and the spirit of invention. In the meantime, however, a controversy between the theory of undulations and the theory of movable polarization, which M. Biot had proposed with a view of accounting for the colors produced by dipolarizing crystals, had occurred among the French men of science. It is clear that in some main features the two theories coincide, the intervals of interference in the one theory being represented by the intervals of the oscillations in the other. But these intervals in M. Biot's explanations were arbitrary hypotheses, suggested by these very facts themselves. In Fresnel's theory, they were essential parts of the general scheme. M. Biot, indeed, does not appear to have been averse from a coalition, for he allowed to Fresnel that the theory of undulations took the phenomena at a higher point and carried them further. And M. Biot could hardly have dissented from M. Arago's account of the matter, that Fresnel's views linked together the oscillations of movable polarization. But Fresnel, whose hypothesis was all of one piece, could give up no part of it, although he allowed the usefulness of M. Biot's formulae. Yet M. Biot's speculations fell in better with the views of the leading mathematicians of Paris. We may consider as evidence of the favor with which they were looked upon the large space they occupy in the volumes of the Academy for 1811, 1812, 1817, and 1818. In 1812, the entire volume is filled with a memoir of M. Biot's on the subject of movable polarization. This doctrine also had some advantage in coming early before the world in a didactic form, in his Traité de Physique, which was published in 1816, and was the most complete treatise on general physics which had appeared up to that time. In this and others of this author's writings, he expresses facts so entirely in the terms of his own hypothesis that it is difficult to separate the two. In the sequel M, Arago was the most prominent of M. Biot's opponents, and in his report upon Fresnel's memoir on the colors of crystalline plates, he exposed the weaknesses of the theory of movable polarization with some severity. The details of this controversy need not occupy us, but we may observe that this may be considered as the last struggle, 117, in favor of the theory of emission among mathematicians of eminence. After this crisis of the war, the theory of movable polarization lost its ground, and the explanations of the undulatory theory and the calculations belonging to it being published in the Annales de Chimie et de Physique, of which M. Arago was one of the conductors, soon diffused it over Europe. It was probably in consequence of the delays to which we have referred in the publication of Fresnel's memoirs that as late as December 1826, the Imperial Academy at St. Petersburg proposed, as one of their prize questions for the 2 following years, this: to deliver the optical system of waves from all the objections which have, as it appears, with justice been urged against it, and to apply it to the polarization and double refraction of light. In the program to this announcement, Fresnel's researches on the subject are not alluded to, though his memoir on diffraction is noticed. They were, therefore, probably not known to the Russian Academy. Young was always looked upon as a person of marvelous variety of attainments and extent of knowledge, but during his life, he hardly held that elevated place among great discoverers which posterity will probably assign him. In 1802, he was constituted Foreign Secretary of the Royal Society, an office which he held during life. In 1827, he was elected one of the 8 foreign members of the Institute of France, perhaps the greatest honor which men of science usually receive. The fortune of his life in some other respects was of a mingled complexion. His profession of a physician occupied sufficiently to fetter, without rewarding him. While he was lecturer at the Royal Institution, he was, in his lectures, too profound to be popular, and his office of superintendent of the Nautical Almanac subjected him to much minute labor and many petulant attacks of pamphleteers. On the other hand, he had a leading part in the discovery of the long-sought key to the Egyptian hieroglyphics, and thus the age which was marked by 2 great discoveries, one in science and one in literature, owed them both in a great measure to him. Dr. Young died in 1829, when he had scarcely completed his 56th year. Fresnel was snatched from science still more prematurely, dying in 1827 at the early age of 39. We need not say that both these great philosophers possessed, in an eminent degree, the leading characteristics of the discoverer's mind: perfect clearness of view, rich fertility of invention, and intense love of knowledge. We cannot read without great interest a letter of 118, Fresnel to Young, in November 1824. For a long time that sensibility, or that vanity, which people call love of glory, is much blunted in me. I labor much less to catch the suffrages of the public than to obtain an inward approval which has always been the sweetest reward of my efforts. Without doubt, I have often wanted the spur of vanity to excite me to pursue my researches in moments of disgust and discouragement. But all the compliments which I have received from Arago, de Laplace, or Biot never gave me so much pleasure as the discovery of a theoretical truth or the confirmation of a calculation by experiment. Note 106/9. I was able to give this and some other extracts from the then unedited correspondence of Young and Fresnel by the kindness of the Dean of Ely, Professor Peacock, of Trinity College, Cambridge, whose Life of Dr. Young has since been published. Though Young and Fresnel were in years the contemporaries of many who are now alive, we must consider ourselves as standing towards them in the relation of posterity. The epoch of induction in optics is past. We have now to trace the verification and application of the true theory. Chapter 13. Confirmation and extension of the undulatory theory. After the undulatory theory had been developed in all its main features, by its great authors, Young and Fresnel, although it bore marks of truth that could hardly be fallacious, there was still here, as in the case of other great theories, a period in which difficulties were to be removed, objections answered, men's minds familiarized to the new conceptions thus presented to them, and in which, also, it might reasonably be expected that the theory would be extended to facts not at first included in its domain. This period is, indeed, that in which we are living, and we might, perhaps with propriety, avoid the task of speaking of our living contemporaries. But it would be unjust to the theory not to notice some of the remarkable events characteristic of such a period which have already occurred, and this may be done very simply. 119. In the case of this great theory, as in that of gravitation, by far the most remarkable of these confirmatory researches were conducted by the authors of the discovery, especially Fresnel. And in looking at what he conceived and executed for this purpose, we are, it appears to me, strongly reminded of Newton by the wonderful inventiveness and sagacity with which he devised experiments and applied to them mathematical reasonings. One double refraction of compressed glass. One of these confirmatory experiments was the production of double refraction by the compression of glass. Fresnel observes that though Sir D. Brewster had shown that glass under compression produced colors resembling those which are given by doubly refracting crystals, very skillful physicists had not considered those experiments as a sufficient proof of the bifurcation of the light. In the hypothesis of movable polarization, it is added, there is no apparent connection between these phenomena of coloration and double refraction. But on Young's theory, that the colors arise from two rays which have traversed the crystal with different velocities, it appears almost unavoidable to admit also a difference of path in the two rays. Though, he says, I had long since adopted this opinion, it did not appear to me so completely demonstrated that it was right to neglect an experimental verification of it. And therefore, in 1819, he proceeded to satisfy himself of the fact by the phenomena of diffraction. The trial left no doubt on the subject, but he still thought it would be interesting actually to produce two images in glass by compression, and by a highly ingenious combination calculated to exaggerate the effect of the double refraction, which is very feeble even when the compression is most intense, he obtained two distinct images. This evidence of the dependence of depolarizing structure upon a doubly refracting state of particles, thus excogitated out of the general theory, and verified by trial, may well be considered, as he says, as a new occasion of proving the infallibility of the principle of interferences. To circular polarization. Fresnel then turned his attention to another set of experiments, related to this indeed, but by a tie so recondite that nothing less than his clearness and acuteness of view could have detected any connection. The optical properties of quartz had been perceived to be peculiar from the period of the discovery, 120, of depolarized colors by Arago and Biot. At the end of the notice just quoted, Fresnel says, as soon as my occupations permit me, I propose to employ a pile of prisms similar to that which I have described, in order to study the double refraction of the rays which traverse crystals of quartz in the direction of the axis. He then ventures, without hesitation, to describe beforehand what the phenomena will be. In the Bulletin des Sciences for December 1822, it is stated that experiment had confirmed what he had thus announced. The phenomena are those which have since been spoken of as circular polarization, and the term first occurs in this notice. They are very remarkable, both by their resemblances to, and their differences from, the phenomena of plane polarized light. And the manner in which Fresnel was led to this anticipation of the facts is still more remarkable than the facts themselves. Having ascertained by observation that two differently polarized rays, totally reflected at the internal surface of glass, suffer different retardations of their undulations, he applied the formulae which he had obtained for the polarizing effect of reflection to this case. But in this case the formulae expressed an impossibility, yet as algebraical formulae, even in such cases, have often some meaning, I interpreted, he says, in the manner which appeared to me most natural and most probable, what the analysis indicated by this imaginary form. And by such an interpretation, he collected the law of the difference of undulation of the two rays. He was thus able to predict that by two internal reflections in a rhomb, or parallelepiped of glass, of a certain form and position, a polarized ray would acquire a circular undulation of its particles. And this constitution of the ray, it appeared, by reasoning further, would show itself by its possessing peculiar properties, partly the same as those of polarized light and partly different. This extraordinary anticipation was exactly confirmed, and thus the apparently bold and strange guess of the author was fully justified, or at least assented to, even by the most cautious philosophers. As I cannot appreciate the mathematical evidence for the nature of circular polarization, says Prof. Airy, I shall mention the experimental evidence on which I receive it. The conception has since been universally adopted. But Fresnel, having thus obtained circularly polarized rays, saw 121 that he could account for the phenomena of quartz, already observed by M. Arago, as we have noticed in chapter Roman 9. By supposing two circularly polarized rays to pass, with different velocities along the axis. The curious succession of colors, following each other in right-handed or left-handed circular order, of which we have already spoken, might thus be hypothetically explained. But was this hypothesis of two circularly polarized rays, traveling along the axis of such crystals, to be received merely because it accounted for the phenomena? Fresnel's ingenuity again enabled him to avoid such a defect in theorizing. If there were two such rays, they might be visibly separated by the same artifice, of a pile of prisms properly achromatized, which he had used for compressed glass. The result was that he did obtain a visible separation of the rays, and this result has since been confirmed by others. For instance, Professor Airy. The rays were found to be in all respects identical with the circularly polarized rays produced by the internal reflections in Fresnel's rhomb. This kind of double refraction gave a hypothetical explanation of the laws which M. Biot had obtained for the phenomena of this class. For example, the rule that the deviation of the plane of polarization of the emergent ray is inversely as the square of the length of an undulation for each kind of rays. And thus the phenomena produced by light passing along the axis of quartz were reduced into complete conformity with the theory. I believe, however, Fresnel did not deduce the phenomenon from the mathematical formula without the previous suggestion of experiment. He observed appearances which implied a difference of retardation in the two differently polarized rays at total reflection, as Sir D. Brewster observed in reflection of metals phenomena having a like character. The general fact being observed, Fresnel used the theory to discover the law of this retardation, and to determine a construction in which, one ray being a quarter of an undulation retarded more than the other, circular polarization would be produced. And this anticipation was verified by the construction of his rhomb. As a still more curious verification of this law, another of Fresnel's experiments may be mentioned. He found the proper angles for a circularly polarizing glass rhomb on the supposition that there were 122 four internal reflections instead of two of the four taking place when the surface of the glass was dry, and two when it was wet. The rhomb was made, and when all the points of reflection were dry, the light was not circularly polarized. When 2 points were wet, the light was circularly polarized, and when all 4 were wet, it was not circularly polarized. 3 elliptical polarization in quartz. We now come to one of the few additions to Fresnel's theory which have been shown to be necessary. He had accounted fully for the colors produced by the rays which travel along the axis of quartz crystals, and thus for the colors and changes of the central spot, which is produced when polarized light passes through a transverse plate of such crystals. But this central spot is surrounded by rings of colors. How is the theory to be extended to these? This extension has been successfully made by Professor Airy. His hypothesis is that as rays passing along the axis of a quartz crystal are circularly polarized, rays which are oblique to the axis are elliptically polarized, the amount of ellipticity depending in some unknown manner upon the obliquity, and that each ray is separated by double refraction into 2 rays polarized elliptically, the one right-handed, the other left-handed. By means of these suppositions, he not only was enabled to account for the simple phenomena of single plates of quartz, but for many most complex and intricate appearances which arise from the superposition of 2 plates, and which at first sight might appear to defy all attempts to reduce them to law and symmetry, such as spirals, curves approaching to a square form, curves broken in 4 places. I can hardly imagine, he says, very naturally, that any other supposition would represent the phenomena to such extreme accuracy. I am not so much struck with the accounting for the continued dilatation of circles and the general representation of the forms of spirals, as with the explanations of the minute deviations from symmetry, as when circles become almost square and crosses are inclined to the plane of polarization. and I believe that anyone who shall follow my investigation and imitate my experiments will be surprised at their perfect agreement. Differential equations of elliptical polarization. Although circular and elliptical polarization can be clearly conceived, and their existence, it would seem, irresistibly established by the phenomena, it 123 is extremely difficult to conceive any arrangement of the particles of bodies by which such motions can mechanically be produced. And this difficulty is the greater, because some fluids and some gases impress a circular polarization upon light. In which cases we cannot imagine any definite arrangement of the particles, such as might form the mechanism requisite for the purpose. Accordingly, it does not appear that anyone has been able to suggest even a plausible hypothesis on that subject. Yet, even here, something has been done. Professor Mac Cullog of Dublin has discovered that by slightly modifying the analytical expressions resulting from the common case of the propagation of light, we may obtain other expressions which would give rise to such motions as produce circular and elliptical polarization. And though we cannot as yet assign the mechanical interpretation of the language of analysis thus generalized, this generalization brings together and explains by one common numerical supposition two distinct classes of facts, a circumstance which, in all cases, entitles an hypothesis to a very favorable consideration. Mr. Mac Cullog's assumption consists in adding to the two equations of motion which are expressed by means of second differentials, two other terms involving third differentials in a simple and symmetrical manner. In doing this, he introduces a coefficient, of which the magnitude determines both the amount of rotation of the polarization of a ray passing along the axis, as observed and measured by Biot, and the ellipticity of the polarization of a ray which is oblique to the axis, according to Mr. Airy's theory, of which ellipticity that philosopher also had obtained certain measures. The agreement between the two sets of measures thus brought into connection is such as very strikingly to confirm Mr. Mac Cullog's hypothesis. It appears probable, too, that the confirmation of this hypothesis involves, although in an obscure and oracular form, a confirmation of the undulatory theory, which is the starting point of this curious speculation. Elliptical polarization of metals. The effect of metals upon the light which they reflect was known from the first to be different from that which transparent bodies produce. Sir David Brewster, who has recently examined this subject very fully, has described the modification thus produced as elliptic polarization. In employing this term, he seems to have been led, it has been observed, by a 124 desire to avoid as much as possible all reference to theory. The laws which he has obtained, however, belong to elliptically polarized light in the sense in which the term was introduced by Fresnel. And the identity of the light produced by metallic reflection with the elliptically polarized light of the wave theory is placed beyond all doubt by an observation of Professor Airy that the rings of uniaxial crystals produced by Fresnel's elliptically polarized light are exactly the same as those produced by Brewster's metallic light. Newton's rings by polarized light. Other modifications of the phenomena of thin plates by the use of polarized light supplied other striking confirmations of the theory. These were in one case the more remarkable, since the result was foreseen by means of a rigorous application of the conception of the vibratory motion of light and confirmed by experiment. Professor Airy of Cambridge was led by his reasonings to see that if Newton's rings are produced between a lens and a plate of metal by polarized light, then up to the polarizing angle, the central spot will be black, and instantly beyond this, it will be white. In a note in which he announced this, he says, "This I anticipated from Fresnel's expressions. It is confirmatory of them and defies omission." He also predicted that, when the rings were produced between two substances of very different refractive powers, the center would twice pass from black to white and from white to black by increasing the angle, which anticipation was fulfilled by using a diamond for the higher refraction. Note 121/9, addressed to myself, dated May 28, 1831. I ought, however, to notice that this experiment had been made by M. Arago 15 years earlier and published, though not then recollected by Mr. Airy. Conical refraction in the same manner. Professor Hamilton of Dublin pointed out that according to the Fresnelian doctrine of double refraction, there is a certain direction of a crystal in which a single ray of light will be refracted so as to form a conical pencil. For the direction of the refracted ray is determined by a plane which touches the wave surface, the rule being that the ray must pass from the center of the surface to the point of contact. And though in general this contact gives a single point only, it so happens, from the peculiar inflected form of the wave surface, which has what is called a cusp, that in one particular position, the plane can touch the surface in an entire circle. Thus the general rule which assigns the path of 125, the refracted ray would, in this case, guide it from the center of the surface to every point in the circumference of the circle, and thus make it a cone. This very curious and unexpected result, which Professor Hamilton thus obtained from the theory, his friend Professor Lloyd verified as an experimental fact. We may notice, also, that Professor Lloyd found the light of the conical pencil to be polarized according to a law of an unusual kind, but one which was easily seen to be in complete accordance with the theory. 8. Fringes of shadows. The phenomena of the fringes of shadows of small holes and groups of holes, which had been the subject of experiment by Fraunhofer, were at a later period carefully observed in a vast variety of cases by M. Schwert of Spires, and published in a separate work, Bewegungserscheinungen, Phenomena of Inflection, 1836. In this treatise, the author has with great industry and skill calculated the integrals which, as we have seen, are requisite in order to trace the consequences of the theory. And the accordance which he finds between these and the varied and brilliant results of observation is throughout exact. I shall, says he in the preface, prove by the present treatise that all inflection phenomena, through openings of any form, size, and arrangement, are not only explained by the undulation theory, but that they can be represented by analytical expressions, determining the intensity of the light in any point whatever. And he justly adds that the undulation theory accounts for the phenomena of light as completely as the theory of gravitation does for the facts of the solar system. Note 123/9. Die Bewegungserscheinungen aus dem Fundamentalgesetz der Undulationstheorie analytisch entwickelt und in Bildern dargestellt, von F. M. Schwert. Mannheim, 1835. Objections to the theory. We have hitherto mentioned only cases in which the undulatory theory was either entirely successful in explaining the facts, or at least hypothetically consistent with them and with itself. But other objections were started, and some difficulties were long considered as very embarrassing. Objections were made to the theory by some English experimenters, as Mr. Potter, Mr. Barton, and others. These appeared in scientific journals and were afterwards answered in similar publications. The objections depended partly on the measure of the intensity of light in the different points of the phenomena, a datum which it is very difficult to obtain with accuracy, 126, by experiment, and partly on misconceptions of the theory, and I believe there are none of them which would now be insisted on. We may mention, also, another difficulty, which it was the habit of the opponents of the theory to urge as a reproach against it, long after it had been satisfactorily explained. I mean the half-undulation which Young and Fresnel had found it necessary, in some cases, to assume as gained or lost by one of the rays. Though they and their followers could not analyze the mechanism of reflection with sufficient exactness to trace out all the circumstances, it was not difficult to see, upon Fresnel's principles, that reflection from the interior and exterior surface of glass must be of opposite kinds, which might be expressed by supposing one of these rays to lose half an undulation. And thus there came into view a justification of the step which had originally been taken upon empirical grounds alone. 10. Dispersion, on the undulatory theory. A difficulty of another kind occasioned a more serious and protracted embarrassment to the cultivators of this theory. This was the apparent impossibility of accounting, on the theory, for the prismatic dispersion of color, for it had been shown by Newton that the amount of refraction is different for every color, and the amount of refraction depends on the velocity with which light is propagated. Yet the theory suggested no reason why the velocity should be different for different colors, for by mathematical calculation, vibrations of all degrees of rapidity, in which alone colors differ, are propagated with the same speed. Nor does analogy lead us to expect this variety. There is no such difference between quick and slow waves of air. The sounds of the deepest and the highest bells of a peal are heard at any distance in the same order. Here, therefore, the theory was at fault. But this defect was far from being a fatal one. For though the theory did not explain, it did not contradict dispersion. The suppositions on which the calculations had been conducted and the analogy of sound were obviously in no small degree precarious. The velocity of propagation might differ for different rates of undulation, in virtue of many causes which would not affect the general theoretical results. Many such hypothetical causes were suggested by various eminent mathematicians as solutions of this conspicuous difficulty. But without dwelling upon these conjectures, it may suffice to notice that hypothesis upon which the attention of mathematicians was soon concentrated. This was the hypothesis of finite intervals between the 127 particles of the ether. The length of one of those undulations which produce light is a very small quantity, its mean value being 1/50,000th of an inch. But in the previous investigations of the consequences of the theory, it had been assumed that the distance from each other of the particles of the ether, which, by their attractions or repulsions, cause the undulations to be propagated, is indefinitely less than this small quantity, so that its amount might be neglected in the cases in which the length of the undulation was one of the quantities which determined the result. But this assumption was made arbitrarily, as a step of simplification, and because it was imagined that, in this way, a nearer approach was made to the case of a continuous fluid ether, which the supposition of distinct particles imperfectly represented. It was still free for mathematicians to proceed upon the opposite assumption, of particles of which the distances were finite, either as a mathematical basis of calculation or as a physical hypothesis. And it remained to be seen if, when this was done, the velocity of light would still be the same for different lengths of undulation, that is, for different colors. M. Cauchy, calculating, upon the most general principles, the motion of such a collection of particles as would form an elastic medium, obtained results which included the new extension of the previous hypothesis. Professor Powell of Oxford applied himself to reduce to calculation, and to compare with experiment the result of these researches. And it appeared that, on M. Cauchy's principles, a variation in the velocity of light is produced by a variation in the length of the wave, provided that the interval between the molecules of the ether bears a sensible ratio to the length of an undulation. Professor Powell obtained also, from the general expressions, a formula expressing the relation between the refractive index of a ray and the length of a wave or the color of light. It then became his task to ascertain whether this relation obtained experimentally, and he found a very close agreement between the numbers which resulted from the formula and those observed by Fraunhofer for 10 different kinds of media, namely, certain glasses and fluids. To these, he afterwards added 10 other cases of crystals observed by M. Rudberg. Mr. Kelland of Cambridge also calculated, in a manner somewhat different, the results of the same hypothesis of finite intervals, and, obtaining 128 formulae not exactly the same as Professor Powell, found also an agreement between these and Fraunhofer's observations. It may be observed that the refractive indices observed and employed in these comparisons were not those determined by the color of the ray, which is not capable of exact identification, but those more accurate measures which Fraunhofer was enabled to make, in consequence of having detected in the spectrum the black lines which he called B, C, D, E, F, G, H. The agreement between the theoretical formulae and the observed numbers is remarkable. Throughout all the series of comparisons of which we have spoken, yet we must at present hesitate to pronounce upon the hypothesis of finite intervals as proved by these calculations. For though this hypothesis has given results agreeing so closely with experiment, it is not yet clear that other hypotheses may not produce an equal agreement. By the nature of the case, there must be a certain gradation and continuity in the succession of colors in the spectrum, and hence, any supposition which will account for the general fact of the whole dispersion may possibly account for the amount of the intermediate dispersions, because these must be interpolations between the extremes. The result of this hypothetical calculation, however, shows very satisfactorily that there is not in the fact of dispersion anything which is at all formidable to the undulatory theory. 11. Conclusion. There are several other of the more recondite points of the theory which may be considered as, at present, too undecided to allow us to speak historically of the discussions which they have occasioned. For example, it was conceived, for some time, that the vibrations of polarized light are perpendicular to the plane of polarization. But this assumption was not an essential part of the theory, and all the phenomena would equally allow us to suppose the vibrations to be in the polarization plane, the main requisite being that light polarized in planes at right angles to each other should also have the vibrations at right angles. Accordingly, for some time, this point was left undecided by Young and Fresnel, and more recently, some mathematicians have come to the opinion that ether vibrates in the plane of polarization. The theory of transverse vibrations is equally stable, whichever supposition may be finally confirmed. Note 130/9, for on account of these, see Professor Lloyd's report on physical optics. Britt, Asok, Report, 1834. We may speak in the same manner of the suppositions which, from 129, the time of Young and Fresnel, the cultivators of this theory have been led to make respecting the mechanical constitution of the ether, and the forces by which transverse vibrations are produced. It was natural that various difficulties should arise upon such points, for transverse vibrations had not previously been made the subject of mechanical calculation, and the forces which occasion them must act in a different manner from those which were previously contemplated. Still, we may venture to say, without entering into these discussions, that it has appeared, from all the mathematical reasonings which have been pursued, that there is not, in the conception of transverse vibrations, anything inconsistent either with the principles of mechanics, or with the best general views which we can form, of the forces by which the universe is held together. I willingly speak as briefly as the nature of my undertaking allows, of those points of the undulatory theory which are still under deliberation among mathematicians. With respect to these, an intimate acquaintance with mathematics and physics is necessary to enable anyone to understand the steps which are made from day to day, and still higher philosophical qualifications would be requisite in order to pronounce a judgment upon them. I shall therefore conclude this survey by remarking the highly promising condition of this great department of science in respect to the character of its cultivators. Nothing less than profound thought and great mathematical skill can enable anyone to deal with this theory, in any way likely to promote the interests of science. But there appears, in the horizon of the scientific world, a considerable class of young mathematicians who are already bringing to these investigations the requisite talents and zeal, and who, having acquired their knowledge of the theory since the time when its acceptation was doubtful, possess, without effort, that singleness and decision of view as to its fundamental doctrines, which it is difficult for those to attain whose minds have had to go through the hesitation, struggle, and balance of the epoch of the establishment of the theory. In the hands of this new generation, it is reasonable to suppose the analytical mechanics of light will be improved as much as the analytical mechanics of the solar system was by the successors of Newton. We have already had to notice many of this younger race of undulationists. For besides Mcauchy, Poisson, and Ampere, M. Lemay has been more recently following these researches in France. In 130 Belgium, M. Quetelet has given great attention to them, and in our own country, Sir William Hamilton and Professor Lloyd of Dublin have been followed by Mr. MacCulloch. Professor Powell of Oxford has continued his researches with unremitting industry, and at Cambridge, Professor Airy, who did much for the establishment and diffusion of the theory before he was removed to the post of Astronomer Royal at Greenwich, has had the satisfaction to see his labors continued by others, even to the most recent time. For Mr. Kelland, whom we have already mentioned, and Mr. Archibald Smith, the two persons who, in 1834 and 1836, received the highest mathematical honors which that university can bestow, have both of them published investigations respecting the undulatory theory. Note 132/9 on the dispersion of light as explained by the hypothesis of finite intervals. Cam, Trans Volume Roman 6, p. 153. Note 133/9, Investigation of the Equation to Fresnel's Wave Surface, Ib. p. 85. See also, in the same volume, Mathematical Considerations on the Problem of the Rainbow, showing it to belong to physical optics by R. Potter, Esquire, of Queen's College. We may be permitted to add, as a reflection obviously suggested by these facts, that the cause of the progress of science is incalculably benefited by the existence of a body of men, trained and stimulated to the study of the higher mathematics, such as exist in the British universities, who are thus prepared, when an abstruse and sublime theory comes before the world with all the characters of truth, to appreciate its evidence, to take steady hold of its principles, to pursue its calculations, and thus to convert into a portion of the permanent treasure and inheritance of the civilized world, discoveries which might otherwise expire with the great geniuses who produced them, and be lost for ages, as, in former times, great scientific discoveries have sometimes been. The reader who is acquainted with the history of recent optical discovery will see that we have omitted much which has justly excited admiration, as, for example, the phenomena produced by glass under heat or pressure, noticed by Lobeck and Biot and Brewster, and many most curious properties of particular minerals. We have omitted, too, all notice of the phenomena and laws of the absorption of light, which hitherto stand unconnected with the theory. But in this we have not materially deviated from our main design, for our end, in what we have done, has been to trace the advances of optics, 131, towards perfection as a theory, and this task we have now nearly executed as far as our abilities allow. We have been desirous of showing that the type of this progress in the histories of the two great sciences, physical astronomy and physical optics, is the same. In both, we have many laws of phenomena detected and accumulated by acute and inventive men. We have preludial guesses which touch the true theory, but which remain for a time imperfect, undeveloped, unconfirmed. Finally, we have the epoch when this true theory, clearly apprehended by great philosophical geniuses, is recommended by its fully explaining what it was first meant to explain, and confirmed by its explaining what it was not meant to explain. We have then its progress struggling for a little while with adverse prepossessions and difficulties, finally overcoming all these, and moving onwards, while its triumphal procession is joined by all the younger and more vigorous men of science. It would, perhaps, be too fanciful to attempt to establish a parallelism between the prominent persons who figure in these two histories. If we were to do this, we must consider Huygens and Hooke as standing in the place of Copernicus, since, like him, they announced the true theory, but left it to a future age to give it development and mechanical confirmation. Malus and Brewster, grouping them together, correspond to Tycho Brahe and Kepler, laborious in accumulating observations, inventive and happy in discovering laws of phenomena, and Young and Fresnel combined make up the Newton of optical science. In the report on physical optics, Britt, Ass, reports 1834, by Prof. Lloyd, the progress of the mathematical theory after Fresnel's labors is stated more distinctly than I have stated it, to the following effect. Ampere, in 1828, proved Fresnel's mathematical results directly, which Fresnel had only proved indirectly, and derived from his proof Fresnel's beautiful geometrical construction. Prof. MacCulloch not long after gave a concise demonstration of the same theorem, and of the other principal points of Fresnel's theory. He represents the elastic force by means of an ellipsoid whose axes are inversely proportional to those of Fresnel's generating ellipsoid, and deduces Fresnel's construction geometrically. In the third supplement to his essay on the theory of systems of rays, trans Ri Acad. Volume Roman 17. Sir W. Hamilton has presented that portion of Fresnel's theory which relates to the fundamental problem of the determination of the velocity and polarization of a plane wave, in a very elegant and analytical form. This he does by means of what he calls the 132 characteristic function of the optical system to which the problem belongs. From this function is deduced the surface of wave slowness of the medium, and by means of this surface, the direction of the rays refracted into the medium. From this construction also Sir W. Hamilton was led to the anticipation of conical refraction, mentioned above. The investigations of Mcauchy and Lemay refer to the laws by which the particles of the ether act upon each other and upon the particles of other bodies. A field of speculation which appears to me not yet ripe for the final operations of the analyst. Among the mathematicians who have supplied defects in Fresnel's reasoning on this subject, I may mention Mr. Tovey, who treated it in several papers in the Philosophical Magazine, 1837-40. Mr. Tovey's early death must be deemed a loss to mathematical science. Besides investigating the motion of symmetrical systems of particles which may be supposed to correspond to biaxial crystals, Mr. Tovey considered the case of unsymmetrical systems and found that the undulations propagated would, in the general case, be elliptical, and that in a particular case, circular undulations would take place, such as are propagated along the axis of quartz. It appears to me, however, that he has not given a definite meaning to those limitations of his general hypothesis, which conduct him to this result. Perhaps if the hypothetical conditions of this result were traced into detail, they would be found to reside in a screw-like arrangement of the elementary particles, in some degree such as crystals of quartz themselves exhibit in their forms, when they have plagiahedral faces at both ends. Such crystals of quartz are, some like a right-handed, and some like a left-handed screw, and, as Sir John Herschel discovered, the circular polarization is right-handed or left-handed according as the plagiahedral form is so. In Mr. Tovey's hypothetical investigation, it does not appear upon what part of the hypothesis this difference of right and left-handed depends. The definition of this part of the hypothesis is a very desirable step. When crystals of quartz are right-handed at one end, they are right-handed at the other end. But there is a different kind of plagiahedral form, which occurs in some other crystals, for instance, in apatite. In these, the plagiahedral faces are right-handed at the one extremity and left-handed at the other. For the sake of distinction, we may call the former homologous plagiahedral faces, since at both ends they have the same name, and the latter heterologous plagiahedral faces. 133. The homologous plagiahedral faces of quartz crystals are accompanied by homologous circular polarization of the same name. I do not know that heterologous circular polarization has been observed in any crystal, but it has been discovered by Dr. Faraday to occur in glass, and C, when subjected to powerful magnetic action. Perhaps it was presumptuous in me to attempt to draw such comparisons, especially with regard to living persons, as I have done in the preceding pages of this book. Having published this passage, however, I shall not now suppress it. But I may observe that the immense number and variety of the beautiful optical discoveries, which we owe to Sir David Brewster, makes the comparison in his case a very imperfect representation of his triumphs over nature. And that, besides his place in the history of the theory of optics, he must hold a most eminent position in the history of optical crystallography, whenever the discovery of a true optical theory of crystals supplies us with the epoch to which his labors in this field form so rich a prelude. I cordially assent to the expression employed by Mr. Airy in the Phil. Trans for 1840, in which he speaks of Sir David Brewster as the father of modern experimental optics. 135, Book 10. Secondary Mechanical Sciences, continued. History of Thermotics and Atmology. Et primum faciunt ignum si vorter in horas iris. Hinc imbrem gigni terramque criri ex imbri, retroque a terra cuncta revorti, humorum primum, post aera deigned calorum, nec cesser hic inter si mutare, mir de silo ad terram de terra ad sidera mundi. Lucretius, I 783. Water and air and fire alternate run their endless circle, multiform yet one. For molded by the fervor's latent beams, solids flow loose and fluids flash to steams, and elemental flame with secret force pursues through earth, air, sky its stated course. 137. Introduction. Of Thermotics and Atmology. I employ the term thermotics to include all the doctrines respecting heat, which have hitherto been established on proper scientific grounds. Our survey of the history of this branch of science must be more rapid and less detailed than it has been in those subjects of which we have hitherto treated. For our knowledge is, in this case, more vague and uncertain than in the others, and has made less progress towards a general and certain theory. Still, the narrative is too important and too instructive to be passed over. The distinction of formal thermotics and physical thermotics, of the discovery of the mere laws of phenomena, and the discovery of their causes is applicable here, as in other departments of our knowledge. But we cannot exhibit, in any prominent manner, the latter division of the science now before us, since no general theory of heat has yet been propounded, which affords the means of calculating the circumstances of the phenomena of conduction, radiation, expansion, and change of solid, liquid, and gaseous form. Still, on each of these subjects there have been proposed and extensively assented to certain general views, each of which explains its appropriate class of phenomena. And in some cases, these principles have been clothed in precise and mathematical conditions, and thus made bases of calculation. These principles, thus possessing a generality of a limited kind, connecting several observed laws of phenomena, but yet not connecting all the observed classes of facts which relate to heat, will require our separate attention. They may be described as the doctrine of conduction, the doctrine of radiation, the doctrine of specific heat, and the doctrine of latent heat. And these, and similar doctrines respecting heat, make up the science which we may call thermotics proper. But besides these collections of principles which regard heat by itself, the relations of heat and moisture give rise to another and important collection of laws and principles, which I shall treat of in connection with thermotics, and shall term etymology, borrowing 138, the term from the Greek word, letter 1F04 tau mu omicron sigma, which signifies vapor. The atmosphere was so named by the Greeks, as being a sphere of vapor, and undoubtedly the most general and important of the phenomena which take place in the air, by which the earth is surrounded, are those in which water of one consistence or other, ice, water, or steam, is concerned. The knowledge which relates to what takes place in the atmosphere has been called meteorology in its collective form, but such knowledge is, in fact, composed of parts of many different sciences. And it is useful for our purpose to consider separately those portions of meteorology which have reference to the laws of aqueous vapor, and these we may include under the term etymology. The instruments which have been invented for the purpose of measuring the moisture of the air, that is, the quantity of vapor which exists in it, have been termed hygrometers, and the doctrines on which these instruments depend, and to which they lead, have been called hygrometry. But this term has not been used in quite so extensive a sense as that which we intend to affix to etymology. In treating of thermotics, we shall first describe the earlier progress of men's views concerning conduction, radiation, and the like, and shall then speak of the more recent corrections and extensions by which they have been brought nearer to theoretical generality. 139. Thermotics proper. Chapter 1. The doctrines of conduction and radiation. Section 1. Introduction of the doctrine of conduction. By conduction is meant the propagation of heat from one part to another of a continuous body, or from one body to another in contact with it, as when one end of a poker stuck in the fire heats the other end, or when this end heats the hand which takes hold of it. By radiation is meant the diffusion of heat from the surface of a body to points not in contact. It is clear in both these cases that, in proportion as the hot portion is hotter, it produces a greater effect in warming the cooler portion. That is, it communicates more heat to it, if heat be the abstract conception of which this effect is the measure. The simplest rule which can be proposed is that the heat thus communicated in a given instant is proportional to the excess of the heat of the hot body over that of the contiguous bodies. There are no obvious phenomena which contradict the supposition that this is the true law, and it was thence assumed by Newton as the true law for radiation and by other writers for conduction. This assumption was confirmed approximately, and afterwards corrected, for the case of radiation. In its application to conduction, it has been made the basis of calculation up to the present time. We may observe that this statement takes for granted that we have attained to a measure of heat, or of temperature, as heat thus measured is termed, corresponding to the law thus assumed. And, in fact, as we shall have occasion to explain in speaking of the measures of sensible qualities. 140. The thermometrical scale of heat according to the expansion of liquids, which is the measure of temperature here adopted, was constructed with a reference to Newton's law of radiation of heat. And thus the law is necessarily consistent with the scale. In any case in which the parts of a body are unequally hot, the temperature will vary continuously in passing from one part of the body to another. Thus, a long bar of iron, of which one end is kept red hot, will exhibit a gradual diminution of temperature at successive points, proceeding to the other end. The law of temperature of the parts of such a bar might be expressed by the ordinates of a curve which should run alongside the bar. And in order to trace mathematically the consequences of the assumed law, some of those processes would be necessary, by which mathematicians are enabled to deal with the properties of curves, as the method of infinitesimals or the differential calculus, and the truth or falsehood of the law would be determined, according to the usual rules of inductive science, by a comparison of results so deduced from the principle with the observed phenomena. It was easily perceived that this comparison was the task which physical inquirers had to perform, but the execution of it was delayed for some time, partly, perhaps, because the mathematical process presented some difficulties. Even in a case so simple as that above mentioned, of a linear bar with a stationary temperature at one end, partial differentials entered, for there were three variable quantities, the time, as well as the place of each point and its temperature. And at first, another scruple occurred to M. Biot when, about 1804, he undertook this problem. A difficulty, says Laplace in 1809, presents itself, which has not yet been solved. The quantities of heat received and communicated in an instant, by any point of the bar, must be infinitely small quantities of the same order as the excess of the heat of a slice of the body over that of the contiguous slice. Therefore, the excess of the heat received by any slice over the heat communicated is an infinitely small quantity of the second order, and the accumulation in a finite time, which depends on this excess, cannot be finite. I conceive that this difficulty arises entirely from an arbitrary and unnecessary assumption concerning the relation of the infinitesimal parts of the body. Laplace resolved the difficulty by further reasoning founded upon the same assumption which occasioned 141 it. But Fourier, who was the most distinguished of the cultivators of this mathematical doctrine of conduction, follows a course of reasoning in which the difficulty does not present itself. Indeed, it is stated by Laplace, in the memoir above quoted, that Fourier had already obtained the true fundamental equations by views of his own. The remaining part of the history of the doctrine of conduction is principally the history of Fourier's labors. Attention having been drawn to the subject, as we have mentioned, the French Institute, in January 1810, proposed, as their prize question, to give the mathematical theory of the laws of the propagation of heat, and to compare this theory with exact observations. Fourier's memoir, the sequel of one delivered in 1807, was sent in September 1811, and the prize, 3,000 francs, adjudged to it in 1812. In consequence of the political confusion which prevailed in France, or of other causes, these important memoirs were not published by the Academy till 1824. But extracts had been printed in the Bulletin des Sciences in 1808 and in the Annales de Chimie in 1816, and Poisson and M. Cauchy had consulted the manuscript itself. It is not my purpose to give, in this place, an account of the analytical processes by which Fourier obtained his results. The skill displayed in these memoirs is such as to make them an object of just admiration to mathematicians, but they consist entirely of deductions from the fundamental principle which I have noticed, that the quantity of heat conducted from a hotter to a colder point is proportional to the excess of heat, modified by the conductivity or conducting power of each substance. The equations which flow from this principle assume nearly the same forms as those which occur in the most general problems of hydrodynamics. Besides Fourier's solution, Laplace, Poisson, and M. Cauchy have also exercised their great analytical skill in the management of these formulae. We shall briefly speak of the comparison of the results of these reasonings with experiment and notice some other consequences to which they lead. But before we can do this, we must pay some attention to the subject of radiation. 142. Note 4/10. I have given an account of Fourier's mathematical results in the reports of the British Association for 1835. Sect 2. Introduction of the doctrine of radiation. A hot body, as a mass of incandescent iron, emits heat, as we perceive by our senses when we approach it, and by this emission of heat, the hot body cools down. The first step in our systematic knowledge of the subject was made in the Principia. It was in the destiny of that great work, says Fourier, to exhibit, or at least to indicate, the causes of the principal phenomena of the universe. Newton assumed, as we have already said, that the rate at which a body cools, that is, parts with its heat to surrounding bodies, is proportional to its heat. And on this assumption he rested the verification of his scale of temperatures. It is an easy deduction from this law that if times of cooling be taken in arithmetical progression, the heat will decrease in geometrical progression. Kraft, and after him Richman, tried to verify this law by direct experiments on the cooling of vessels of warm water. And from these experiments, which have since been repeated by others, it appears that for differences of temperature which do not exceed 50 degrees, boiling water being 100, this geometrical progression represents, with tolerable, but not with complete, accuracy, the process of cooling. This principle of radiation, like that of conduction, required to be followed out by mathematical reasoning. But it required also to be corrected in the first place, for it was easily seen that the rate of cooling depended not on the absolute temperature of the body, but on the excess of its temperature above the surrounding objects to which it communicated its heat in cooling. And philosophers were naturally led to endeavor to explain or illustrate this process by some physical notions. Lambert, in 1765, published an essay on the force of heat, in which he assimilates the communication of heat to the flow of a fluid out of one vessel into another by an excess of pressure, and mathematically deduces the laws of the process on this ground. But some additional facts suggested a different view of the subject. It was found that heat is propagated by radiation according to straight lines, like light, and that it is, as light is, capable of being reflected by mirrors and thus brought to a focus of intenser action. In this manner, the radiative effect of a body could be more precisely traced. A fact, however, came under notice, which, at first sight, appeared to 143 offer some difficulty. It appeared that cold was reflected no less than heat. A mass of ice, when its effect was concentrated on a thermometer by a system of mirrors, made the thermometer fall just as a vessel of hot water placed in a similar situation made it rise. Was cold, then, to be supposed a real substance, no less than heat? The solution of this and similar difficulties was given by Pierre Prévost, professor at Geneva, whose theory of radiant heat was proposed about 1790. According to this theory, heat, or caloric, is constantly radiating from every point of the surface of all bodies in straight lines, and it radiates the more copiously, the greater is the quantity of heat which the body contains. Hence, a constant exchange of heat is going on among neighboring bodies, and a body grows hotter or colder, according as it receives more caloric than it emits, or the contrary. And thus a body is cooled by rectilinear rays from a cold body, because along these paths it sends rays of heat in greater abundance than those which return the same way. This theory of exchanges is simple and satisfactory, and was soon generally adopted, but we must consider it rather as the simplest mode of expressing the dependence of the communication of heat on the excess of temperature, than as a proposition of which the physical truth is clearly established. A number of curious researches on the effect of the different kinds of surface of the heating and of the heated body were made by Leslie and others. On these I shall not dwell, only observing that the relative amount of this radiative and receptive energy may be expressed by numbers for each kind of surface, and that we shall have occasion to speak of it under the term exterior conductivity. It is thus distinguished from interior conductivity, which is the relative rate at which heat is conducted in the interior of bodies. Note 6/10. The term employed by Fourier, conductibility or conducibility, suggests expressions altogether absurd, as if the bodies could be called conductible or conducible with respect to heat. I have therefore ventured upon a slight alteration of the word, and have used the abstract term which analogy would suggest, if we suppose bodies to be conductive in this respect. Sect. 3. Verifications of the doctrines of conduction and radiation. The interior and exterior conductivity of bodies are numbers, which enter as elements or coefficients into the mathematical calculations founded on the doctrines of conduction and radiation. These 144 coefficients are to be determined for each case by appropriate experiments. When the experimenters had obtained these data, as well as the mathematical solutions of the problems, they could test the truth of their fundamental principles by a comparison of the theoretical and actual results in properly selected cases. This was done for the law of conduction in the simple cases of metallic bars heated at one end by M. Biot, and the accordance with experiment was sufficiently close. In the more complex cases of conduction which Fourier considered, it was less easy to devise a satisfactory mode of comparison. But some rather curious relations, which he demonstrated to exist among the temperatures at different points of an armil, or ring, afforded a good criterion of the value of the calculations, and confirmed their correctness. We may therefore presume these doctrines of radiation and conduction to be sufficiently established, and we may consider their application to any remarkable case to be a portion of the history of science. We proceed to some such applications. Sect 4. The geological and cosmological application of thermotics. By far the most important case to which conclusions from these doctrines have been applied is that of the globe of the Earth and of those laws of climate to which the modifications of temperature give rise. And in this way, we are led to inferences concerning other parts of the universe. If we had any means of observing these terrestrial and cosmical phenomena to a sufficient extent, they would be valuable facts on which we might erect our theories, and they would thus form part, not of the corollaries, but of the foundations of our doctrine of heat. In such a case, the laws of the propagation of heat, as discovered from experiments on smaller bodies, would serve to explain these phenomena of the universe, just as the laws of motion explain the celestial movements. But since we are almost entirely without any definite indications of the condition of the other bodies in the solar system as to heat, and since, even with regard to the Earth, we know only the temperature of the parts at or very near the surface, our knowledge of the part which heat plays in the Earth and the heavens must be in a great measure, not a generalization of observed facts, but a deduction from theoretical principles. Still, such knowledge, whether obtained, 145 from observation or from theory, must possess great interest and importance. The doctrines of this kind which we have to notice refer principally to the effect of the sun's heat on the Earth, the laws of climate, the thermotical condition of the interior of the Earth, and that of the planetary spaces. One effect of solar heat on the Earth that the sun's heat passes into the interior of the Earth in a variable manner, depending upon the succession of days and nights, summers and winters, is an obvious consequence of our first notions on this subject. The mode in which it proceeds into the interior, after descending below the surface, remain to be gathered, either from the phenomena or from reasoning. Both methods were employed. Saussure endeavored to trace its course by digging in 1785, and thus found that at the depth of about 31 feet, the annual variation of temperature is about 1/12 what it is at the surface. Leslie adopted a better method, sinking the bulbs of thermometers deep in the earth, while their stems appeared above the surface. In 1813, 16, and 17, he observed thus the temperatures at the depths of 1, 2, 4, and 8 feet, at Abbotshall, in Fifeshire. The results showed that the extreme annual oscillations of the temperature diminish as we descend. At the depth of 1 foot, the yearly range of oscillation was 25 degrees Fahrenheit. At 2 feet, it was 20 degrees. At 4 feet, it was 15 degrees. At 8 feet, it was only 9 degrees and a half. And the time at which the heat was greatest was later and later in proceeding to the lower points. At 1 foot, the maximum and minimum were 3 weeks after the solstice of summer and of winter. At 2 feet, they were 4 or 5 weeks. At 4 feet, they were 2 months. And at 8 feet, 3 months. The mean temperature of all the thermometers was nearly the same. Similar results were obtained by Ott at Zurich in 1762 and by Herrenschneider at Strasbourg in 1821, 2, 3. These results had already been explained by Fourier's theory of conduction. He had shown that when the surface of a sphere is affected by a periodical heat, certain alternations of heat travel uniformly into the interior, but that the extent of the alternation diminishes in geometrical progression in this descent. This conclusion applies to the effect of days and years on the temperature of the Earth, and shows that such facts as those observed by Leslie are both exemplifications of 146, the general circumstances of the Earth, and are perfectly in accordance with the principles on which Fourier's theory rests. Climate. The term climate, which means inclination, was applied by the ancients to denote that inclination of the axis of the terrestrial sphere from which result the inequalities of days in different latitudes. This inequality is obviously connected also with a difference of thermotical condition. Places near the poles are colder, on the whole, than places near the equator. It was a natural object of curiosity to determine the law of this variation. Such a determination, however, involves many difficulties and the settlement of several preliminary points. How is the temperature of any place to be estimated? And if we reply by its mean temperature, how are we to learn this mean? The answers to such questions require very multiplied observations, exact instruments, and judicious generalizations, and cannot be given here. But certain first approximations may be obtained without much difficulty. For instance, the mean temperature of any place may be taken to be the temperature of deep springs, which is probably identical with the temperature of the soil below the reach of the annual oscillations. Proceeding on such facts, Mayer found that the mean temperature of any place was nearly proportional to the square of the cosine of the latitude. This, as a law of phenomena, has since been found to require considerable correction, and it appears that the mean temperature does not depend on the latitude alone, but on the distribution of land and water and on other causes. M. de Humboldt has expressed these deviations by his map of isothermal lines, and Sir D. Brewster has endeavored to reduce them to a law by assuming two poles of maximum cold. Note 12/10, British Assoc, 1833, Prof. Forbes' Report on Meteorology, p. 215. The expression which Fourier finds for the distribution of heat in a homogeneous sphere is not immediately comparable with Mayer's empirical formula, being obtained on a certain hypothesis, namely, that the equator is kept constantly at a fixed temperature. But there is still a general agreement, for according to the theory, there is a diminution of heat in proceeding from the equator to the poles in such a case. The heat is propagated from the equator and the neighboring parts and radiates out from the poles into the surrounding space. And thus, in the case of the Earth, the solar heat enters in the tropical, 147 parts, and constantly flows towards the polar regions, by which it is emitted into the planetary spaces. Climate is affected by many thermotic influences, besides the conduction and radiation of the solid mass of the Earth. The atmosphere, for example, produces upon terrestrial temperatures effects which it is easy to see are very great, but these it is not yet in the power of calculation to appreciate, and it is clear that they depend upon other properties of air besides its power to transmit heat. We must therefore dismiss them, at least for the present. Temperature of the interior of the Earth. The question of the temperature of the interior of the Earth has excited great interest, in consequence of its bearing on other branches of knowledge. The various facts which have been supposed to indicate the fluidity of the central parts of the terrestrial globe belong, in general, to geological science. But so far as they require the light of thermotical calculations in order to be rightly reasoned upon, they properly come under our notice here. The principal problem of this kind which has been treated of is this: if in the globe of the Earth there be a certain original heat, resulting from its earlier condition and independent of the action of the sun, to what results will this give rise? And how far do the observed temperatures of points below the surface lead us to such a supposition? It has, for instance, been asserted that in many parts of the world the temperature, as observed in mines and other excavations, increases in descending at the rate of 1 degree centesimal in about 40 yards. What inference does this justify? The answer to this question was given by Fourier and by Laplace. The former mathematician had already considered the problem of the cooling of a large sphere in his memoirs of 1807, 1809, and 1811. These, however, lay unpublished in the archives of the Institute for many years. But in 1820, when the accumulation of observations which indicated an increase of the temperature of the Earth as we descend had drawn observation to the subject, Fourier gave, in the Bulletin of the Philomathic Society, a summary of his results, as far as they bore on this point. His conclusion was that such an increase of temperature in proceeding towards the center of the Earth can arise from nothing but the remains of a primitive heat, that the heat which the sun's action would communicate would, in its final and 148 permanent state, be uniform in the same vertical line, as soon as we get beyond the influence of the superficial oscillations of which we have spoken. And that, before the distribution of temperature reaches this limit, it will decrease, not increase, in descending. It appeared also, by the calculation, that this remaining existence of the primitive heat in the interior of the Earth's mass was quite consistent with the absence of all perceptible traces of it at the surface, and that the same state of things which produces an increase of 1 degree of heat in descending 40 yards does not make the surface a quarter of a degree hotter than it would otherwise be. Fourier was led also to some conclusions, though necessarily very vague ones, respecting the time which the Earth must have taken to cool from a supposed original state of incandescence to its present condition, which time it appeared must have been very great, and respecting the extent of the future cooling of the surface, which it was shown must be insensible. Everything tended to prove that, within the period which the history of the human race embraces, no discoverable change of temperature had taken place from the progress of this central cooling. Laplace further calculated the effect which any contraction of the globe of the Earth by cooling would produce on the length of the day. He had already shown, by astronomical reasoning, that the day had not become shorter by 1/200th of a second since the time of Hipparchus, and thus his inferences agreed with those of Fourier. As far as regards the smallness of the perceptible effect due to the past changes of the Earth's temperature, there can be no doubt that all the curious conclusions just stated are deduced in a manner quite satisfactory from the fact of a general increase of heat in descending below the surface of the Earth. And thus our principles of speculative science have a bearing upon the history of the past changes of the universe, and give us information concerning the state of things in portions of time otherwise quite out of our reach. Heat of the planetary spaces in the same manner, this portion of science is appealed to for information concerning parts of space which are utterly inaccessible to observation. The doctrine of heat leads to conclusions concerning the temperatures of the spaces which surround the Earth, and in which the planets of the solar system revolve. In his memoir, published in 1827, Fourier states that he conceives it to follow from his principles that these planetary spaces, 149, are not absolutely cold, but have a proper heat independent of the sun and of the planets. If there were not such a heat, the cold of the polar regions would be much more intense than it is, and the alternations of cold and warmth arising from the influence of the sun would be far more extreme and sudden than we find them. As the cause of this heat in the planetary spaces, he assigns the radiation of the innumerable stars which are scattered through the universe. Fourier says, "We conclude from these various remarks, and principally from the mathematical examination of the question, that this is so. I am not aware that the mathematical calculation which bears peculiarly upon this point has anywhere been published. But it is worth notice that Svanberg has been led to the opinion of the same temperature in these spaces which Fourier had adopted, 50 centigrade below zero, by an entirely different course of reasoning, founded on the relation of the atmosphere to heat. In speaking of this subject, I have been led to notice incomplete and perhaps doubtful applications of the mathematical doctrine of conduction and radiation. But this may at least serve to show that thermotics is a science, which, like mechanics, is to be established by experiments on masses capable of manipulation, but which, like that, has for its most important office the solution of geological and cosmological problems. I now return to the further progress of our thermotical knowledge. Sect 5. Correction of Newton's law of cooling. In speaking of the establishment of Newton's assumption that the temperature communicated is proportional to the excess of temperature, we stated that it was approximately verified, and afterwards corrected, Chapter I, Sect 1. This correction was the result of the researches of M. Dulong and Petty in 1817, and the researches by which they were led to the true law are an admirable example both of laborious experiment and sagacious induction. They experimented through a very great range of temperature, as high as 240 degrees centigrade, which was necessary because the inaccuracy of Newton's law becomes considerable only at high temperatures. They removed the effect of the surrounding medium by making their experiments in a vacuum. They selected with great 150 judgment the conditions of their experiments and comparisons, making one quantity vary while the others remained constant. In this manner, they found that the quickness of cooling for a constant excess of temperature increases in geometrical progression when the temperature of the surrounding space increases in arithmetical progression. Whereas, according to the Newtonian law, this quickness would not have varied at all. Again, this variation being left out of the account, it appeared that the quickness of cooling, so far as it depends on the excess of temperature of the hot body, increases as the terms of a geometrical progression diminished by a constant number, when the temperature of the hot body increases in arithmetical progression. These two laws, with the coefficients requisite for their application to particular substances, fully determine the conditions of cooling in a vacuum. Starting from this determination, Dulong and Petty proceeded to ascertain the effect of the medium in which the hot body is placed upon its rate of cooling, for this effect became a residual phenomenon when the cooling in the vacuum was taken away. We shall not here follow this train of research, but we may briefly state that they were led to such laws as this: that the rapidity of cooling due to any gaseous medium in which the body is placed is the same so long as the excess of the body's temperature is the same, although the temperature itself vary, that the cooling power of a gas varies with the elasticity according to a determined law.